Hello there, and welcome to Nightfall Science. Tonight, we slow algebra down until every symbol, rule, and equation begins to feel simple. From variables and negative numbers to functions, factoring, and quadratics, we will move gently through the ideas that often seem confusing at first. Let your shoulders relax and allow each step to arrive without pressure. Let's begin. Algebra often becomes confusing before the mathematics itself becomes difficult. A page suddenly fills with letters, numbers begin standing beside symbols, parentheses appear, equal signs seem to divide the page into two separate worlds, and a question that once asked for a simple number now asks for something called x. At first, this can feel like arithmetic has been replaced by a new language, but algebra is not a completely different kind of mathematics. It is arithmetic written in a more flexible form. The numbers still add, they still subtract, they still multiply and divide. Algebra simply allows some of those numbers to remain unknown, changeable, or general. So tonight, we begin with the quietest and most important idea. A letter in algebra is usually standing in place of a number. That is all. The letter is not mysterious. It does not change the rules of arithmetic. It gives us a way to talk about a number before we know exactly what the number is. Imagine a closed box containing several coins. The box is too dark to see inside. We know the coins are there. We simply do not know how many. We could call the unknown number of coins x. In that moment, x becomes a label. It means the number of coins inside the box. Later, perhaps we learn that the box contains 5 coins. Then x equals 5. The letter has not transformed into the number 5. It has been representing 5 all along. We simply discovered its value. This kind of letter is called a variable. The word variable can make the idea sound more complicated than it is. A variable is a symbol, usually a letter, that represents a number. Sometimes the number is unknown. Sometimes it can change. Sometimes the variable stands for every possible number that follows a certain rule. The meaning depends upon the situation. Consider the statement, x plus 3 equals 7. Here, x represents one unknown number. Only one value makes the statement true. That value is 4. 4 plus 3 equals 7. In this problem, x does not move through many values. We are searching for one particular answer. Now consider the statement, y equals x plus 3. This is different. The value of y depends upon the value of x. If x is 1, y is 4. If x is 2, y is 5. If x is 10, y is 13. Here, x and y can vary. They can take many values while preserving the relationship. The same symbol, a variable, can therefore serve two closely related purposes. It may hide a number we are trying to find, or it may describe a number that can change. The surrounding equation tells us which meaning is intended. There is nothing special about the letter x. Mathematicians could use any letter. A problem about time may use t. A problem about distance may use d. A circle's radius may be represented by r. A person's age may be represented by r. The letters are chosen for convenience. They help us remember what the number represents. But a variable called t behaves in exactly the same arithmetic way as a variable called x. The symbol may change. The mathematical rules do not. Algebra also contains numbers that are already known. These are sometimes called constants. A constant is a value that remains fixed within the expression or equation. In x plus 3, the x may be unknown or changeable. The number 3 stays 3. It is constant. In 2x plus 5, both 2 and 5 are fixed numbers. The value of x may vary. The constants do not. A number placed directly beside a variable usually means multiplication. 2x means 2 multiplied by x. We could write 2 times x, but algebra usually removes the multiplication symbol between a number and a variable. This keeps expressions cleaner. Instead of writing 3 times y, we write 3y. Instead of writing 7 times a, we write 7a. The number multiplying the variable is called a coefficient. In 3x, the coefficient is 3. In 12y, the coefficient is 12. In negative 5a, the coefficient is negative 5. The coefficient tells us how many copies of the variable we have. 3x can be imagined as x plus x plus x. 5y means y added to itself 5 times. If x equals 4, then 3x means 3 multiplied by 4. The result is 12. A variable without a visible coefficient still has 1. The expression x really means 1x. Its coefficient is 1. The number 1 is usually left unwritten because writing it adds no new information. In the same way, negative x means negative 1 times x. The invisible coefficient is negative 1. This becomes useful later when expressions are combined. For now, it is enough to remember that every variable term has a coefficient, even when the coefficient is not shown. Algebraic expressions are built from smaller pieces called terms. A term may be a number, a variable, or a product of numbers and variables. In the expression 3x plus 5, there are two terms. 3x is one term, 5 is another. The plus sign separates them. In 4a minus 2b plus 7, there are three terms, 4a, negative 2b, and 7. The subtraction sign can be understood as part of the term that follows it. So instead of thinking of 4a, then a subtraction sign, then 2b, it is often helpful to think of the terms as 4a and negative 2b. This becomes especially useful when rearranging expressions. Terms are separated by addition or subtraction. Multiplication does not separate terms. In 5xy, there is only one term. 5x and y are all multiplied together. In 3 times open parenthesis, x plus 2 close parenthesis, the expression inside the parentheses contains two terms, but the full structure is being multiplied by 3. Learning to see these pieces is one of the quiet skills of algebra. At first, an expression may appear as one long row of symbols. With practice, it begins to separate naturally into parts, coefficients, variables, constants, terms, operations, parentheses. Each part has a role. An algebraic expression is not the same thing as an equation. An expression is a mathematical phrase. It may contain numbers, variables, and operations. For example, x plus 4 is an expression. 3y minus 2 is another expression. 2a squared plus 5a minus 7 is also an expression. An expression does not make a complete claim. It does not say that one thing equals another. It simply describes a value. An equation contains an equal sign. It states that two expressions have the same value. X plus 4 equals 9 is an equation. 3y minus 2 equals 10 is an equation. The equal sign creates a relationship between the left side and the right side. This distinction is simple but important. Expressions can be simplified. Equations can be solved. To simplify an expression means to rewrite it in a cleaner or more useful form without changing its value. To solve an equation means to find the value, or values, that make the equation true. Suppose we have the expression 2x plus 3x. We can simplify it to 5x. We have not discovered what x equals. We have simply combined two groups of x with three more groups of x. The expression is now shorter, but it still depends upon x. Now suppose we have the equation 2x plus 3x equals 20. We can simplify the left side to 5x. Then the equation becomes 5x equals 20. From there, we can solve and discover that x equals 4. Simplifying and solving are connected, but they are not identical. The equal sign itself is often misunderstood. Many people first encounter it in arithmetic as a signal that the answer is coming. 3 plus 4 equals 7. The equal sign appears just before 7, so it can begin to feel like it means, now calculate the result. But the equal sign has a deeper meaning. It means the expression on one side has exactly the same value as the expression on the other side. It describes balance. 7 equals 3 plus 4 is just as true as 3 plus 4 equals 7. The equal sign does not point in one direction. It connects two equivalent quantities. Imagine a perfectly balanced scale. The left side holds one collection of objects. The right side holds another. If the scale is balanced, the total weight on the left equals the total weight on the right. The collections may look different. Their values are the same. An equation works in this way. X plus 3 may look different from 7, but when x is 4, both sides have the same value. The equation is balanced. This idea of balance explains almost every basic method used to solve equations. Whatever is done to one side must also be done to the other. If 3 is removed from the left side, 3 must also be removed from the right. If the left side is divided by 2, the right side must also be divided by 2. The goal is to keep the equation balanced while gradually isolating the variable. Suppose x plus 3 equals 7. We want x by itself. The left side contains x and an added 3. To remove the 3, subtract 3. But we cannot subtract 3 only from the left side. That would change the balance. We subtract 3 from both sides. x plus 3 minus 3 equals 7 minus 3. The positive 3 and negative 3 cancel. The result is x equals 4. The method is not a trick. It is the preservation of equality. Both sides were changed in exactly the same way, so they remain equal. This also explains why solving an equation often uses inverse operations. Addition and subtraction undo each other. Multiplication and division undo each other. Squaring and taking a square root can undo each other under appropriate conditions. When a variable is surrounded by operations, we gently reverse those operations. If 5 has been added, subtract 5. If the variable has been multiplied by 3, divide by 3. If it has been divided by 4, multiply by 4. The aim is to return the variable to a simpler state, but the equation must remain balanced throughout. Algebra sometimes feels confusing because the operations are written compactly. Take the expression 2x plus 6. This means first multiply x by 2, then add 6. If x equals 4, 2x becomes 8. Then 8 plus 6 becomes 14. The order matters. If we added 6 to x first and then multiplied by 2, we would have 2 times open parenthesis, x plus 6 close parenthesis. That is a different expression. When x equals 4, x plus 6 is 10. 2 times 10 is 20. 14 and 20 are not the same. Parentheses show which part should be treated as a group. They are like quiet walls around an expression. Everything inside belongs together. Operations outside the parentheses act upon the entire group. 3 times open parentheses, x plus 2 close parentheses, means 3 multiplied by the complete quantity x plus 2. If x equals 4, the quantity inside is 6. 3 times 6 is 18. The expression 3x plus 2 is different. If x equals 4, 3x is 12. Then 2 is added. The result is 14. Parentheses change structure. They are not decoration. They tell us how the expression has been assembled. One of the most useful habits in algebra is substitution. To substitute means to replace a variable with a known value. Suppose the expression is 3x plus 2 and x equals 5. We replace x with 5. The expression becomes 3 times 5 plus 2. 3 times 5 is 15. 15 plus 2 is 17. Substitution allows us to test an expression for a particular value. It also allows us to check whether a solution is correct. Suppose we solve x plus 7 equals 12 and conclude that x equals 5. We can substitute 5 back into the original equation. 5 plus 7 equals 12. That statement is true. So the solution works. If we had concluded that x equals 6, substitution would produce 6 plus 7 equals 12. That becomes 13 equals 12. This is false. The attempted solution does not work. Checking by substitution is calm and reliable. It is especially useful when equations become longer. A small error may hide inside several steps. Substitution brings the final answer back to the beginning and asks one simple question: does this value make the original equation true? Algebra also uses conventions. These are agreed ways of writing that prevent expressions from becoming cluttered. A number beside a variable means multiplication. A variable written over a number may indicate division. An exponent tells us how many times a quantity is multiplied by itself. A fraction bar acts like parentheses around both the numerator and the denominator. These conventions allow a large amount of meaning to fit into a small space. But compact writing can feel dense until the symbols are translated into words. Whenever an expression seems confusing, it can help to read it slowly. 2x plus 5 means 2 multiplied by x, then 5 added. X squared means x multiplied by itself. 3 open parenthesis. X minus 4 close parenthesis means 3 multiplied by the entire difference between x and 4. A fraction with x plus 2 on top and 5 underneath means the whole quantity, x plus 2 divided by 5. Reading aloud reveals the structure. The symbols begin to behave like a sentence. There are also several common symbols that can all represent multiplication. A small cross may be used in basic arithmetic. A centered dot may appear in algebra. Parentheses placed side by side can mean multiplication. A number beside a variable means multiplication. 2 open parenthesis, x plus 1 close parenthesis, means 2 multiplied by x plus 1. Open parenthesis, x plus 1 close parenthesis, open parenthesis, x minus 1 close parenthesis, means the first quantity multiplied by the second. The symbol changes to prevent confusion. The letter x is often used as a variable. Using a multiplication cross beside it could make the expression difficult to read, so algebra prefers dots, parentheses, or simple placement. Division also appears in several forms. There is the division symbol. There is a fraction bar. There may be a slash in typed mathematics. They all describe a quantity being divided by another. But a fraction bar also groups its entire top and bottom. The expression x plus 2, all divided by 3, means add 2 to x first, then divide the result by 3. The grouping is built into the fraction. This is one reason fractions become important in algebra. They are not only numbers like 1/2 or 3/4. They can contain complete expressions. Another early source of confusion is that letters placed beside one another mean multiplication. The expression AB means A multiplied by B. It does not mean a two-digit number. It does not mean the letters form one new variable called AB, unless the context specifically defines it that way. Usually, individual letters written together represent a product. 3AB means 3 multiplied by A multiplied by B. The order of multiplication does not matter for ordinary real numbers. 3AB has the same value as B times 3 times A. Algebra usually places the numerical coefficient first, followed by variables in alphabetical order. This is a writing convention. It keeps expressions consistent. The value remains unchanged if the factors are rearranged. Addition behaves similarly. X plus y has the same value as y plus x. This is called the commutative property. Multiplication is also commutative. X times y equals y times x. Subtraction is not. X minus y is generally not equal to y minus x. Division is not commutative either. X divided by y is generally not equal to y divided by x. These differences matter. Operations that look related do not always share the same properties. Another useful property is association. When several numbers are added, grouping them differently does not change the sum. Open parenthesis a plus b, close parenthesis plus c, has the same value as a plus, open parenthesis b plus c, close parenthesis. Multiplication behaves the same way, but subtraction and division do not. Grouping changes their results. This is why parentheses must be respected. They show the intended association. Then there is the distributive property. This connects multiplication with addition. 3 times open parenthesis x plus 2 close parenthesis can be rewritten as 3x plus 6. The 3 multiplies every term inside the parentheses. 3 times x becomes 3x. 3 times 2 becomes 6. The expression has been expanded. Nothing has changed in value. Only the form has changed. If x equals 4, the original expression gives 3 times 6, which is 18. The expanded expression gives 12 plus 6, which is also 18. The distributive property is one of the central movements of algebra. It allows parentheses to be opened. It allows common factors to be pulled out. It appears in simplifying expressions, solving equations, multiplying polynomials, and factoring. For now, it can be imagined as sharing. A number outside the parentheses is shared with every term inside. 2 times open parentheses, a plus b, close parentheses, becomes 2a plus 2b. Negative 3 times open parentheses, x minus 4 close parentheses, becomes negative 3x plus 12. The second example deserves a slow look. Negative 3 multiplied by x gives negative 3x. Negative 3 multiplied by negative 4 gives positive 12. The negative sign outside must be distributed too. Signs are part of the numbers. They travel with the multiplication. Many algebra mistakes come from distributing to the first term and forgetting the rest. The outside factor must reach every term within the parentheses. No term is skipped. It is like light filling the entire enclosed space. Each part is affected. Finally, algebra becomes easier when expressions are viewed as instructions rather than decorations. The expression 2x plus 3 tells us what to do with a number. Start with the number represented by x. Multiply it by 2, then add 3. It is a small machine. A number enters. Operations are performed. A result emerges. If 5 enters, 13 emerges. If 10 enters, 23 emerges. If negative 2 enters, negative 1 emerges. Thinking of expressions as machines prepares us for functions later. For now, it reminds us that an expression has structure. It is a sequence of operations acting upon a value. The letters do not make algebra uncertain. They make it general. Arithmetic may tell us that 3 apples plus 5 apples equals 8 apples. Algebra allows us to say that x apples plus 5 apples equals x plus 5 apples. The statement works whether x is 2, 10, or 1000. One expression describes many possible situations. This is the power of algebra. It does not abandon numbers. It reveals patterns that remain true across many numbers. A variable is a place where a number may enter. A coefficient tells us how many copies are present. A term is one piece of an expression. A constant remains fixed. An equation states that 2 expressions are equal. Parentheses preserve groups. Substitution replaces a variable with a value. Inverse operations help us isolate what is unknown. And the equal sign keeps the entire structure balanced. These ideas are the foundation beneath almost everything that follows. They may appear simple when separated. Confusion often comes when they arrive together, so there is no need to rush. A long expression is only a collection of smaller familiar pieces. A complicated equation is only a balance containing operations. Every symbol can be read, every operation can be traced, and every unknown value can be approached one careful step at a time. In the next part, we will move slowly through negative numbers, signs, subtraction, absolute value, and the rules that make expressions change from positive to negative. Negative numbers often feel confusing because they ask us to imagine less than nothing. With ordinary counting numbers, the meaning feels physical. 1 apple, 2 books, 5 stars. The number tells us how many objects are present. But negative 3 apples does not usually describe a pile of fruit. So negative numbers require a different kind of picture. They describe direction, position, change, debt, temperature, or distance from a reference point. The number 0 becomes the center. Positive numbers lie on one side. Negative numbers lie on the other. Imagine a number line stretching quietly in both directions. 0 rests in the middle. To the right are 1, 2, 3, 4, and numbers continuing without end. To the left are -1, -2, -3, -4, and numbers continuing without end in the opposite direction. Positive numbers move to the right. Negative numbers move to the left. This simple line gives negative numbers a place to exist. -3 is not less real than +3. It is simply 3 units to the left of 0. +3 is 3 units to the right. The two numbers are opposites. They have the same distance from 0, but they point in different directions. This idea of direction appears in many real situations. A temperature of 5 degrees above 0 can be represented by +5. A bank balance of $20 means money is available. A balance of -$20 may mean $20 is owed. An elevator on floor 4 is above the reference level. A parking level marked -2 may be 2 floors below it. The negative sign does not always mean something bad. It means the quantity lies in the opposite direction from the chosen positive direction. If east is positive, west may be negative. If upward motion is positive, downward motion may be negative. If profit is positive, loss may be negative. The meaning depends upon the reference system. In algebra, a negative sign can play several roles. It may be part of a number, -5. It may indicate subtraction, 7 minus 5. Or it may mean taking the opposite of a quantity, -x. These ideas are closely connected, but they are not identical. Consider -5. Here, the negative sign belongs to the number. It tells us the number is 5 units below 0 on the number line. Now consider 7 minus 5. The minus sign describes an operation. It tells us to subtract 5 from 7. The result is +2. Now consider -x. This means the opposite of x. If x is +4, -x is -4. If x is -4, -x is +4. The negative sign does not guarantee that the final value is below 0. It reverses the sign of whatever x already is. This is an important point. -x is not always a negative number. Its value depends upon x. If x equals 10, -x equals -10. If x equals -10, -x equals +10. If x equals 0, -x is still 0. The symbol means take the opposite. The same idea appears in expressions such as negative open parenthesis, x plus 3, close parenthesis. The negative sign applies to the entire grouped quantity. It means take the opposite of x plus 3. This can also be understood as multiplying the quantity by -1. negative open parenthesis, x plus 3, close parenthesis, becomes negative x minus 3. The sign of every term inside changes. Positive x becomes negative x. Positive 3 becomes negative 3. If the expression were negative open parenthesis, x minus 3 close parenthesis, the result would be negative x plus 3. The x changes from positive to negative. The negative 3 changes to positive 3. Every term inside is multiplied by negative 1. The signs reverse. Negative numbers become especially confusing when subtraction is involved. Many learners are told that two negatives make a positive. This phrase can be useful, but it is incomplete. Two negative signs do not always create a positive result merely because they appear near each other. Their relationship matters. When a negative number is subtracted, subtraction of a negative becomes addition. 5 minus negative 2 becomes 5 plus 2. The result is 7. On the number line, begin at 5. Subtracting positive 2 would move 2 units left, but subtracting negative 2 reverses the direction. The movement goes 2 units right. The result is 7. Another way to understand this is through opposites. Subtracting a number means adding its opposite. 5 minus 2 is the same as 5 plus negative 2. 5 minus negative 2 means 5 plus the opposite of negative 2. The opposite of negative 2 is positive 2. So the expression becomes 5 plus 2. This rule works consistently. 8 minus negative 3 becomes 8 plus 3. Negative 4 minus negative 6 becomes negative 4 plus 6. That result is positive 2. But two negative numbers being added do not automatically create a positive. Negative 3 plus negative 5 is negative 8. Both quantities move in the negative direction. Start at negative 3, move 5 more units left. The result is negative 8. So the phrase two negatives make a positive applies most clearly when negative signs are multiplied or divided, or when one negative sign removes another through subtraction. It does not describe every expression containing two negative numbers. Addition with signed numbers becomes easier when direction is remembered. Positive means movement to the right. Negative means movement to the left. For positive 3 plus positive 4, begin at 3 and move 4 units right. The result is 7. For negative 3 plus negative 4, begin at negative 3 and move 4 units left. The result is negative 7. When the signs are the same, the distances combine, the common sign remains. Positive 5 plus positive 2 is positive 7. Negative 5 plus negative 2 is negative 7. When the signs are different, the directions oppose one another. Positive 7 plus negative 3 means begin at 7 and move 3 units left. The result is 4. Negative 7 plus positive 3 means begin at negative 7 and move 3 units right. The result is negative 4. A practical rule is to compare the distances from 0. Subtract the smaller distance from the larger. Then keep the sign of the number farther from 0. For negative 9 plus positive 4, the distances are 9 and 4. 9 is larger. 9 minus 4 is 5. The number with the larger distance was negative 9, so the answer is negative 5. For positive 12 plus negative 7, 12 has the larger distance. 12 minus 7 is 5. The larger number was positive, so the result is positive 5. This method works because opposite directions cancel. A positive unit and a negative unit together make 0. Imagine positive and negative tokens. One positive token paired with one negative token disappears into a 0 pair. If we have 7 positive tokens and 3 negative tokens, 3 pairs cancel. 4 positive tokens remain. The result is positive 4. If we have 8 negative tokens and 5 positive tokens, 5 pairs cancel. 3 negative tokens remain. The result is negative 3. This picture is useful when variables are involved. 3x plus negative 2x can be written as 3x minus 2x. One positive x remains, so the result is x. Negative 5y plus 2y leaves 3 negative y terms. The result is negative 3y. Like terms combine according to the same signed number rules. The variables tell us what kind of quantity we have. The coefficients tell us how many positive or negative copies are present. Subtraction can always be rewritten as addition of the opposite. This is one of the most useful transformations in algebra. 7 minus 4 becomes 7 plus negative 4. X minus 5 becomes x plus negative 5. 3a minus negative 2a becomes 3a plus positive 2a. Rewriting subtraction this way allows addition rules to handle everything. Instead of memorizing separate rules for every possible subtraction problem, we change subtraction into addition. Then we combine signed quantities. Consider -3 minus 5. Rewrite it as -3 plus -5. Both numbers are negative. The result is -8. Now consider -3 minus -5. Rewrite it as -3 plus +5. The signs are different. 5 has the larger distance from 0. 5 minus 3 is 2. The result is +2. The transformation makes the structure clearer. Parentheses are especially important around negative numbers. Suppose we substitute -4 for x in the expression x squared. We should write open parenthesis -4 close parenthesis squared. The parentheses show that the entire negative number is being squared. -4 multiplied by -4 equals +16. But the expression -4 squared, written without grouping, may be interpreted as the negative of 4 squared. The exponent applies to 4 first. 4 squared is 16. Then the negative sign remains outside. The result is -16. These two expressions look similar. They represent different structures. Open parenthesis -4 close parenthesis squared equals +16. Negative open parenthesis 4 squared close parenthesis equals -16. The position of the parentheses determines whether the negative sign is part of the quantity being squared. This distinction becomes important when substituting negative values. Whenever a variable is replaced by a negative number, placing the number in parentheses is a reliable habit. If the expression is 3x squared plus 2x and x equals -2, write 3 open parenthesis -2 close parenthesis squared plus 2 open parenthesis -2 close parenthesis. Now the structure is visible. -2 squared is +4, 3 times 4 is 12, 2 times -2 is -4, 12 plus -4 is 8. Without parentheses, signs can easily become lost. Multiplying signed numbers follows a pattern. Positive times positive gives positive. Positive times negative gives negative. Negative times positive gives negative. Negative times negative gives positive. The same pattern applies to division. Numbers with the same sign produce a positive result. Numbers with different signs produce a negative result. This rule can be remembered through direction. Multiplying by a positive number preserves direction. Multiplying by a negative number reverses direction. Start with +3. Multiply by +2. The direction remains positive. The result is +6. Start with +3. Multiply by -2. The negative factor reverses the direction. The result is -6. Start with -3. Multiply by -2. The first number is already negative. The second negative reverses that direction. The result becomes +6. A negative factor acts like a reflection across 0. One negative sign reverses direction once. 2 negative signs reverse direction twice. After 2 reversals, the quantity points in the original positive direction. This gives a deeper meaning to the rule that negative times negative is positive. It is not an arbitrary exception. It preserves the consistency of arithmetic. We can see this through the distributive property. Begin with 0. 0 can be written as 3 plus -3. Now multiply the entire expression by -2. -2 times open parenthesis. 3 plus -3, close parenthesis, must equal -2 times 0. The result is 0. Distribute the -2. -2 times 3 is -6. The second product is -2 times -3. The two results must add to 0. Since the first is -6, the second must be +6. Therefore, -2 times -3 equals +6. The positive result is required to keep distribution consistent. Sign rules also apply to several factors. Consider -2 times -3 times -4. Multiply 2 factors at a time. -2 times -3 is +6. +6 times -4 is -24. There were 3 negative factors. The final result is negative. With 4 negative factors, the result would be positive. An even number of negative factors produces a positive product. An odd number produces a negative product. Each negative factor reverses the sign. An even number of reversals returns to positive. An odd number leaves the direction reversed. Exponents create repeated multiplication, so the same pattern appears. -2 in parentheses, raised to the second power, is +4. There are two negative factors. -2 in parentheses, raised to the third power, is -8. There are three negative factors. -2 in parentheses, raised to the fourth power, is +16. There are four negative factors. A negative base raised to an even power gives a positive result. A negative base raised to an odd power gives a negative result. Without them, an expression such as -x² usually means take x squared first, then apply the negative sign. If x is 3, -x² is -9, but open parenthesis, -x close parenthesis squared is +x². The structure matters more than the appearance. Absolute value introduces another way of thinking about signs. The absolute value of a number is its distance from 0. Distance is never negative. The absolute value of +5 is 5. The absolute value of -5 is also 5. Both numbers lie 5 units from 0. Absolute value is written with vertical bars. The absolute value of x asks how far x is from 0. It does not ask whether x lies to the left or right. It ignores direction and keeps only distance. This means the absolute value of any real number is 0 or positive. It can never be negative. The absolute value of 0 is 0. The absolute value of -12 is 12. The absolute value of +12 is 12. But absolute value does not simply mean remove the negative sign. That shortcut works when the value inside is already known. With a variable, the sign may not be known. The absolute value of x equals x when x is 0 or positive. It equals -x when x is negative. This second statement may look strange. Suppose x is -4, then -x is +4. So the absolute value becomes 4 as expected. The expression changes according to the sign of x. Absolute value equations often have two solutions, because 2 points can share the same distance from 0. The equation absolute value of x equals 5 asks which numbers are 5 units from 0. One number is +5, the other is -5. So x equals 5 or x equals -5. The equation does not ask for one direction. It asks for a distance. There are usually 2 points at a given positive distance from 0. If the equation were absolute value of x equals 0, there would be only one solution. Only 0 lies 0 units from 0. If the equation were absolute value of x equals -3, there would be no solution among real numbers. A distance cannot equal -3. Absolute value also describes distance between two numbers. The distance between x and 3 can be written as the absolute value of x minus 3. If x is 8, the difference is 5. The distance is 5. If x is -2, the difference is -5. The absolute value is again 5. The sign of the subtraction depends upon which point lies farther right. Absolute value removes that directional sign and keeps the distance. This becomes useful in equations, inequalities, measurement, and error. A temperature within 2 degrees of 20 can be described using absolute value. A measured length within a small tolerance of a target can also be described this way. The notation is compact. The meaning remains distance. Negative signs also interact with fractions. A fraction is negative when its numerator and denominator have different signs. -3/5 is negative. 3/-5 is also negative. -3/-5 is positive. Two negative signs cancel through division. The negative sign may be placed in front of the entire fraction. These forms are equivalent. -3/5, -3/+5, +3/-5. They all represent the same number. For clarity, algebra usually places one negative sign in front of the fraction. When both numerator and denominator are negative, the fraction simplifies to positive. Signs can also be factored. Consider -3x minus 6. Both terms contain -3. Factoring out -3 gives -3 times open parenthesis, x plus 2 close parenthesis. To check, distribute. -3 times x is -3x. -3 times +2 is -6. Sometimes factoring out a negative number makes the expression inside the parenthesis simpler. For example, 3 minus x can be written as negative open parenthesis, x minus 3 close parenthesis. Distribute the negative 1. Negative x plus 3. Rearranged, this is 3 minus x. The two forms are equal. This relationship appears frequently when factoring expressions and comparing formulas. One expression may look reversed. A negative factor may reveal that the structures are actually the same. The order of numbers on the number line also becomes important. Positive 5 is greater than positive 2 because it lies farther right. Negative 2 is greater than negative 5 for the same reason. Although 5 has a larger absolute value than 2, negative 5 lies farther left, so negative 5 is smaller. Among negative numbers, the number closer to 0 is greater. Negative 1 is greater than negative 10. A debt of 1 unit is a larger financial position than a debt of 10 units. A temperature of negative 1 degree is warmer than negative 10 degrees. The number line makes this clear. Greater always means farther right. Less always means farther left. This remains true whether the numbers are positive or negative. When inequalities are solved, one special sign rule appears. Multiplying or dividing both sides by a negative number reverses the inequality symbol. Suppose negative 2x is greater than 6. Divide both sides by negative 2. The result is x less than negative 3. The direction reverses. This happens because multiplication by a negative number reflects the number line. Greater values move to the opposite side after reflection. Consider the true statement, 3 is greater than 1. Multiply both numbers by negative 1. Negative 3 and negative 1 appear. But negative 3 is less than negative 1. The order has reversed. Therefore, an inequality symbol must reverse whenever both sides are multiplied or divided by a negative quantity. Equations do not need this change because equality is symmetric. If two quantities are equal, their negatives remain equal. But inequalities describe order. Negative multiplication reverses that order. We will return to inequalities more fully later. For now, it is enough to remember that the sign change is not an extra rule without meaning. It reflects the entire number line across 0. Negative numbers become easier when each symbol is given a role. A negative sign may belong to a number. It may reverse a quantity. It may appear because subtraction has been rewritten as addition. Two nearby negative signs may create addition, or they may belong to separate terms. Parentheses show which quantity a sign controls. Absolute value removes direction and keeps distance. Multiplication by a negative reverses direction. An even number of reversals returns to positive. An odd number leaves the result negative. None of these ideas needs to be rushed. When an expression contains many signs, slow it down, circle or imagine each term. Notice the parentheses. Rewrite subtraction as addition of the opposite. Multiply one pair of factors at a time. Substitute negative values inside parentheses. Check the final answer on the number line. A complicated row of signs is still built from simple movements. Left, right, towards 0, away from 0, a reversal. Then perhaps another reversal. Negative numbers do not create a separate mathematics. They complete the number line. Without them, subtraction would sometimes have nowhere to go. Equations describing debt, direction, temperature, and change would remain incomplete. With negative numbers, algebra can move freely on both sides of 0. The line no longer begins. It extends quietly in both directions. In the next part, we will move through the order of operations, parentheses, exponents, fractions, and the reason algebraic steps must be performed in a careful sequence. Algebra becomes much easier when every operation is performed in a clear and predictable order. Without an agreed order, the same expression could produce several different answers. One person might add first. Another might multiply first. A third might begin on the right side. The symbols would remain the same, but the result would depend upon the reader. Mathematics avoids this confusion by using a shared order of operations. The order is not meant to make expressions difficult. It exists so that everyone reads the same expression in the same way. Consider the expression 3 plus 4 times 2. There are two possible operations, addition and multiplication. If we add 3 and 4 first, we get 7. Then 7 times 2 gives 14. If we multiply 4 and 2 first, we get 8. Then add 3. The answer becomes 11. Both calculations appear possible unless an order has been established. Under the standard order of operations, Multiplication is performed before addition, so 3 plus 4 times 2 equals 11. The multiplication belongs together first, then the addition is completed. This does not mean multiplication is more important than addition. It simply has greater priority when both appear without extra grouping. The usual order begins with grouping symbols, then exponents, then multiplication and division, then addition and subtraction. Grouping symbols include parentheses, brackets, and fraction bars. They tell us which quantities must be handled together. Exponents describe repeated multiplication. Multiplication and division share the same level. Addition and subtraction also share the same level. Operations on the same level are performed from left to right. This last detail is important. Multiplication does not always come before division. They are equal in priority. Addition does not always come before subtraction. They are equal as well. When equal priority operations appear in one line, move from left to right. Consider 12 divided by 3 times 2. Division and multiplication share the same level. Begin on the left. 12 divided by 3 is 4. Then 4 times 2 is 8. The answer is 8. It would be incorrect to multiply 3 and 2 first, merely because multiplication appears in a remembered phrase before division. The expression is not 12 divided by 6, unless parentheses create that grouping. 12 divided by open parentheses, 3 times 2 close parentheses would equal 2. The parentheses make the denominator a complete group. Without parentheses, left to right order gives 8. The same principle applies to addition and subtraction. 10 minus 4 plus 2. Begin from the left. 10 minus 4 is 6. 6 plus 2 is 8. If 4 and 2 were added first, the result would be 4. But no parentheses tell us to combine them, so the correct result is 8. The familiar phrase used to remember the order can sometimes cause confusion. People may remember parentheses, exponents, multiplication, division, addition, subtraction, but this should not be interpreted as 6 completely separate levels. Multiplication and division belong together. Addition and subtraction belong together. A more accurate picture is 4 stages. First, grouping. Second, exponents. Third, multiplication and division from left to right. Fourth, addition and subtraction from left to right. This structure remains reliable. Parentheses come first because they define a group. Consider 2 times open parentheses, 3 plus 4 close parentheses. The quantity inside the parentheses must be found first. 3 plus 4 is 7. Then 2 times 7 is 14. Without the parentheses, 2 times 3 plus 4 would be interpreted as 6 plus 4. The result would be 10. The parentheses change the expression's structure. They tell us that the addition is part of one complete quantity being multiplied by 2. Parentheses may also appear inside other parentheses. When grouping symbols are nested, begin with the innermost group. Work outward one layer at a time. Consider 2 times open parentheses, 3 plus open parentheses, 4 minus 1 close parentheses. The innermost group is 4 minus 1. That becomes 3. The expression is now 2 times open parentheses, 3 plus 3 close parentheses. The remaining parentheses contain 6. 2 times 6 is 12. Each layer is opened only after the layer inside has been simplified. This is like unpacking nested boxes. The smallest box is opened first, then the next, then the outermost container. Brackets and braces may be used when several layers of grouping appear. They function like parentheses. Their different shapes simply make the structure easier to see. An expression might contain braces outside, brackets in the middle, and parentheses inside. The mathematical rule does not change. Begin with the innermost group, then move outward. A fraction bar also creates grouping. Everything above the bar belongs to the numerator. Everything below belongs to the denominator. Suppose we have the quantity 3 plus 5, all divided by 4. The numerator is 3 plus 5. That entire group is divided by 4. First calculate the numerator. 3 plus 5 is 8. Then 8 divided by 4 is 2. This is different from 3 plus 5 divided by 4. Without the fraction grouping, division happens before addition. 5 divided by 4 is 1 and 1/4. Then 3 is added. The result is 4 and 1/4. A fraction bar silently performs the work of parentheses. It groups the complete numerator and the complete denominator. When reading algebra aloud, it is helpful to say the whole quantity. The quantity 3 plus 5 divided by 4. This reminds us that the addition belongs together. Parentheses also appear during substitution. Suppose the expression is 2x squared minus 3x, and x equals -4. Replace every x with -4 inside parentheses. 2 times open parentheses, -4 close parentheses squared, minus 3 times open parentheses, -4 close parentheses. Now follow the order. The exponent comes before the surrounding multiplication. -4 squared is +16. 2 times 16 is 32. 3 times -4 is -12. The expression says 32 minus -12. Subtracting a negative becomes addition. The final result is 44. Each step becomes manageable when the order is respected. Trying to perform everything at once invites signs and powers to become mixed. Exponents are performed after grouping and before ordinary multiplication. An exponent tells us how many times the base is used as a factor. 3 squared means 3 times 3. The result is 9. 2 cubed means 2 times 2 times 2. The result is 8. The small raised number is the exponent. The quantity being repeated is the base. In 5 squared, 5 is the base and 2 is the exponent. In x cubed, x is the base and 3 is the exponent. In open parenthesis, x plus 2 close parenthesis squared, the entire quantity x plus 2 is the base. The parentheses show that the whole expression is multiplied by itself. Open parenthesis, x plus 2 close parenthesis squared means open parenthesis, x plus 2 close parenthesis times open parenthesis, x plus 2 close parenthesis. It does not mean x squared plus 2 squared. This is one of the most common misunderstandings involving exponents. An exponent applied to a sum does not automatically distribute across addition. Open parenthesis, x plus 2 close parenthesis squared is not equal to x squared plus 4. To see why, let x equal 3. The original expression becomes open parenthesis, 3 plus 2 close parenthesis squared. 5 squared is 25. The incorrect version would give 3 squared plus 4. 9 plus 4 is 13. 25 and 13 are not equal. The square acts on the whole group. Multiplying the binomial by itself produces an additional middle term. Open parenthesis, x plus 2 close parenthesis squared becomes x squared plus 4, x plus 4. That fuller pattern will appear later when we study polynomials. For now, the important idea is that powers do not distribute across addition or subtraction. They do distribute across multiplication. Open parenthesis, 3x close parenthesis squared means 3x times 3x. 3 times 3 is 9. X times x is x squared. So the result is 9x squared. The square affects both factors because they are multiplied together inside the parentheses. Similarly, open parenthesis, a close parenthesis, cubed becomes a cubed b cubed. The entire product is repeated 3 times, but open parenthesis, a plus b, close parenthesis, cubed, cannot be simplified by cubing each term alone. Addition creates interactions between the terms when the expression is multiplied by itself. Exponents have several special cases. Any Kunoa number raised to the first power remains unchanged. 7 to the first power is 7. X to the first power is x. The exponent 1 is usually not written. When we see x, we may think of it as x to the first power. Any Kunoa number raised to the 0 power equals 1. 5 to the 0 power equals 1. X to the 0 power equals 1, provided x is not 0. This rule may initially seem strange. 0 repeated multiplications do not create an obvious picture, but the rule keeps exponent patterns consistent. Consider powers of 2. 2 cubed is 8. 2 squared is 4. 2 to the first power is 2. Each time the exponent decreases by 1, the value is divided by 2. Continue the pattern. 2 to the 0 power must be 2 divided by 2. The result is 1. The same reasoning works for every Tungoo base. 3 squared is 9. 3 to the first power is 3. 3 to the 0 power is 1. Each downward step divides by 3. The expression 0 to the 0 power is treated separately and may be left undefined or assigned meaning only within certain contexts. In elementary algebra, it is safest not to assume that 0 to the 0 power equals 1. Negative exponents also continue the pattern. 2 to the negative first power means 1/2. 2 to the negative second power means 1/4. A negative exponent does not make the value negative, it creates a reciprocal. X to the negative 1 equals 1 divided by x. X to the negative 2 equals 1 divided by x squared. Again, x cannot be 0 because division by 0 is not allowed. The negative sign belongs to the exponent. It tells us to move the factor to the opposite side of a fraction bar. The sign of the resulting number depends upon the base. Negative 2 raised to the negative third power means 1 divided by negative 2 cubed. Negative 2 cubed is negative 8, so the result is negative 1/8. The exponent determines repetition and reciprocal structure. The base determines the sign pattern. Exponents also follow their own laws when multiplied or divided. When powers with the same base are multiplied, their exponents are added. X squared times x cubed becomes x to the fifth power. This works because x squared means 2 factors of x. X cubed means 3 factors of x. Together, there are 5 factors. X times x times x times x times x. So the result is x to the fifth power. The bases must be the same for this shortcut. X squared times y cubed cannot become a single power unless x and y have a known relationship. The expression remains x squared y cubed. When powers with the same base are divided, the exponents are subtracted. X to the fifth divided by x squared becomes x cubed. 5 factors of x appear on top, 2 appear below, 2 pairs cancel, 3 factors remain in the numerator. This rule assumes x is not 0. If the exponent on the bottom is larger, the result can be written with a negative exponent, or as a reciprocal. X squared divided by x to the fifth becomes x to the negative third. This is the same as 1 divided by x cubed. The exponent subtraction gives 2 minus 5, which is negative 3. The negative exponent records that 3 factors remain in the denominator. When a power is raised to another power, the exponents are multiplied. Open parenthesis, x squared, close parenthesis, cubed, means x squared multiplied by itself 3 times. Each copy contributes 2 factors of x. 3 groups of 2 create 6. So the result is x to the sixth power. This differs from multiplying 2 separate powers. X squared times x cubed adds the exponents. A power raised to a power multiplies them. The written structure tells us which rule applies. Parentheses make that structure visible. Order of operations becomes especially important with exponents and negative signs. Negative 3 squared, without parentheses around negative 3, is interpreted as the negative of 3 squared. The exponent applies to 3. 3 squared is 9. The negative sign remains outside. The result is negative 9. Open parentheses. Negative 3 close parentheses squared means the entire negative number is the base. Negative 3 times negative 3 is positive 9. These expressions differ only by parentheses, but the results have opposite signs. When a negative value is intended as the base, it must be grouped. The same issue appears with variables. Negative x squared means negative open parentheses. X squared, close parentheses. Open parenthesis. Negative x close parenthesis squared means negative x times negative x, which becomes positive x squared. A small pair of parentheses can change the whole expression. This is why careful notation matters. Fractions create another area where order and grouping become essential. A fraction represents division. 3/4 means 3 divided by 4. The numerator is the quantity being divided. The denominator is the quantity we divide by. The denominator cannot equal 0. Division by 0 is undefined. To understand why, remember that division asks how many groups of one quantity fit inside another. 12 divided by 3 is 4 because 3 times 4 equals 12. If 12 divided by 0 had an answer, there would need to be some number that satisfies 0 times that number equals 12. But 0 times every number is 0. It can never equal 12. So no answer exists. 0 divided by a Tungoo number is allowed. 0 divided by 5 equals 0, because 5 times 0 equals 0. The confusion comes from reversing the positions. 0 in the numerator is acceptable when the denominator is Tungoo. 0 in the denominator is not. Fractions can be simplified by dividing the numerator and denominator by the same Tungoo factor. 6/8 can be simplified to 3/4. Both 6 and 8 are divisible by 2. Dividing the top and bottom by 2 does not change the fraction's value. It changes only its form. This works because dividing by the same number in the numerator and denominator is equivalent to multiplying by 1. 2 over 2 equals 1. Multiplying or dividing by 1 preserves value. Algebraic fractions follow the same principle. 6x over 8 can simplify to 3x over 4. The numerical factor of 2 cancels, but cancellation must involve factors, not terms separated by addition. Consider the fraction open parenthesis, x plus 2 close parenthesis over x. The x in the denominator cannot cancel with the x inside the sum. The numerator is not x times 2, it is x plus 2. There is no common factor of x across the entire numerator. Cancellation only works when the same factor multiplies every part. For example, open parenthesis, x times open parenthesis, x plus 2 close parenthesis over x can simplify. The numerator contains x as a factor. The denominator is x. The common factor cancels, provided x is not 0. The result is x plus 2. But x plus 2 over x must remain as written, or be separated into x over x plus 2 over x. That becomes 1 plus 2 over x. The distinction between terms and factors is central. Terms are separated by addition or subtraction. Factors are multiplied. Only factors can cancel. A common mistake is to cross out symbols that look alike without checking the structure. The expression x plus 3 over x plus 5 does not allow the x terms to cancel. The numerator is one sum. The denominator is another. Neither x is a factor of the entire group. If the expressions were x times open parenthesis, x plus 3 close parenthesis, over x times open parenthesis, x plus 5 close parenthesis, then the common factor x could cancel. Parentheses and multiplication reveal why. When adding fractions, the denominators must match. 1/3 plus 1/3 equals 2/3. Both fractions describe pieces of the same size. The numerators can be combined, but 1/2 plus 1/3 cannot become 2/5. Halves and thirds are different sized pieces. They must first be rewritten using a common denominator. The smallest common denominator for 2 and 3 is 6. 1/2 becomes 3/6. 1/3 becomes 2/6. Now the pieces match. 3/6 plus 2/6 equals 5/6. The denominator remains 6 because we are counting 6th-sized pieces. Algebraic fractions work the same way. 1 over x plus 1 over y requires a common denominator. A common denominator is xy. 1 over x becomes y over xy. 1 over y becomes x over xy. The sum becomes x plus y over xy. The denominators do not simply add. The fractions must first be expressed in the same units. Subtraction follows the same process. 3 over x minus 1 over y becomes 3y over xy minus x over xy. The result is 3y minus x over xy. Parentheses may be needed around a multi-term numerator. They preserve the subtraction as one grouped quantity. Multiplying fractions is more direct. Multiply the numerators, then multiply the denominators. 2/3 times 5/7 becomes 10 over 21. If common factors appear, they may be simplified before or after multiplication. Algebraic factors can also cancel. 2x over 3y times 9y over 4x contains common factors. The x cancels with x. The y cancels with y. 2 and 4 simplify. 9 and 3 simplify. The final result is 3/2, provided x and y are both tango. The restrictions remain important. Whenever a factor is cancelled, the original denominator tells us which values were forbidden. Dividing fractions uses the reciprocal. To divide by a fraction, multiply by its reciprocal. 3/4 divided by 2/5 becomes 3/4 times 5/2. The result is 15/8. The reciprocal of 2/5 is 5/2. This rule works because dividing by a quantity is equivalent to multiplying by the number that produces 1 with it. 2/5 times 5/2 equals 1. The reciprocal undoes the fraction. The same idea applies in algebra. A over b divided by c over d becomes a over b times d over c. But c cannot be 0, and d must also satisfy the original denominator restrictions. Complex fractions contain fractions within fractions. They often look more confusing than they are. A fraction divided by another fraction can be rewritten using multiplication by the reciprocal. For example, the quantity 1 over x, all divided by 2 over y, becomes 1 over x times y over 2. The result is y over 2x. Slowly identifying the large fraction bar helps. The top is one complete fraction, the bottom is another. Once that structure is seen, the usual division rule applies. The order of operations also governs equations. Consider 2x plus 3 equals 11. Multiplication appears on the left, but solving is not the same as evaluating an expression. We are not simply applying the order of operations to find a numerical result. We are reversing the operations around x while preserving equality. The expression 2x plus 3 says multiply x by 2, then add 3. To isolate x, reverse the sequence, subtract 3 first, then divide by 2. This resembles undoing a machine from the outside inward. The last operation performed on x is the first operation undone. The equation becomes 2x equals 8. Then x equals 4. When solving, the order of inverse operations usually runs opposite to the order used to evaluate. This is because we begin with the completed structure and carefully unpack it. Suppose open parenthesis x plus 5 close parenthesis divided by 3 equals 7. The original expression tells us to add 5 to x, then divide by 3. To solve, undo division first by multiplying both sides by 3. X plus 5 equals 21. Then subtract 5. X equals 16. The outermost operation is undone first. Parentheses help us see the layers surrounding the variable. An equation can be imagined as a wrapped object. The variable sits in the center. Operations form layers around it. To reveal the variable, remove the outer layers one at a time. Always perform the same operation on both sides so the equation remains balanced. Some equations can be solved in different valid orders. The goal is not to follow one rigid path. The goal is to use legal operations that preserve equality and simplify the structure. Consider 3 open parenthesis, x plus 2 close parenthesis, equals 18. One method is to divide both sides by 3 first. Then x plus 2 equals 6. Subtract 2. X equals 4. Another method is to distribute first. 3x plus 6 equals 18. Subtract 6. 3x equals 12. Divide by 3. X equals 4. Both methods are correct. One may be shorter. Algebra often allows more than one path. A good path reduces complexity while avoiding unnecessary work. The distributive property may open parentheses, or dividing by a common factor may remove them more quickly. The choice depends upon the expression. Order of operations does not mean there is only one acceptable sequence of algebraic transformations. It means each written expression has one agreed value. When rewriting equations, every transformation must preserve that value and the set of solutions. This is a subtle but important distinction. Evaluating follows the structure already written. Simplifying may reorganize the structure using valid properties. Solving uses inverse operations to uncover unknown values. Each activity has its own rhythm. A useful habit is to rewrite one clear line at a time. Do not attempt several unrelated operations mentally while copying the same expression. If parentheses are simplified, show the new expression. If exponents are evaluated, show the result. If multiplication is completed, write the next line. This makes errors easier to locate. It also reduces pressure on memory. Algebra is not a test of how many symbols can be held in the mind at once. Paper exists to preserve each step. A clean sequence allows the reasoning to remain visible. Suppose we evaluate the expression 2 plus 3 times open parenthesis, 5 minus 2 close parenthesis squared divided by 9. Begin with the parentheses. 5 minus 2 is 3. The expression becomes 2 plus 3 times 3 squared divided by 9. Next, evaluate the exponent. 3 squared is 9. Now we have 2 plus 3 times 9 divided by 9. Multiplication and division share a level. Move from left to right. 3 times 9 is 27. 27 divided by 9 is 3. Finally, add. 2 plus 3 is 5. The expression appeared complicated, but each stage contained only one familiar movement. Grouping, exponents, multiplication and division, addition. The symbols became quiet when handled in order. If a variable appears, the same process applies after substitution. Consider 2 plus 3 times open parenthesis, x minus 2 close parenthesis squared divided by 9 with x equal to 5. Substitute 5 inside parenthesis. 2 plus 3 times open parenthesis. 5 minus 2 close parenthesis squared divided by 9. The remaining steps are identical. The final result is 5. Substitution turns the algebraic expression into an arithmetic one. Then the order of operations completes the evaluation. Restrictions must also be checked. Suppose an expression contains 1 divided by x minus 3. If x equals 3, the denominator becomes 0. The expression is undefined. The substitution cannot be completed as an ordinary real number. This does not mean x is never allowed to equal 3 in every problem. It means this particular expression excludes that value. Whenever variables appear in denominators, the values that make those denominators 0 must be ruled out. These excluded values form part of the expression's domain. The domain is the set of input values for which an expression or function is defined. For a simple expression such as 2x plus 5, every real number can be used. For 1 over x, 0 is excluded. For 1 over x minus 3, 3 is excluded. Later, square roots and logarithms will create other restrictions. For now, denominator restrictions are the most important. A cancelled factor does not erase an original restriction. Consider x minus 3 over x minus 3. It appears that the numerator and denominator cancel, leaving 1. And for most values of x, that is correct. But when x equals 3, the original denominator is 0. The original expression is undefined. So it equals 1 for every allowed value except 3. After simplification, the restriction must remain remembered. The simplified form describes the same values only on the original domain. This is why algebra is not merely crossing out symbols. Every expression carries structural information, order, grouping, and restrictions. Simplification should preserve all of them. Another source of confusion comes from implied multiplication. The expression 2x squared means 2 multiplied by x squared. The exponent applies only to x. It does not apply to the coefficient 2. If the entire product was squared, parentheses would be required. Open parentheses 2x close parentheses squared becomes 4x squared. But 2x squared remains 2 times x squared. When x equals 3, 2x squared gives 2 times 9, which is 18. Open parenthesis, 2x close parenthesis squared gives 6 squared, which is 36. The difference comes from the base of the exponent. Always identify exactly what the exponent is attached to. A small exponent affects the symbol or grouped expression immediately before it. In a fraction, an exponent may apply to the numerator, denominator, or entire fraction. 3 over 4, all squared, means 3 squared over 4 squared. The result is 9/16. But 3 over 4 squared means 3 over 16. Parentheses around the fraction show that both parts belong to the base. The visual placement communicates the structure. Radicals or root symbols also create grouping. The square root sign covers everything written beneath its bar. The square root of x plus 4 means the entire quantity x plus 4 is inside the root. This differs from the square root of x, then plus 4 outside. The length of the radical bar matters. In typed language, parentheses often make the distinction clearer. Square root of open parenthesis, x plus 4 close parenthesis. The grouping must be understood before any calculation begins. We will explore roots more deeply later. At this stage, the main lesson is simple. Every symbol has a reach. A negative sign may control one number or an entire group. An exponent may apply to one variable or a whole product. A fraction bar may group several terms. A radical may contain one quantity or many. Parentheses make that reach explicit. When an expression looks confusing, ask what each symbol controls. What is the base of this exponent? What belongs in this numerator? Which terms are inside the parentheses? Where does the negative sign apply? What operation is outermost? These questions reveal the hidden architecture. The expression is not a flat row. It has layers. The outermost operation acts on groups created by inner operations. Seeing those layers is more useful than memorizing a phrase. Algebra becomes clear when structure becomes visible. There is no need to hurry through a long calculation. One careful step is enough. Then another. A pair of parentheses becomes one value. An exponent becomes repeated multiplication. A fraction becomes division of two grouped quantities. Equal priority operations move from left to right, and an equation is unwrapped from its outermost layer while remaining balanced. The order of operations is not a collection of traps. It is an agreement that keeps mathematical language steady. Because of that agreement, an expression means the same thing in every classroom, every textbook, and every computer program that follows the same conventions. The symbols may look compact. Their meaning is precise. In the next part, we will move slowly through simplifying expressions, combining like terms, distributing factors, removing parentheses, and understanding why some terms can be combined while others must remain separate. Simplifying an algebraic expression means rewriting it in a cleaner form, without changing its value. The expression may become shorter, its structure may become easier to see, parentheses may disappear, fractions may reduce, several terms may become one. But the simplified expression must always represent the same quantity as the original. Nothing is solved unless an equation is present. Nothing is guessed. The expression is simply reorganized using valid algebraic rules. Consider 3x plus 2x. Both terms contain the same variable raised to the same power. 3 copies of x are combined with 2 more copies of x. The result is 5x. This is similar to ordinary counting. 3 apples plus 2 apples equals 5 apples. 3 books plus 2 books equals 5 books. 3x terms plus 2x terms equals 5x terms. The variable identifies the kind of quantity. The coefficients tell us how many copies are present. Terms that share the same variable structure are called like terms. 3x and 2x are like terms. 5y and negative 7y are like terms. 4x squared and 9x squared are like terms. 2ab and negative 3ab are also like terms. The variable parts match exactly. Only the coefficients differ. Like terms can be combined by adding or subtracting their coefficients. The variable part remains unchanged. 4x plus 7x becomes 11x. Negative 3y plus 8y becomes 5y. 10a squared minus 4a squared becomes 6a squared. 2xy plus 5xy becomes 7xy. The variables do not disappear. They remain because we are still counting that particular kind of term. Unlike terms cannot be combined through addition or subtraction. 3x plus 2y cannot become 5xy. It cannot become 5x. It cannot become 5y. The variables represent different quantities. 3 apples plus 2 books cannot be rewritten as 5 apples or 5 books. There are 5 objects in total, but the kinds remain different. In algebra, the expression stays 3x plus 2y unless more information is given about x and y. The same is true for powers. 3x plus 2x squared cannot be combined. One term contains x to the first power. The other contains x squared. These are different variable structures. If x equals 2, then 3x equals 6, 2x squared equals 8. The total is 14. If we incorrectly combine them as 5x squared, the result would be 20. If we incorrectly combine them as 5x, the result would be 10. Neither matches the original, so the terms must remain separate. Powers matter. Variables matter. Every exponent must match. 4x squared y and 7x squared y are like terms. Their variable parts are identical. The result is 11x squared y. But 4x squared y and 7xy squared are not like terms. The exponents are attached to different variables. The first contains 2 factors of x and 1 factor of y. The second contains 1 factor of x and 2 factors of y. They may look similar. Their structures are different. A reliable way to identify like terms is to ignore the coefficients briefly. Look only at the variables and exponents. If those parts match exactly, the terms are like terms. If any variable or exponent differs, they are unlike. Consider the expression 5x squared minus 3x plus 7 plus 2x squared plus 8x minus 4. At first, the terms appear mixed. We can group terms with matching structures. 5x squared and 2x squared belong together. Negative 3x and positive 8x belong together. Positive 7 and negative 4 are constants, so they belong together. Now combine the coefficients. 5x squared plus 2x squared becomes 7x squared. Negative 3x plus 8x becomes 5x. 7 minus 4 becomes 3. The simplified expression is 7x squared plus 5x plus 3. The order of the terms has changed, the value has not. Terms are often arranged from the highest exponent to the lowest. This is called descending order. The x squared term comes first, then the x term, then the constant. This arrangement is conventional. It makes polynomial expressions easier to read and compare. But rearranging terms is valid only because addition is commutative. A plus b equals b plus a. When a term is negative, its sign must travel with it. In the expression 5x minus 3y plus 2x plus 7y, the terms are 5x, negative 3y, positive 2x, and positive 7y. Group the x terms. 5x plus 2x becomes 7x. Group the y terms. Negative 3y plus 7y becomes 4y. The result is 7x plus 4y. The minus sign was part of the negative 3y term. It did not remain behind when the term moved. Thinking of subtraction as addition of a negative helps preserve signs. 5x minus 3y can be written as 5x plus negative 3y. Now every term has a visible sign. This makes rearrangement safer. Constants are also like terms with one another. They contain no variables. 3 and 7 can combine. Negative 5 and 12 can combine. In 2x plus 3 plus 4x minus 9, the variable terms become 6x. The constants become negative 6. So the expression simplifies to 6x minus 6. A constant cannot normally combine with a variable term. 2x plus 3 does not become 5x. The first term changes when x changes. The second remains fixed. They have different structures. Suppose x equals 1. 2x plus 3 equals 5. The incorrect expression 5x also equals 5. For this one value, they happen to match. But let x equal 2. 2x plus 3 becomes 7. 5x becomes 10. The expressions are not equivalent. Testing more than one value can reveal an invalid simplification. An algebraic identity must work for every allowed value, not merely one accidental example. Combining like terms is really an application of the distributive property. 3x plus 2x can be written as open parenthesis, 3 plus 2 close parenthesis. X, both terms contain the factor x. The coefficients combine inside the parentheses. 3 plus 2 is 5. So the result is 5x. Negative 4y plus 9y becomes open parenthesis. Negative 4 plus 9 close parenthesis y. That becomes 5y. The variable is factored conceptually. The coefficients are added. This explains why unlike terms cannot combine. 3x plus 2y has no single matching variable factor shared by both complete terms. The expression cannot be rewritten as open parenthesis, 3 plus 2 close parenthesis times one common variable. The structures are different. The distributive property can move in two directions. It can expand an expression by removing parentheses, or it can factor an expression by creating parentheses. Expansion changes a product into a sum. Factoring changes a sum into a product. Consider 3 times open parenthesis, x plus 4 close parenthesis. To expand, distribute 3 to every term inside. 3 multiplied by x gives 3x. 3 multiplied by 4 gives 12. The result is 3x plus 12. Now look at the expression in reverse. 3x plus 12 contains a common factor of 3. 3x is 3 times x. 12 is 3 times 4. Factoring out 3 gives 3 times open parenthesis, x plus 4 close parenthesis. Expansion and factoring undo one another. They are opposite movements based upon the same property. The distributive property states that multiplying a number by a sum gives the same result as multiplying each term separately, and then adding a times open parenthesis, b plus c close parenthesis equals ab plus ac. The factor outside reaches every term inside. If the parentheses contain 3 terms, the factor reaches all 3. 2 times open parenthesis, x plus y plus 5 close parenthesis, becomes 2x plus 2y plus 10. No term is skipped. If the outside factor is a variable, the same rule applies. X times open parenthesis, x plus 3 close parenthesis, becomes x squared plus 3x. X multiplied by x gives x squared. X multiplied by 3 gives 3x. If the outside factor contains several parts, each part multiplies every term inside. 3x times open parenthesis, 2x minus 5 close parenthesis, becomes 6x squared minus 15x. 3x times 2x gives 6x squared. 3x times negative 5 gives negative 15x. The coefficient and variable factors are multiplied separately. 3 times 2 is 6, x times x is x squared. Then 3 times -5 is -15. The remaining x stays. Negative factors require careful attention. -2 times open parenthesis, x plus 4 close parenthesis, becomes -2x minus 8. -2 multiplies both terms. -2 times x is -2x. -2 times +4 is -8. Now consider -2 times open parenthesis, x minus 4 close parenthesis. The first product is still -2x. The second product is -2 times -4. That becomes +8. The result is -2x plus 8. The sign inside the parentheses belongs to the term. The outside factor multiplies the complete sign term. A negative sign directly before parentheses means multiplication by -1. Negative open parentheses x plus 5 close parentheses becomes -x minus 5. The sign of every term changes. Negative open parentheses x minus 5 close parentheses becomes -x plus 5. The subtraction inside represents -5. Multiplying -5 by -1 produces +5. This pattern is sometimes described as changing every sign inside the parentheses. That description works because multiplying by -1 reverses each term. But it is useful to remember the underlying multiplication. The signs are not changing by magic. Every term is being multiplied by -1. Consider 7 minus open parentheses 2x plus 3 close parentheses. The subtraction before the parentheses means the entire grouped expression is being subtracted. This is equivalent to adding -1 times the group. Distribute the negative sign. 7 minus 2x minus 3. Now combine the constants. 7 minus 3 is 4. The simplified result is 4 minus 2x. A common mistake is to remove the parentheses without changing both signs. Someone may write 7 minus 2x plus 3, but that subtracts 2x and adds 3. The original expression subtracts the entire quantity 2x plus 3. Both terms must be subtracted. Now consider 7 minus open parentheses 2x minus 3 close parentheses. Distribute the negative sign. 7 minus 2x plus 3. The -3 inside becomes +3 when the whole group is subtracted. Combine the constants. The result is 10 minus 2x. The difference between the two examples is only one sign inside the parentheses. Yet the final constants differ. Careful distribution preserves the meaning. Multiple sets of parentheses can be simplified one at a time. Consider 3 times open parentheses, x plus 2 close parentheses, minus 2 times open parentheses, x minus 5 close parentheses. Distribute 3 through the first group, 3x plus 6. Then distribute -2 through the second group. The expression contains -2 times the parentheses, so the outside factor is -2. -2 times x is -2x. -2 times -5 is +10. The expanded expression is 3x plus 6 minus 2x plus 10. Now combine like terms. 3x minus 2x becomes x. 6 plus 10 becomes 16. The simplified result is x plus 16. The work becomes clearer when the sign before each group is treated as part of the outside factor. A plus sign before parentheses can be understood as +1. A minus sign can be understood as -1. 4 plus open parenthesis, x minus 3 close parenthesis, simply becomes 4 plus x minus 3. The positive sign does not change the terms. Then the constants combine to give x plus 1. 4 minus open parenthesis, x minus 3 close parenthesis, becomes 4 minus x plus 3. Then the constants combine to give 7 minus x. The only difference is the sign outside the group. That sign determines whether the inside terms remain or reverse. Sometimes parentheses are unnecessary. Open parenthesis, x plus 3 close parenthesis, plus open parenthesis, 2x minus 5 close parenthesis, can be written without changing signs because the groups are being added. The expression becomes x plus 3 plus 2x minus 5. Combine like terms. X plus 2x is 3x. 3 minus 5 is -2. The result is 3x minus 2. But when the second group is subtracted, every sign within it reverses. Open parenthesis, x plus 3, close parenthesis, minus open parenthesis, 2x minus 5, close parenthesis becomes x plus 3 minus 2x plus 5. Combine the x terms. x minus 2x is negative x. Combine the constants. 3 plus 5 is 8. The result is negative x plus 8. The subtraction applies to the complete second group. Another common source of confusion is multiplying two grouped expressions. The distributive property still applies. Every term in the first group must multiply every term in the second. Consider open parenthesis x plus 2 close parenthesis times open parenthesis x plus 3 close parenthesis. Begin with x from the first group. Multiply it by both terms in the second group. X times x gives x squared. X times 3 gives 3x. Now take positive 2 from the first group. Multiply it by both terms in the second. 2 times x gives 2x. 2 times 3 gives 6. The expanded expression is x squared plus 3x plus 2x plus 6. Combine like terms. 3x plus 2x becomes 5x. The result is x squared plus 5x plus 6. This method may be described as distributing twice. Each term in one parenthesis reaches every term in the other. For two binomials, 4 products appear before like terms are combined. A binomial is an expression containing two terms. Open parenthesis x plus 2 close parenthesis is a binomial. Open parenthesis x minus 7 close parenthesis is another. Multiplying binomials creates a pattern. The first terms multiply. The outer pair multiplies. The inner pair multiplies. The last terms multiply. Some learners use a word formed from these positions to remember the process. But the distributive property is more general. It works with 2 terms, 3 terms, or any number of terms. Every term multiplies every term. Consider open parenthesis x minus 4 close parenthesis times open parenthesis x plus 5 close parenthesis. Multiply x by both terms, x squared plus 5x. Then multiply negative 4 by both terms, negative 4x minus 20. Combine the middle terms. 5x minus 4x becomes x. The result is x squared plus x minus 20. The negative sign belongs to 4. It affects both products created by that term. Now consider open parenthesis x minus 3 close parenthesis squared. The exponent means the entire binomial multiplies by itself. Open parenthesis x minus 3 close parenthesis times open parenthesis x minus 3 close parenthesis. Multiply each term. X times x gives x squared. X times negative 3 gives negative 3x. Negative 3 times x gives another negative 3x. Negative 3 times negative 3 gives positive 9. Combine the middle terms. Negative 3x minus 3x becomes negative 6x. The expanded result is x squared minus 6x plus 9. It is not x squared plus 9. The two middle products are essential. They appear because both terms in one copy interact with both terms in the other. Similarly, open parenthesis x plus 3 close parenthesis squared becomes x squared plus 6x plus 9. The only difference is the sign of the middle term. O squared binomial follows a useful pattern. The square of the first term, twice the product of the two terms, then the square of the second term. For x plus 3, the square of x is x squared, twice x times 3 is 6x. The square of 3 is 9. For x minus 3, the middle product is negative. The square of negative 3 remains positive. So the result is x squared minus 6x plus 9. These patterns become useful later, but understanding the multiplication is safer than memorizing a form without meaning. The difference of squares creates another pattern. Open parenthesis x plus 4 close parenthesis times open parenthesis x minus 4 close parenthesis. Multiply x by both terms. X squared minus 4x. Multiply positive 4 by both terms. Positive 4x minus 16. The middle terms cancel. Negative 4x plus positive 4x equals 0. The result is x squared minus 16. A sum and difference containing the same terms produce a difference of squares. Open parenthesis a plus b close parenthesis times open parenthesis a minus b close parenthesis becomes a squared minus b squared. The middle terms are opposites. They disappear. This pattern can also be reversed during factoring. X squared minus 16 can become open parenthesis x plus 4 close parenthesis times open parenthesis x minus 4 close parenthesis. Simplification sometimes requires distributing before combining like terms. Consider 2 times open parenthesis 3x plus 4, close parenthesis, plus 5x. The 2x terms cannot be combined immediately because 3x is still inside a product. First distribute 2, 6x plus 8 plus 5x. Now combine 6x and 5x. The result is 11x plus 8. Trying to combine 2 and 5 because they appear outside variable terms would be incorrect. 2 is a factor of the entire parenthesis. It must perform its multiplication first. Now consider 3x plus 2 times open parenthesis, x plus 5 close parenthesis. Distribute 2, 3x plus 2x plus 10. Combine like terms. The result is 5x plus 10. The sequence is often parentheses first, then like terms. But there may be different valid approaches when common factors appear. For example, 2x plus 4x can immediately combine to 6x. It could also be written as 2x plus 2 times 2x. Factoring and combining may lead to the same result. The simplest route depends on the expression. Fractions can also have like terms. 1/2 x plus 1/3 x contains the same variable part. The coefficients are 1/2 and 1/3. Add the fractional coefficients. A common denominator is 6. 1/2 becomes 3/6. 1/3 becomes 2/6. The total coefficient is 5/6. The simplified expression is 5/6 x. The variable does not interfere with the fraction addition. It is the common factor shared by both terms. Negative 3/4 y plus 1/2 y can be combined similarly. 1/2 becomes 2/4. Negative 3/4 plus 2/4 is negative 1/4. The result is negative 1/4 y. Decimals can also serve as coefficients. 0.5x plus 1.2x becomes 1.7x. The same like term rule applies. Coefficients may be integers, fractions, decimals, irrational numbers, or algebraic expressions. If the variable structure matches, the coefficients can be combined. Consider ax plus bx. The coefficients are a and b. The common variable factor is x. The expression can be written as open parenthesis, a plus b close parenthesis x. We cannot combine a and b numerically because their values are unknown. But factoring x reveals the common structure. This is still a form of simplification. The best form depends upon the purpose. ax plus bx may be useful when individual contributions matter. Open parenthesis a plus b close parenthesis x may be useful when the common factor matters. Equivalent expressions can look very different. 2 times open parenthesis x plus 3 close parenthesis and 2x plus 6 are equivalent. X squared minus 9 and open parenthesis x minus 3 close parenthesis times open parenthesis x plus 3 close parenthesis are equivalent. The first form is expanded. The second is factored. Neither is always more correct. One form may make evaluation easier. Another may make solving easier. Another may reveal zeros, patterns, or common factors. Simplifying does not always mean making an expression shorter. Sometimes a longer expanded expression is considered simpler for one task. Sometimes a shorter factored expression is more useful. The goal is clarity and usefulness while preserving value. Suppose we need to evaluate 3 times open parenthesis x plus 4 close parenthesis when x equals 6. The factored form is convenient. X plus 4 is 10. 3 times 10 is 30. The expanded form 3x plus 12 also works. 3 times 6 is 18. 18 plus 12 is 30. Both give the same result. Suppose instead we need to solve 3x plus 12 equals 0. The factored form 3 times open parenthesis x plus 4 close parenthesis equals 0 may reveal the solution quickly. Since 3 is not 0, x plus 4 must equal 0. So x equals negative 4. Factoring can reveal structure that expansion hides. A simplified expression should also avoid unnecessary parenthesis. 3x plus open parenthesis 2x minus 5 close parenthesis can become 3x plus 2x minus 5. The parentheses are not needed because the group is simply being added. Then the x terms combine. The result is 5x minus 5. But parentheses that preserve a denominator, exponent base, or multiplied group should not be removed carelessly. Open parenthesis x plus 2 close parenthesis squared cannot lose its parentheses. The exponent applies to the entire sum. 1 over open parenthesis x plus 2 close parenthesis also needs grouping. The entire sum is the denominator. Removing the grouping changes the expression's meaning. Simplification should remove only parentheses that no longer serve a structural purpose. The same is true for multiplication symbols. 3 times x is usually written 3x. 1 times x becomes x. -1 times x becomes -x. 0 times any expression becomes 0. These small conventions reduce clutter, but they rely upon known identities. Multiplying by 1 preserves a value. Multiplying by 0 produces 0. Adding 0 changes nothing. Subtracting 0 changes nothing. These identity properties are constantly used during simplification. X plus 0 becomes x. 1x becomes x. X divided by 1 becomes x. X minus x becomes 0. X divided by x becomes 1, only when x is not 0. That restriction matters. The expression x divided by x is undefined at 0, so simplification to 1 is valid only for Tungo x. The original domain must be preserved. 0 has several special behaviors. 0 added to a term changes nothing. 0 multiplied by a term makes the product 0. A 0 coefficient removes a term. 3x minus 3x becomes 0x. 0x equals 0. The variable disappears because no copies remain. But 0 divided by x is 0 only when x is not 0, and x divided by 0 is undefined. The position of 0 matters. Expressions can be checked through substitution. Suppose we simplify 2 times open parenthesis x plus 3 close parenthesis minus x to x plus 6. To verify, choose a value such as x equals 4. The original expression gives 2 times 7 minus 4. That is 14 minus 4. The result is 10. The simplified expression gives 4 plus 6. That is also 10. Try another value, perhaps x equals -2. The original gives 2 times 1 minus -2. That becomes 2 plus 2. The result is 4. The simplified expression gives -2 plus 6. That also equals 4. Matching examples do not prove equivalence completely, but they can reveal many errors. A formal justification comes from valid algebraic properties. Distribute 2x plus 6 minus x. Combine 2x minus x. The result is x plus 6. Each step preserves value for every x. This is stronger than checking a few cases. Still, substitution is a useful final reassurance. An invalid simplification often fails quickly when tested. Consider the incorrect claim that open parenthesis x plus 3 close parenthesis squared equals x squared plus 9. Let x equal 1. The original gives 4 squared, which is 16. The claimed form gives 1 plus 9, which is 10. The mismatch reveals the missing middle term. Or consider the incorrect claim that x plus 2 over x equals 2. Let x equal 2. The original fraction is 4 over 2, which equals 2. The incorrect simplification appears to work. But let x equal 4. The original becomes 6 over 4, which is 1 1/2. It does not equal 2. A single convenient value can be misleading. Testing several values, including negative values when allowed, provides a stronger check. Common algebra mistakes often come from treating addition like multiplication. Multiplication allows factors to combine and cancel. Addition requires like terms. X times x becomes x squared. But x plus x becomes 2x. X squared times x cubed becomes x to the 5th. But x squared plus x cubed cannot combine. 2 times open parenthesis, x plus 3 close parenthesis, distributes. But 2 raised to the power, x plus 3, does not follow the same rule. Every operation has its own properties. A rule valid for multiplication may fail for addition. A rule valid for powers may fail for sums. This is why structure matters more than visual similarity. Take the expression 3x times 4x. This is multiplication. Multiply the coefficients. 3 times 4 is 12. Multiply the variable factors. X times x is x squared. The result is 12x squared. Now compare 3x plus 4x. This is addition. The terms are like terms. Add the coefficients. 3 plus 4 is 7. Keep x. The result is 7x. The same visible pieces produce different results, because the operation between them differs. 3x times 4y becomes 12xy. But 3x plus 4y remains unchanged because the terms are unlike. Multiplication can join different variables into one product. Addition cannot combine unlike terms into one term. Division follows factor rules. 12x squared divided by 3x becomes 4x, provided x is not 0. 12 divided by 3 is 4. X squared divided by x leaves x. But 12x squared plus 3x cannot be reduced by dividing both terms casually, unless the whole expression is inside a fraction or a common factor is deliberately extracted. We could factor 3x from the sum. 12x squared plus 3x becomes 3x times open parenthesis, 4x plus 1 close parenthesis. This does not divide the expression. It rewrites the common factor explicitly. Factoring begins by identifying what every term shares. Consider 6x squared plus 9x. Both terms contain a numerical factor of 3. They also both contain x. The greatest common factor is 3x. Divide each term by 3x to discover what remains inside. 6x squared divided by 3x is 2x. 9x divided by 3x is 3. So the factored form is 3x times open parenthesis, 2x plus 3 close parenthesis. Distribute to check. 3x times 2x gives 6x squared. 3x times 3 gives 9x. The original expression returns. Factoring out the greatest common factor is often the first step in more advanced factoring. It simplifies the remaining terms. Consider negative 8x squared plus 12x. Both terms share 4x. We could factor positive 4x. The result would be 4x times open parenthesis, negative 2x plus 3 close parenthesis. We could also factor negative 4x. Then the expression becomes negative 4x times open parenthesis, 2x minus 3 close parenthesis. Both forms are correct. The second may be preferred because the first term inside the parentheses is positive. Factoring a negative reverses all signs inside. The choice is partly conventional. The value remains the same. Expressions containing many variables follow the same method. 12a squared b plus 18ab squared. The numerical greatest common factor is 6. Both terms contain a. Both contain b. The greatest common variable factor is ab. So factor 6ab. The first term divided by 6ab leaves 2a. The second leaves 3b. The result is 6ab times open parenthesis, 2a plus 3b, close parenthesis. No variable exponent greater than the smallest shared exponent can be factored. The first term contains a squared. The second contains only a to the first power. So only one factor of a is common. The first contains 1b. The second contains b squared. So only 1b is common. Factoring removes what every term truly shares. Like term combination and factoring are closely connected but different. 3x plus 2x combines to 5x because the variable parts are identical. 3x plus 3y cannot combine, but it can be factored as 3 times open parenthesis, x plus y close parenthesis, because both terms share a factor of 3. The result still contains two unlike terms inside the parentheses. They have not been added. Their common multiplier has been made visible. Similarly, x squared plus x cannot combine as like terms, but both terms share x. The factored form is x times open parenthesis, x plus 1 close parenthesis. Factoring does not claim that x squared and x are the same kind of term. It identifies a shared factor. This distinction becomes valuable in equations. The equation x squared plus x equals 0 may look difficult. Factor x. X times open parenthesis, x plus 1 close parenthesis equals 0. A product equals 0 only when at least one factor equals 0. So x equals 0, or x plus 1 equals 0. The second gives x equals negative 1. Factoring reveals both solutions. We will explore this method more fully when studying quadratics. For now, notice how a change of form can reveal information hidden in the expanded expression. Simplifying algebra is less about making symbols disappear and more about showing their relationships clearly. Like terms reveal repeated quantities. Distribution reveals how a factor reaches several terms. Factoring reveals what several terms share. Parentheses reveal grouping. Exponents reveal repeated multiplication. Fractions reveal division and restrictions. Every transformation changes the appearance while preserving the underlying value. A calm approach is to ask the same sequence of questions. Are there parentheses that should be distributed? Are there signs that must change? Which terms are like terms? What common factors are present? Are there fractions that can reduce? Are any values excluded? Can the result be arranged more clearly? There may not always be something to do at every stage. An expression such as 3x plus 2y is already simplified for many purposes. The inability to combine it does not mean the work is incomplete. Sometimes the correct simplified form still contains several terms. Not every expression becomes one number or one variable term. Algebra preserves distinctions when they matter. With practice, the eye begins to notice matching structures. X terms gather quietly. X squared terms form another group. Constants remain together. Outside factors move through parentheses. Negative signs reverse complete groups. Common factors emerge from sums. The expression becomes less like a crowded line of symbols and more like an organized collection. There is no need to perform every step mentally. Write the terms clearly. Carry each sign. Use one line for distribution, another for combining. Check by substituting a simple value. The purpose of simplification is clarity. The process should also remain clear. In the next part, we will begin solving equations more deeply, moving from one-step equations to variables on both sides, fractions, parentheses, special cases, and the reason some equations have one solution, no solution, or infinitely many solutions. Solving an equation means finding every value that makes the equation true. The word solving can make the process sound like a puzzle with a hidden trick. But most equations are not solved through guessing. They are solved by preserving balance. An equation says that the expression on the left has the same value as the expression on the right. The two sides may look different. Their values are equal. The goal is to rewrite the equation until the variable stands alone. Every legal step must preserve the equality. Imagine a balanced scale. If 2 kilograms are added to the left side, 2 kilograms must also be added to the right. If both sides are divided into 3 equal groups, the division must affect both sides. An operation performed equally on both sides creates a new equation with the same solutions. This principle is more important than any individual shortcut. The shortcuts work because they preserve balance. Begin with a one-step equation. X plus 5 equals 12. The variable has 5 added to it. To isolate x, undo the addition. Subtract 5 from both sides. X plus 5 minus 5 equals 12 minus 5. The positive 5 and negative 5 make 0. X remains. 12 minus 5 is 7. So x equals 7. The solution can be checked in the original equation. 7 plus 5 equals 12. The statement is true. Now consider x minus 4 equals 9. The variable has 4 subtracted. Undo that subtraction by adding 4 to both sides. X minus 4 plus 4 equals 9 plus 4. X equals 13. Substitution confirms the result. 13 minus 4 is 9. For 3x equals 18, the variable is multiplied by 3. Divide both sides by 3. 3x divided by 3 equals 18 divided by 3. The factor of 3 cancels on the left. X equals 6. For x divided by 5 equals 4. Undo the division by multiplying both sides by 5. X divided by 5, multiplied by 5, equals 4 times 5. X equals 20. These equations require one inverse operation. Addition is undone by subtraction. Subtraction is undone by addition. Multiplication is undone by division. Division is undone by multiplication. Two-step equations contain 2 layers around the variable. Consider 2x plus 3 equals 11. The expression says multiply x by 2, then add 3. To solve, undo the operations in reverse order. The addition of 3 occurred last, so subtract 3 first. 2x plus 3 minus 3 equals 11 minus 3. 2x equals 8. Now undo multiplication by 2. Divide both sides by 2. X equals 4. The solution can be checked. 2 times 4 plus 3 is 8 plus 3. The result is 11. The equation balances. Now consider 5x minus 7 equals 18. Add 7 to both sides. 5x equals 25. Then divide both sides by 5. X equals 5. Check the original. 5 times 5 minus 7 is 25 minus 7. The result is 18. The solution works. The order used while solving reverses the order used while evaluating. To evaluate 5x minus 7, multiply first and subtract afterward. To solve, undo the subtraction first, then undo the multiplication. The variable is wrapped inside a sequence of operations. Solving removes the outermost layer first. This can be imagined as unpacking a carefully wrapped object. The variable sits at the center. Multiplication forms one layer. Addition or subtraction forms another. The outer layer is removed, then the next. Consider the equation x divided by 3 plus 4 equals 10. The expression means divide x by 3, then add 4. Subtract 4 from both sides. X divided by 3 equals 6. Then multiply both sides by 3. X equals 18. Substitute 18. 18 divided by 3 is 6. 6 plus 4 is 10. The equation is true. Now consider the quantity x plus 4, all divided by 3, equals 10. This equation looks similar. Its structure is different. The entire quantity x plus 4 is divided by 3. To solve, undo the outer division first. Multiply both sides by 3. X plus 4 equals 30. Then subtract 4. X equals 26. The first equation gave 18. The second gives 26. Parentheses and fraction grouping change the order of operations surrounding the variable. Reading the expression aloud helps reveal the difference. X divided by 3, then plus 4, or the quantity x plus 4, all divided by 3. The words expose the layers. Equations with parentheses can often be solved in more than one way. Consider 3 times open parenthesis x plus 2 close parenthesis equals 21. One approach is to divide by 3 first. X plus 2 equals 7. Then subtract 2. X equals 5. Another approach is to distribute first. 3x plus 6 equals 21. Subtract 6. 3x equals 15. Divide by 3. X equals 5. Both methods are valid. Dividing first is shorter because the entire left side is multiplied by 3. But distribution may be necessary when other terms appear outside the parentheses. Consider 3 times open parenthesis x plus 2 close parenthesis plus 4 equals 25. The outermost operation affecting the product is the addition of 4. Subtract 4. 3 times open parenthesis x plus 2 close parenthesis equals 21. Now divide by 3. X plus 2 equals 7. Then subtract 2. X equals 5. Distribution would also work. 3x plus 6 plus 4 equals 25. Combine the constants. 3x plus 10 equals 25. Subtract 10. 3x equals 15. Divide by 3. X equals 5. The best method is usually the one that reduces complexity. There is no reward for creating more terms than necessary. But when a factor cannot be divided cleanly from the entire equation, distribution may be the clearer path. Consider 3 times open parenthesis x plus 2 close parenthesis plus 5x equals 26. The left side contains the product and another variable term. Distribute 3. 3x plus 6 plus 5x equals 26. Combine like terms. 8x plus 6 equals 26. Subtract 6. 8x equals 20. Divide by 8. X equals 20 over 8. Simplify the fraction. X equals 5 halves, or 2 and 1 half. Check the original. X plus 2 becomes 4 and 1 half. 3 times 4 and 1 half is 13 and 1 half. 5x is 12 and 1 half. Together, they equal 26. The fractional solution is valid. An answer does not need to be a whole number. Algebraic variables can represent fractions, decimals, negative numbers, irrational numbers, or any other allowed value. A result such as 5 halves is not evidence that something went wrong. It is simply the value that balances the equation. Equations may also contain variables on both sides. Consider 5x plus 2 equals 3x plus 10. The variable cannot be isolated by working on only one side. We need to gather variable terms on one side and constants on the other. Subtract 3x from both sides. 5x minus 3x plus 2 equals 3x minus 3x plus 10. 2x plus 2 equals 10. Now subtract 2. 2x equals 8. Divide by 2. X equals 4. Check both sides. The left side is 5 times 4 plus 2. That is 22. The right side is 3 times 4 plus 10. That is also 22. The equation balances. We could instead subtract 5x from both sides. Then 2 equals negative 2x plus 10. Subtract 10. Negative 8 equals negative 2x. Divide by negative 2. X equals 4. Both paths are valid. One path keeps the variable coefficient positive. That may feel simpler, but a negative coefficient is not wrong. The goal is to perform balanced operations that lead toward isolation. Consider 7x minus 4 equals 10x plus 8. Subtract 7x from both sides. Negative 4 equals 3x plus 8. Subtract 8. Negative 12 equals 3x. Divide by 3. X equals negative 4. Check the original. 7 times negative 4 minus 4 is negative 28 minus 4. The result is negative 32. 10 times negative 4 plus 8 is negative 40 plus 8. The result is also negative 32. A negative solution balances the equation perfectly. Equations with parentheses on both sides may require several stages. Consider 2 times open parenthesis, x plus 3 close parenthesis equals 4 times open parenthesis, x minus 1 close parenthesis. Distribute both sides. 2x plus 6 equals 4x minus 4. Subtract 2x from both sides. 6 equals 2x minus 4. Add 4. 10 equals 2x. Divide by 2. X equals 5. Check using the original grouped equation. The left side is 2 times 8. That is 16. The right side is 4 times 4. That is also 16. The solution works. Now consider 3 times open parenthesis, 2x minus 1, close parenthesis, plus 5 equals 2 times open parenthesis, x plus 4 close parenthesis. Distribute. 6x minus 3 plus 5 equals 2x plus 8. Combine the constants on the left. 6x plus 2 equals 2x plus 8. Subtract 2x. 4x plus 2 equals 8. Subtract 2. 4x equals 6. Divide by 4. X equals 3 halves. The equation contains several operations, but each step uses familiar movements. Distribute. Combine like terms. Gather variables. Gather constants. Divide by the remaining coefficient. This sequence is a useful general guide, but it should not become a rigid ritual. Some equations simplify faster through a different first step. Look at the structure before acting. Fractions often make equations appear more complicated than they are. Consider x divided by 4 plus 3 equals 8. Subtract 3. X divided by 4 equals 5. Multiply by 4. X equals 20. Now consider x over 3 plus x over 6 equals 5. The denominators differ. We could combine the fractions first. A common denominator is 6. X over 3 becomes 2x over 6. 2x over 6 plus x over 6 equals 3x over 6. This simplifies to x over 2. So x over 2 equals 5. Multiply by 2. X equals 10. Another method is to clear the fractions immediately. Multiply every term by the least common denominator, 6. 6 times x over 3 gives 2x. 6 times x over 6 gives x. 6 times 5 gives 30. The equation becomes 2x plus x equals 30. 3x equals 30. X equals 10. Clearing denominators often makes fraction equations easier. But every term on both sides must be multiplied. No term can be skipped. Consider x over 2 plus 3 over 4 equals 5. The least common denominator is 4. Multiply the entire equation by 4. 4 times x over 2 gives 2x. 4 times 3 over 4 gives 3. 4 times 5 gives 20. The new equation is 2x plus 3 equals 20. Subtract 3. 2x equals 17. Divide by 2. X equals 17 halves. The fraction did not disappear from the final answer. Clearing denominators removes fractions from the equation's structure. It does not guarantee an integer solution. Now consider x plus 1 over 3 equals x minus 2 over 5. Here, the complete expressions x plus 1 and x minus 2 form the numerators. The equation is the quantity x plus 1 divided by 3 equals the quantity x minus 2 divided by 5. Multiply both sides by 15, the least common denominator. 15 times the left fraction gives 5 times open parenthesis. Facond times the right gives 3 times open parenthesis. x minus 2 close parenthesis. The equation becomes 5 times open parenthesis, x plus 1 close parenthesis equals 3 times open parenthesis, x minus 2 close parenthesis. Distribute. 5x plus 5 equals 3x minus 6. Subtract 3x. 2x plus 5 equals negative 6. Subtract 5. 2x equals negative 11. Divide by 2. X equals negative 11 halves. The fraction bars group the numerators. After clearing denominators, the parentheses preserve those groups. Without them, distribution could be performed incorrectly. Some equations include decimal coefficients. Consider 0.5, x plus 2 equals 7. Subtract 2. 0.5x equals 5. Divide by 0.5. X equals 10. Dividing by 0.5 is the same as multiplying by 2. We could also remove the decimal at the beginning by multiplying the entire equation by 10. 5x plus 20 equals 70. Subtract 20. 5x equals 50. X equals 10. Both methods work. Multiplying by a power of 10 can turn terminating decimals into integers. This often makes the arithmetic easier. Every term must again be multiplied. Suppose 0.2x plus 0.3 equals 1.1. Multiply the equation by 10. 2x plus 3 equals 11. Subtract 3. 2x equals 8. X equals 4. The decimal equation has become an ordinary integer equation. Percentages can be handled similarly, because a percentage is a fraction with denominator 100. 20% of x equals 30 can be written as 0.2x equals 30. Divide by 0.2. X equals 150. Or write 20 over 100 times x equals 30. Simplify 20 over 100 to 1/5. X divided by 5 equals 30. Multiply by 5. X equals 150. Different representations may reveal different paths. Equations do not always have exactly one solution. Some have no solution. Some have infinitely many solutions. This becomes clear when the variable terms cancel. Consider 2x plus 3 equals 2x plus 7. Subtract 2x from both sides. The variable disappears. 3 equals 7. This statement is false. No value of x can make the original equation true. Whatever x is, the left side is always 4 less than the right side. The equation has no solution. A false statement after simplification signals inconsistency. Now consider 2x plus 3 equals 2x plus 3. Subtract 2x. 3 equals 3. This is always true. Every value of x makes the original equation true. The equation has infinitely many solutions. It is an identity. Both sides are simply different copies of the same expression. A true numerical statement, after the variable cancels, indicates that all allowed values are solutions. Consider 3 times open parenthesis, x plus 2 close parenthesis equals 3x plus 6. Distribute the left side. 3x plus 6 equals 3x plus 6. Subtract 3x and 6. 0 equals 0. This is true for every real value of x. The equation expresses the distributive property. It does not restrict x to one number. Now consider 3 times open parenthesis, x plus 2 close parenthesis equals 3x plus 7. Distribute. 3x plus 6 equals 3x plus 7. Subtract 3x. 6 equals 7. False. No solution exists. The two sides have identical variable behavior, but different constants. They can never meet. These special cases are not errors, they are valid outcomes. One solution means the equation's balance occurs at one value. No solution means the sides never become equal. Infinitely many solutions means the sides are equal for every allowed value. The final simplified statement tells us which situation has occurred. Equations containing absolute value behave differently because absolute value represents distance. Consider the absolute value of x equals 4. The question asks, which numbers lie 4 units from 0? There are 2, positive 4 and negative 4. So x equals 4 or x equals negative 4. Now consider the absolute value of x minus 3 equals 5. This asks which values of x are 5 units away from 3. One lies 5 units to the right. 3 plus 5 is 8. The other lies 5 units to the left. 3 minus 5 is negative 2. So x equals 8, or x equals -2. Algebraically, we create two equations. X minus 3 equals 5, or x minus 3 equals -5. The first gives x equals 8. The second gives x equals -2. Both should be checked in the original absolute value equation. The distance from 8 to 3 is 5. The distance from -2 to 3 is also 5. If the absolute value equals 0, only one solution appears. The absolute value of x plus 4 equals 0. A distance is 0 only when the inside expression equals 0. X plus 4 equals 0. X equals -4. If an absolute value equals a negative number, there is no real solution. The absolute value of x equals -3 has no solution. Distance cannot be negative. Equations involving squares may also have two solutions. Consider x squared equals 9. Both 3 squared and -3 squared equal 9. So x equals 3 or x equals -3. Taking a square root requires remembering both signs. X equals plus or minus 3. The plus or minus symbol represents two possibilities. Now consider open parenthesis, x minus 2 close parenthesis squared equals 16. The quantity x minus 2 can equal positive 4 or negative 4. First case, x minus 2 equals 4, x equals 6. Second case, x minus 2 equals -4, x equals -2. Both values work. 6 minus 2 is 4, and 4 squared is 16. -2 minus 2 is -4, and -4 squared is also 16. Squaring removes sign information. When solving backward, both possible signs must be restored. But not every equation with a square can be solved by taking a square root immediately. Consider x squared plus 5x equals 6. The left side is not one complete squared quantity. Taking a square root of each term separately would be invalid. The equation must be rearranged and solved using factoring, completing the square, or the quadratic formula. Those methods will appear later. For now, notice the structure. Square root methods work directly when a single squared expression is isolated. Restrictions can create false-looking or extraneous solutions. An extraneous solution is a value produced during algebraic work that does not satisfy the original equation. This often happens when both sides are squared or when equations contain variable denominators. Consider the equation square root of x equals -3. The principal square root of a real number is never negative, so the original equation has no real solution. But suppose someone squares both sides, x equals 9. That value appears to solve the squared equation. Yet checking in the original gives square root of 9 equals -3. 3 equals -3. False. X equals 9 is extraneous. Squaring both sides can introduce new possibilities because positive and negative numbers have the same square. The transformed equation may have more solutions than the original. Checking is essential. Variable denominators also require care. Consider 1 over x equals 2. Multiply both sides by x. 1 equals 2x. Divide by 2. X equals 1/2. The solution is allowed because x is not 0. Check. 1 divided by 1/2 equals 2. The equation is true. Now consider x over x equals 1. The expression appears to simplify to 1 equals 1. That suggests every x works. But x cannot equal 0 because the original denominator would be 0. So the solution set is every real number except 0. The restriction survives simplification. Consider the equation 1 over x minus 2 equals 1 over x minus 2, where the complete denominator is x minus 2. Both sides are identical. Every allowed x is a solution, but x equals 2 is not allowed. The equation has infinitely many solutions within its domain, excluding 2. The phrase infinitely many does not always mean every real number. It means every value permitted by the original expression. Now consider 1 over x equals 1 over x plus 1. The denominator on the right is the quantity x plus 1. The restrictions are x not equal to 0 and x not equal to -1. Multiply both sides by x times open parenthesis, x plus 1 close parenthesis. The left becomes x plus 1. The right becomes x. So x plus 1 equals x. Subtract x. 1 equals 0. False. There is no solution. The two reciprocal expressions never become equal within the allowed domain. Equations may include literal parameters. A parameter is a letter treated as a fixed value within one problem, even though its numerical value is not specified. Consider a x equals b. To solve for x, divide by a. X equals b over a. But this assumes a is not 0. If a equals 0, the situation changes. 0 times x equals b. If b is tungoo, no solution exists. If b is also 0, every x is a solution. The simple formula x equals b over a carries a condition. A cannot equal 0. Algebraic formulas often include such assumptions. They may not always be written beside every step. Understanding the restrictions keeps the formula honest. Solving a formula for one variable uses the same balance principles. Consider the distance formula d equals rt. Suppose we want to solve for t. Divide both sides by r. d over r equals t, so t equals d over r, assuming r is not 0. Now consider the area formula for a triangle. A equals 1/2 bh. To solve for h, multiply both sides by 2. 2a equals bh, then divide by b. h equals 2a over b, assuming b is not 0. The letters may all be variables. The process remains the same. Treat the desired variable as the unknown to isolate. Treat the others as known quantities or parameters. Formulas can look more complicated because no numerical constants reveal easy arithmetic, but the operations are identical. Consider y equals mx plus b. Solve for x. Subtract b from both sides. Y minus b equals mx. Divide by m. X equals open parenthesis. Y minus b close parenthesis over m, assuming m is not 0. The grouped numerator matters. The entire difference y minus b is divided by m. A formula can also be rearranged in several equivalent forms. Each form highlights a different variable. This is one of algebra's greatest practical strengths. One relationship can be adapted to answer many different questions. Word problems become easier when the equation is built before the arithmetic begins. Suppose a taxi charges a fixed fee of 4 units plus 2 units for every kilometer. The total cost is 18 units. How many kilometers were traveled? Let x represent the number of kilometers. The variable cost is 2x. The fixed fee is 4. The total is 18. So 2x plus 4 equals 18. Subtract 4. 2x equals 14. Divide by 2. X equals 7. The algebra represents the structure of the situation. The number 7 is not guessed. It emerges from the balance. The most difficult part of many word problems is not solving the equation. It is translating the language into mathematical relationships. Words such as total, difference, product, per, and of often signal operations. But context matters more than vocabulary alone. 5 more than x means x plus 5. 5 less than x means x minus 5. The order of words can be deceptive. 5 less than x is not 5 minus x. It means begin with x and remove 5. The result is x minus 5. Twice a number means 2x. The quotient of a number and 4 means x divided by 4. 3 consecutive integers can be represented as x, x plus 1, and x plus 2. 3 consecutive even integers can be x, x plus 2, and x plus 4, provided x is even. The variable chooses a starting point. The algebra preserves the relationship among the values. Suppose 3 consecutive integers have a sum of 36. Let the first be x. The next is x plus 1. The third is x plus 2. Their sum is 36. X plus open parenthesis, x plus 1, close parenthesis, plus open parenthesis, x plus 2, close parenthesis, equals 36. Remove unnecessary parentheses. 3x plus 3 equals 36. Subtract 3. 3x equals 33. X equals 11. The integers are 11, 12, and 13. Their sum is 36. Checking the original context confirms the result. They are consecutive, and their total is correct. Equations involving rates often use multiplication. Distance equals rate times time. If a vehicle travels at 60 kilometers per hour for t hours, the distance is 60t. If the total distance is 240 kilometers, the equation is 60t equals 240. Divide by 60. T equals 4 hours. Units can guide the equation. Kilometers per hour multiplied by hours produces kilometers. The hour units conceptually cancel. Dimensional reasoning can reveal whether a formula has been arranged sensibly. If a calculation for time produces square kilometers, something has likely been translated incorrectly. Mixture and percentage equations follow the same balance logic. Suppose a store reduces a price by 20%. The new price is 80% of the original. If the new price is 40 units, Let x be the original price. 0.8x equals 40. Divide by 0.8, x equals 50. Check. 20% of 50 is 10. 50 minus 10 is 40. The equation reflects what remains after the reduction. A 20% discount does not mean subtract 20 from every price. It means subtract 20% of the original amount. The variable makes that distinction precise. Age problems often compare quantities at different times. Suppose one person is 5 years older than another. Let the younger age be x. The older age is x plus 5. If their ages total 35, the equation is x plus open parenthesis, x plus 5 close parenthesis equals 35. 2x plus 5 equals 35. Subtract 5. 2x equals 30. X equals 15. The younger person is 15. The older is 20. The difference is 5. The total is 35. The check confirms both conditions. The variable does not need to represent the quantity explicitly requested, but choosing a simple representation usually shortens the equation. When a problem feels confusing, define the variable clearly in words. Let x be the younger person's current age. Let t be the number of hours. Let p be the original price. A clear definition prevents the symbol from becoming detached from the situation. After solving, return to the definition. If x represents hours, the final answer should include hours. If x represents the smaller integer, use it to find the others. The algebraic solution is not complete until it is interpreted. Sometimes an equation gives a mathematically valid value that does not fit the real situation. Suppose the equation for the number of people produces -3. The algebra may have been solved correctly, but a negative number of people is not meaningful in the original context. The model, assumptions, or translation may need reconsideration. Context can restrict the solution set further than algebra alone. A length may need to be positive. A probability must lie between 0 and 1. A time duration may need to be non-negative. An answer should satisfy both the equation and the situation. Checking an equation is more than confirming arithmetic. It can also check interpretation. Substitute the value into the original equation. Then ask whether the value makes sense. Does the number have the correct units? Does it satisfy stated restrictions? Does it answer the actual question? These final checks prevent a correct calculation from becoming an incorrect conclusion. The most reliable general method for linear equations can be summarized quietly. Simplify each side if needed. Distribute through parentheses. Combine like terms. Clear fractions or decimals when helpful. Move variable terms to one side. Move constants to the other. Divide by the remaining coefficient, then check the result in the original equation. But the method is not a chant that replaces thought. Each equation has a structure. Some steps may be unnecessary. Some may occur in a different order. The balance principle remains constant underneath them all. When solving feels confusing, write the same operation on both sides. Do not move a term across the equal sign as though it changes sign by magic. That common shortcut is really a compressed description of adding or subtracting the term on both sides. In 5x plus 3 equals 18, saying the 3 moves across and becomes -3 can produce the correct result, but the deeper step is subtracting 3 from both sides. The sign changes because +3 and -3 cancel on the left, while -3 appears on the right. Understanding the full operation prevents errors when equations become more complex. Terms do not leap across the equal sign. The equation is transformed symmetrically. Likewise, a coefficient does not simply move underneath the other side. Both sides are divided by that coefficient. A denominator does not jump across and become multiplication. Both sides are multiplied by the denominator. The shortcuts are compact ways of describing balanced operations. They are safe only when the underlying action is understood. The equal sign should remain steady throughout the work. Each new line must be equivalent to the one before it. Do not write an expression, then an equal sign, then an unrelated operation. For example, 3x plus 6 equals 12 does not equal subtract 6. Subtract 6 is an instruction, not a value. Instead, write 3x plus 6 minus 6 equals 12 minus 6. Or write the resulting equivalent equation. 3x equals 6. The equal sign always connects quantities with equal value. Clear notation protects mathematical meaning. Solving equations is not about making the variable lonely for its own sake. It is about revealing which values preserve a relationship. The variable may represent a distance, a price, a time, a temperature, a number in a pattern, an unknown measurement. The equation collects the known relationships. Balanced operations uncover the value that fits them. One step removes addition, another removes multiplication. Parentheses open, fractions clear, like terms gather, and sometimes the variable disappears entirely, revealing that every allowed value works or that none can. Each result tells us something about the relationship. One solution means the two sides meet once. No solution means they remain apart. Infinitely many solutions means they were the same relationship all along. There is no need to fear a long equation. It is still made from familiar pieces. A coefficient, a constant, a group, a fraction, a repeated variable term. Begin by simplifying what can be simplified. Then preserve balance. One operation on the left, the same operation on the right, a clear new line, then another. The equation gradually becomes quieter. The extra structure falls away until the value of the variable becomes visible. In the next part, we will move slowly into inequalities, number line solutions, interval thinking, compound conditions, and the important reason an inequality reverses when multiplied or divided by a negative number. An equation says that two quantities are exactly equal. An inequality says that one quantity is larger, smaller, or possibly equal to another. The symbols change, but the central idea remains familiar. An inequality compares positions on the number line. It describes order. 5 is greater than 2. -3 is less than 1. A temperature may be at least 10 degrees. A speed may need to remain below a limit. A budget may allow no more than a certain amount. These are not statements of exact equality. They describe ranges of possible values. This is why an inequality often has many solutions rather than one. Consider x greater than 3. There is not one single value of x. 4 works, 5 works, 3.1 works, 100 works. Every real number to the right of 3 on the number line satisfies the inequality. The solution is a region, not a single point. The symbol greater than points toward the smaller quantity and opens toward the larger quantity. In x greater than 3, the wider side faces x. This tells us that x lies above 3. In x less than 3, the narrow point faces x. This tells us that x lies below 3. The symbols may be read in either direction. 5 is greater than 2, or 2 is less than 5. Both statements describe the same relationship. The order of the quantities changes. The symbol changes with it. A useful visual reminder is that the open side faces the larger value. The pointed side faces the smaller value. There are 4 common inequality symbols: greater than, less than, greater than or equal to, and less than or equal to. The words or equal to include the boundary value. X greater than 3 does not include 3. 3 is not greater than itself. But x greater than or equal to 3 does include 3. It also includes every value above 3. The same difference appears with less than. X less than 5 excludes 5. X less than or equal to 5 includes it. On a number line, an open circle shows that the boundary is excluded. A filled circle shows that the boundary is included. For x greater than 3, place an open circle at 3. Shade or extend the line to the right. For x greater than or equal to 3, use a filled circle at 3, then extend to the right. For x less than 3, use an open circle and extend left. For x less than or equal to 3, use a filled circle and extend left. The number line translates the symbol into space. Greater values lie to the right, smaller values lie to the left. The boundary point determines where the region begins. Absolute value can also be understood through number line distance. But ordinary inequalities begin with order. The number line remains the clearest picture. Solving a simple inequality resembles solving an equation. The same operation is usually performed on both sides. The goal is to isolate the variable. Consider x plus 4 greater than 9. Subtract 4 from both sides. X greater than 5. Every number above 5 makes the original statement true. Check one value. Let x equal 6. 6 plus 4 is 10. 10 is greater than 9. The inequality is true. Check a value outside the solution. Let x equal 4. 4 plus 4 is 8. 8 is not greater than 9. The inequality is false. The boundary at 5 separates values that work from values that do not. Now consider x minus 7 less than or equal to 2. Add 7 to both sides. X less than or equal to 9. 9 is included. 9 minus 7 is 2. The original inequality allows equality. Any value below 9 also works. For multiplication by a positive number, the process remains almost identical to solving an equation. Consider 3x greater than 12. Divide both sides by positive 3. X greater than 4. The direction remains the same. Multiplying or dividing both sides by a positive number preserves order. If 8 is greater than 5, then 16 is greater than 10. Both numbers were multiplied by positive 2. Their positions stretched away from 0. Their order did not reverse. Positive scaling keeps the number line facing the same direction. But multiplication or division by a negative number reverses the order. This is the most famous special rule of inequalities. Consider the true statement, 3 is greater than 1. Multiply both sides by negative 1. The values become negative 3 and negative 1. On the number line, negative 3 lies to the left of negative 1, so negative 3 is less than negative 1. The original greater than relationship has become a less than relationship. The symbol must reverse. This happens because multiplication by a negative number reflects the number line across 0. Right becomes left. Larger positions become smaller positions. Smaller positions become larger positions. The entire order reverses. Now solve negative 2x greater than 6. Divide both sides by negative 2. Because the divisor is negative, reverse the inequality symbol. X less than negative 3. Check a value from the solution region. Let x equal negative 4. Negative 2 times negative 4 is positive 8. 8 is greater than 6. The original inequality is true. Check a value outside the region. Let x equal 0. Negative 2 times 0 is 0. 0 is not greater than 6. The inequality is false. Without reversing the sign, we would incorrectly claim x greater than negative 3. That would include 0, which does not work. The reversal is therefore not a decorative rule. It protects the correct ordering. Consider negative 5x less than or equal to 20. Divide both sides by negative 5. Reverse the inequality. X greater than or equal to negative 4. Check the boundary. Negative 5 times negative 4 is 20. 20 is less than or equal to 20. True. Check a larger value, such as 0. Negative 5 times 0 is 0. 0 is less than or equal to 20. True. Check a smaller value, such as negative 10. Negative 5 times negative 10 is 50. 50 is not less than or equal to 20. False. The number line again confirms the solution. Addition and subtraction never require reversing the symbol. Only multiplication or division by a negative quantity reverses order. Adding the same number to both sides shifts both points equally along the number line. Their relative positions remain unchanged. If 5 is greater than 2, then 5 minus 10 is still greater than 2 minus 10. Negative 5 is greater than negative 8. Both points moved left by 10. The one that began farther right remains farther right. Multiplication by a positive number stretches or compresses the number line without flipping it. Multiplication by a negative number stretches or compresses and reflects it. The reflection causes the reversal. Two-step inequalities follow the same careful pattern. Consider 3x plus 5 less than 17. Subtract 5. 3x less than 12. Divide by positive 3. X less than 4. No reversal occurs because the division is positive. Now consider negative 3x plus 5 less than 17. Subtract 5. Negative 3x less than 12. Divide by negative 3. Reverse the symbol. X greater than negative 4. Check a solution such as 0. Negative 3 times 0 plus 5 is 5. 5 is less than 17. True. Check a value such as negative 10. Negative 3 times negative 10 plus 5 is 35. 35 is not less than 17. False. The solution region lies to the right of negative 4. Inequalities with variables on both sides are solved much like equations. Consider 5x plus 2 greater than 3x plus 10. Subtract 3x from both sides. 2x plus 2 greater than 10. Subtract 2. 2x greater than 8. Divide by positive 2. X greater than 4. Check x equals 5. The left side is 27. The right side is 25. The statement is true. Check x equals 3. The left side is 17. The right side is 19. The statement is false. Now consider 2x minus 7 less than 5x plus 2. Subtract 2x. Negative 7 less than 3x plus 2. Subtract 2. Negative 9 less than 3x. Divide by positive 3. Negative 3 less than x. This may be rewritten as x greater than negative 3. Both forms mean the same thing. Sometimes the variable appears on the right side after solving. That is not incorrect, but many people prefer placing the variable on the left. When the sides are swapped, the symbol must point consistently. Negative 3 less than x becomes x greater than negative 3. The relationship remains unchanged. Suppose instead we solve 4x plus 6 greater than or equal to 7x minus 3. Subtract 4x, 6 greater than or equal to 3x minus 3. Add 3, 9 greater than or equal to 3x. Divide by positive 3, 3 greater than or equal to x. Rewritten with x on the left, this becomes x less than or equal to 3. The phrase changes from 3 is at least x to x is at most 3. The same boundary and region remain. Parentheses are handled through distribution or division when possible. Consider 2 times open parentheses, x plus 3 close parentheses greater than 10. Divide by positive 2, x plus 3 greater than 5. Subtract 3, x greater than 2. Distribution would give the same result. 2x plus 6 greater than 10. Subtract 6, 2x greater than 4. Divide by 2, x greater than 2. Now consider negative 2 times open parentheses, x plus 3 close parentheses greater than 10. Dividing first requires dividing by negative 2. So reverse the inequality. X plus 3 less than negative 5. Subtract 3. Negative 2x minus 6 greater than 10. Add 6. Negative 2x greater than 16. Divide by negative 2 and reverse. X less than negative 8. The two paths agree. The negative outside the parentheses eventually causes the reversal. Inequalities can also simplify into statements that are always true or always false. Consider 2x plus 3 less than 2x plus 7. Subtract 2x from both sides. 3 less than 7. This statement is always true or always false. Consider 2x plus 3 less than 2x plus 7. Subtract 2x from both sides. 3 less than 7. This statement is always true. Every real value of x satisfies the original inequality. The solution is all real numbers. Now consider 2x plus 9 less than 2x plus 4. Subtract 2x, 9 less than 4. This is false. No real value of x satisfies the inequality. The solution set is empty. The variable disappeared because both sides changed at the same rate. The constants determine whether the relationship always holds or never holds. Consider 3 times open parentheses, x plus 2 close parentheses greater than 3x plus 1. Distribute. 3x plus 6 greater than 3x plus 1. Subtract 3x, 6 greater than 1. True. Every real x works. Now consider 3 times open parentheses, x plus 2 close parentheses less than 3x plus 1. After distribution and cancellation, we get 6 less than 1. False. No solution exists. These special outcomes resemble equations with infinitely many or no solutions. The difference is that the final statement is an inequality rather than equality. A true statement means all allowed values work. A false statement means none do. Compound inequalities combine two comparisons. They often describe a value trapped between two boundaries. For example, 3 less than x less than 8. This means x is greater than 3 and less than 8. Both conditions must be true. The solution lies between 3 and 8. Neither boundary is included. On the number line, place open circles at 3 and 8. Shade the interval between them. A value such as 5 works. 5 is greater than 3 and less than 8. A value such as 9 fails because it is not less than 8. A value such as 2 fails because it is not greater than 3. The word "and" is important. The solution must satisfy both inequalities at the same time. A compound inequality may include one or both boundaries. 3 less than or equal to x less than 8 includes 3 but excludes 8. 3 less than x less than or equal to 8 excludes 3 but includes 8. 3 less than or equal to x less than or equal to 8 includes both. The number line circles show each decision. Compound inequalities can often be solved across all 3 sections at once. Consider 2 less than x plus 1 less than 6. Subtract 1 from every part. 2 minus 1 less than x plus 1 minus 1 less than 6 minus 1. The result is 1 less than x less than 5. The same operation was applied to the left expression, the middle expression, and the right expression. The balance of both comparisons was preserved. Now consider -4 less than or equal to 2x less than 10. Divide all three parts by +2. -2 less than or equal to x less than 5. The symbols remain unchanged because the division is positive. Now consider -6 less than -2x less than 4. Divide all three parts by -2. Every inequality direction must reverse. The left comparison and the right comparison both flip. If performed mechanically, the result may appear as 3 greater than x greater than -2. This is correct. It can be rewritten in increasing order as -2 less than x less than 3. The solution lies between -2 and 3. Check a value such as 0. -2 times 0 is 0. -6 is less than 0. And 0 is less than 4. Both conditions are true. Check x equals 4. -2 times 4 is -8. -6 is not less than -8. The value fails. Multiplying or dividing a complete compound inequality by a negative number reverses both inequality signs. The order of the boundary values may then need rearranging for readability. Some compound inequalities use the word, or rather than and. For example, x less than -2, or x greater than 5. This describes two separate regions. All values below -2 work. All values above 5 work. Values between -2 and 5 do not. On the number line, shade left from -2 and right from 5. The regions extend away from one another. The word or usually combines alternatives. A value needs to satisfy at least one condition. It does not need to satisfy both. By contrast, x greater than 2 and x less than 5 describes the overlap between two conditions. The result is the interval between 2 and 5. The distinction between and an or is central, and usually means intersection, the shared region where both statements are true, or usually means union. All values that satisfy either statement. Consider x greater than 3 and x greater than 7. To satisfy both, x must be greater than 7. Values above 7 automatically satisfy x greater than 3 as well. The overlapping region is the stricter condition. Now consider x greater than 3 or x greater than 7. Any value greater than 3 satisfies at least one condition. So the solution simplifies to x greater than 3. The wider region is enough. Consider x less than 2 and x greater than 5. No number can satisfy both. A value cannot lie below 2 and above 5 simultaneously. The solution set is empty. But x less than 2 or x greater than 5 has two valid outer regions. The logical connector changes everything. Absolute value inequalities combine distance with ranges. Consider the absolute value of x less than 3. This asks for all numbers whose distance from 0 is less than 3. Those numbers lie between -3 and +3. So the solution is -3 less than x less than 3. The endpoints are excluded because the distance must be strictly less than 3. Now consider the absolute value of x less than or equal to 3. The distance may equal 3. So -3 less than or equal to x, less than or equal to 3. The solution is a closed interval centered on 0. A less than absolute value inequality usually creates an inside region. The values remain close to the center. Now consider the absolute value of x greater than 3. This asks for numbers whose distance from 0 is more than 3. They lie farther than 3 units away. So x is less than -3, or x is greater than 3. The solution contains two outer regions. A greater than absolute value inequality usually creates an outside result. The values lie far from the center. This pattern can be understood without memorization. Absolute value is distance. Distance less than a number means stay close. Distance greater than a number means move far away. The center does not always need to be 0. Consider the absolute value of x minus 2 less than 4. This asks for values whose distance from 2 is less than 4. Move 4 units left from 2. The left boundary is -2. Move 4 units right. The right boundary is 6. So -2 less than x less than 6. Algebraically, write -4 less than x minus 2 less than 4. Then add 2 to every part. -2 less than x less than 6. The distance interpretation and the algebraic method agree. Now consider the absolute value of x minus 2 greater than or equal to 4. the distance from 2 must be at least 4. So x lies at or below -2, or at or above 6. The solution is x less than or equal to -2 or x greater than or equal to 6. The boundary values are included because the inequality allows equality. Absolute value inequalities can become more complicated when coefficients appear inside. Consider the absolute value of 2x minus 1 less than 5. Rewrite as -5 less than 2x minus 1 less than 5. Add 1 to all parts. -4 less than 2x less than 6. Divide by +2. -2 less than x less than 3. The solution lies inside the interval. Now consider the absolute value of 2x minus 1 greater than 5. Create two cases. 2x minus 1 greater than 5, or 2x minus 1 less than -5. Solve the first. 2x greater than 6. X greater than 3. Solve the second. 2x less than -4. X less than -2. The result is x less than -2 or x greater than 3. Again, the outer regions appear. Not every absolute value inequality has a solution. The absolute value of x less than -2 has no solution. A distance cannot be less than a negative number. The absolute value of x greater than -2 is true for every real x, because every absolute value is 0 or positive, and every non-negative number is greater than -2. Boundary reasoning can sometimes solve these cases immediately. The value on the other side of the inequality matters. If it is negative, compare it with the fact that absolute value can never be negative. Interval notation offers a compact way to describe inequality solutions. An interval is written using parentheses or square brackets. Parentheses indicate that an endpoint is excluded. Square brackets indicate that an endpoint is included. The solution x greater than 3 can be written as the interval from 3 to infinity. Because 3 is excluded, use a parentheses at 3. Infinity always uses a parentheses because infinity is not a reachable endpoint or ordinary real number. The interval is written as open parentheses 3, infinity close parentheses. The solution x greater than or equal to 3 uses a square bracket at 3, square bracket 3, infinity close parentheses. The solution -2 less than x less than 5 becomes open parentheses, -2, 5 close parentheses. If both endpoints are included, use square brackets around both. If only one is included, use one bracket and one parentheses. Interval notation and inequality notation describe the same set in different forms. A number line provides the picture. The inequality provides the comparison. The interval provides the compact set description. For two separate regions, a union symbol joins the intervals. X less than -2 or x greater than 5 becomes the interval from -infinity to -2, joined with the interval from 5 to infinity. The boundary symbols depend upon whether the inequalities include equality. Infinity always remains open. The union symbol means all values from either interval. Set builder notation provides another description. It may read as the set of all x such that x is greater than 3. This notation emphasizes the condition defining the set. Different forms are useful in different contexts. The mathematics remains the same. Inequalities also appear in real-world constraints. Suppose a person has no more than 50 units to spend. A product costs 8 units. Let x represent the number of products purchased. The cost is 8x. No more than 50 means less than or equal to 50. So 8x less than or equal to 50. Divide by 8. X less than or equal to 6.25. But if x represents whole products, fractional purchases may not be allowed. The greatest possible whole number is 6. The algebraic inequality gives a real number range. The context restricts x to whole numbers. 6 products cost 48 units. 7 would cost 56. So 6 is the maximum. The phrase at least creates a greater than or equal to inequality. Suppose a container must hold at least 12 liters. If it already contains 4 liters and water enters at 2 liters per minute, the amount after t minutes is 4 plus 2t. At least 12 means 4 plus 2t greater than or equal to 12. Subtract 4. 2g greater than or equal to 8. Divide by 2. 2g greater than or equal to 4. The container reaches 12 liters after 4 minutes. Any later time also satisfies the requirement, assuming the flow continues. The solution is not 1 instant alone. It is 4 minutes or more. The phrase no more than means less than or equal to. At most means less than or equal to. At least means greater than or equal to. More than means strictly greater than. Less than means strictly less than. These phrases determine whether the boundary is included. Suppose a ride requires a passenger to be at least 120 centimeters tall. Height h must satisfy h greater than or equal to 120. A person exactly 120 centimeters tall qualifies. Suppose the rule instead says taller than 120 centimeters. Then h must be greater than 120. The exact boundary no longer qualifies. The difference between strict and inclusive language matters. Inequalities can also describe error and tolerance. Suppose a machine part should measure 10 centimeters, with an allowed error of no more than 0.02 centimeters. Let x be the actual measurement. The distance between x and 10 must be at most 0.02. This can be written as the absolute value of x minus 10 less than or equal to 0.02. The solution lies between 9.98 and 10.02. The part may be slightly smaller or slightly larger. The absolute value captures both directions in one statement. Graphing inequalities in two variables introduces regions of the plane. Consider y greater than x plus 1. The boundary is the line y equals x plus 1, but the inequality asks for points whose y-coordinate lies above that line. A dashed boundary line is used when equality is excluded. A solid line is used when equality is included. The plane is shaded on the side containing the solutions. Every point in the shaded region makes the inequality true. This is the two-dimensional version of shading a number line. A boundary separates working points from non-working points. For y less than or equal to 2x minus 3, draw the line y equals 2x minus 3. Because equality is allowed, use a solid line. Shade the region below it. A test point can help determine the correct side. The origin, 0, 0, is often convenient when it is not on the boundary. Substitute it into the inequality. For y greater than x plus 1, 0 greater than 1 is false, so the origin is not in the solution region. Shade the opposite side from the origin. For y less than or equal to 2x plus 3, substitute the origin. 0 is less than or equal to 3. True, so shade the side containing the origin. The same logic extends to systems of inequalities. A system asks for points satisfying several conditions at once. Each inequality shades one region. The solution is the overlap. For example, y greater than x and y less than negative x plus 4 create two half-planes. Their shared region lies between the lines. A point must satisfy both comparisons. The overlap may form a wedge, a strip, a polygon, or no region at all. The geometry makes the word invisible. Only the common area survives. Linear programming uses such feasible regions to find maximum or minimum values under constraints. A business may have limited material, time, and budget. Each limitation becomes an inequality. Their overlap contains all workable plans. An objective expression is then evaluated across that region. Often the best value occurs at a corner point. The topic can become advanced, but the foundation remains simple. An inequality describes an allowed side of a boundary. Several inequalities describe several allowed sides. The feasible region is where those permissions overlap. Care is needed when multiplying inequalities by expressions whose sign is unknown. Consider dividing both sides by x. If the sign of x is not known, we do not know whether the inequality should reverse. If x is positive, the direction remains. If x is negative, the direction reverses. So a step such as dividing by a variable may require separate cases. This is one reason algebraic inequalities can be more delicate than equations. In equations, dividing both sides by a Tungo expression preserves equality regardless of whether the divisor is positive or negative. In inequalities, the sign changes the order. The divisor's sign must be known. Consider x squared greater than x. It may be tempting to divide both sides by x and conclude x greater than 1, but this loses information. If x is negative, dividing by x reverses the inequality. If x is 0, the division is invalid. A safer approach is to move everything to one side. X squared minus x greater than 0. Factor. X times open parenthesis. X minus 1, close parenthesis greater than 0. Now analyze when the product is positive. A product is positive when both factors are positive or both are negative. The critical values are 0 and 1. They divide the number line into three intervals. Below 0, between 0 and 1, and above 1. Choose a test value from each interval. For x below 0, such as -1, both x and x minus 1 are negative. Their product is positive. So values below 0 work. Between 0 and 1, choose 1/2. X is positive. X minus 1 is negative. The product is negative. Those values do not work. Above 1, both factors are positive. The product is positive. Those values work. The solution is x less than 0 or x greater than 1. 0 and 1 are excluded because the original inequality is strict. The incorrect division method would have lost the entire negative region. This example introduces polynomial inequalities. They are solved by finding boundary points, dividing the number line into intervals, and checking the sign within each interval. Consider open parenthesis x minus 2 close parenthesis times open parenthesis x plus 3 close parenthesis less than or equal to 0. The factors become 0 at x equals 2 and x equals -3. These values divide the number line into 3 regions: below -3, between -3 and 2, and above 2. Choose a test value below -3, such as -4. X minus 2 is negative. X plus 3 is negative. The product is positive. Choose 0 in the middle interval. 0 minus 2 is negative. 0 plus 3 is positive. The product is negative. Choose 3 above 2. Both factors are positive. The product is positive. The inequality asks for values where the product is negative or 0, so the middle interval works. The boundary points also work because equality is included. The solution is -3 less than or equal to x less than or equal to 2. The graph of the corresponding quadratic would lie on or below the x-axis across this interval. The sign chart and the graph tell the same story. Rational inequalities involving fractions require additional boundary points where the denominator is 0. Consider open parenthesis x minus 1, close parenthesis divided by open parenthesis x plus 2 close parenthesis greater than 0. The numerator is 0 at x equals 1. The denominator is 0 at x equals -2. These values divide the number line into 3 intervals: below -2, between -2 and 1, and above 1. Test each region. Choose -3. The numerator is -4. The denominator is -1. A negative divided by a negative is positive. The interval works. Choose 0. The numerator is -1. The denominator is +2. The quotient is negative. The interval does not work. Choose 2. The numerator is +1. The denominator is +4. The quotient is positive. The interval works. The solution is x less than -2 or x greater than 1. But the boundary behavior differs. X equals -2 must always be excluded because the denominator becomes 0. X equals 1 gives a quotient of 0. Since the inequality is strictly greater than 0, 1 is also excluded. If the inequality were greater than or equal to 0, x equals 1 would be included. -2 would still be excluded. Denominator restrictions remain absolute. A fraction cannot be defined there, regardless of the comparison symbol. Inequality solutions should be checked thoughtfully. A single substitution confirms only one point. Because the solution usually contains an interval, choose values from several regions. Test a value inside, a value outside, and boundary values when appropriate. For a strict inequality, the boundary should fail. For an inclusive inequality, it should work unless the expression is undefined there. Graphing provides another check. If the inequality is x greater than -2, the shading must extend right. If a negative coefficient was divided out, verify that the sign reversed. If an absolute value inequality says less than, ask whether the solution lies near the center. If it says greater than, ask whether the result lies outside. These conceptual checks catch errors that arithmetic alone may miss. A common mistake is treating an inequality symbol like an equal sign that never changes. Most steps do preserve its direction, but negative multiplication reflects order. Another mistake is reversing the sign during addition or subtraction. That is unnecessary. Only multiplication or division by a negative quantity reverses it. A third mistake is forgetting whether a boundary is included. The small line beneath the symbol matters. Greater than is not the same as greater than or equal to. An open circle is not the same as a filled circle. Another mistake is using and when or is required. Absolute value greater than a positive number creates two outer regions joined by or. Absolute value less than a positive number creates an inner interval joined by and. Distance provides a dependable picture. Close means inside, far means outside. Compound inequalities should also be read slowly. -1 less than x, less than 4 means x lies between the boundaries. It does not mean multiply all three quantities. It contains two comparisons. -1 less than x and x less than 4. Both must hold. The middle quantity participates in both statements. This compact notation is useful because it shows the interval directly, but it should be unpacked when confusion appears. Inequalities are not incomplete equations. They answer a different kind of question. An equation may ask where two quantities meet exactly. An inequality asks where one remains above, below, within, or outside another. The answer may be an interval, several intervals, all real numbers, or no values at all. The number line becomes part of the solution. A boundary is found. Then the direction of valid values is determined. This is why checking one solution is not enough to describe the full answer. The entire region matters. A value just inside the boundary may work. A value just outside may fail. The symbol tells us whether the boundary itself belongs, and the sign of every multiplication tells us whether the order has been preserved or reflected. There is no need to rush through an inequality. Begin by solving as though the number line is nearby. Move addition and subtraction calmly. Divide by positive quantities without changing direction. When dividing by a negative quantity, imagine the line turning over. Reverse the symbol. Then place the result on the number line. Open or filled boundary. Left or right shading. Inside or outside interval. The visual result can confirm the algebra. In the next part, we will move slowly through coordinates, graphs, functions, slope, lines, and the reason an equation can describe an entire shape rather than one unknown number. A graph allows algebra to become visible. Instead of reading only symbols, we can watch a relationship take shape. A point can represent two numbers at once. A line can represent infinitely many solutions. A curve can show how one quantity changes as another changes. The page becomes a map. The algebra tells us where to look. Most basic algebraic graphs use a coordinate plane. The plane contains two number lines. One lies horizontally, the other stands vertically. The horizontal line is called the x-axis. The vertical line is called the y-axis. They cross at 0. This central point is called the origin. Its coordinates are 0, 0. Every point on the plane can be described by an ordered pair. An ordered pair contains two numbers inside parentheses. The first number gives the horizontal position. The second gives the vertical position. The point 3, 2 means move 3 units to the right from the origin. Then move 2 units upward. The point is written as open parentheses, 3, 2, close parentheses. The order matters. 3, 2 is not the same point as 2, 3. The first coordinate always belongs to x. The second belongs to y. A quiet way to remember this is horizontal first, vertical second. Walk across, then rise or fall. For the point -4, 3, begin at the origin. Move 4 units left because the x-coordinate is negative. Then move 3 units upward because the y-coordinate is positive. For the point 2, -5, move 2 units right, then 5 units downward. For -3, -2, move left and then down. The signs determine direction. Positive x lies to the right. Negative x lies to the left. Positive y lies above. Negative y lies below. The axes divide the plane into 4 regions called quadrants. The upper right region is the first quadrant. Both coordinates are positive there. The upper left region is the second quadrant. X is negative, y is positive. The lower left region is the third quadrant. Both coordinates are negative. The lower right region is the fourth quadrant. X is positive, y is negative. The quadrants are numbered counterclockwise, beginning in the upper right. A point on an axis does not lie inside a quadrant. If x equals 0, the point lies on the y-axis. If y equals 0, the point lies on the x-axis. The point 0, 5 lies 5 units above the origin on the vertical axis. The point -3, 0 lies 3 units left on the horizontal axis. Coordinates create a precise location system. A point no longer needs to be described vaguely as somewhere above and to the right. Its ordered pair gives an exact address. Algebraic equations can describe collections of these addresses. Consider the equation y equals x plus 1. This does not ask for one value of x. It describes a relationship between x and y. Every value chosen for x produces a corresponding value of y. If x equals 0, y equals 1. This creates the point 0, 1. If x equals 1, y equals 2. The point is 1, 2. If x equals 2, y equals 3. The point is 2, 3. If x equals -1, y equals 0. The point is -1, 0. Each ordered pair satisfies the same equation. When these points are plotted, they lie along one straight line. The line represents every possible solution. There are infinitely many points between the ones we calculated. The graph fills them in continuously. An equation with two variables often has infinitely many solutions. Each solution is an ordered pair. A graph gathers them into a visible shape. This is different from an equation such as x plus 3 equals 7. That equation contains one variable and usually one solution. But y equals x plus 1 allows x to vary. As x changes, y changes with it. The graph shows the complete relationship. A table of values can help create the graph. Choose several x values. Substitute each into the equation. Calculate the corresponding y value. Then plot the ordered pairs. For y equals 2x plus 1, let x equal -2. Y equals 2 times -2 plus 1. That becomes -4 plus 1. Y equals -3. The first point is -2, -3. Let x equal -1. Y equals -1. The point is -1, -1. Let x equal 0. Y equals 1. The point is 0, 1. Let x equal 1. Y equals 3. The point is 1, 3. Let x equal 2. Y equals 5. The point is 2, 5. These points form a straight line. Only two distinct points are technically needed to determine a line, but plotting more points can reduce errors and reveal the pattern. The equation y equals 2x plus 1 is written in a form called slope-intercept form. The general structure is y equals mx plus b. The letter m represents the slope. The letter b represents the y-intercept. The y-intercept is the point where the line crosses the y-axis. Because every point on the y-axis has x-coordinate 0, substitute 0 for x. Y equals m times 0 plus b. The product becomes 0, so y equals b. The line crosses the y-axis at 0, b. In y equals 2x plus 1, b equals 1. The y-intercept is 0, 1. This is visible in the table. When x equals 0, y equals 1. The slope is 2. Slope describes how steeply a line rises or falls. It measures vertical change compared with horizontal change. Slope is often described as rise over run. The rise is the change in y. The run is the change in x. Suppose one point is 0, 1 and another is 1, 3. Moving from the first point to the second, x increases by 1. That is a run of 1. Y increases by 2. That is a rise of 2. The slope is 2 divided by 1, so the slope is 2. The line rises 2 units for every 1 unit moved to the right. From 0, 1, move right 1, and up 2. The new point is 1, 3. Move right 1, and up 2 again. The next point is 2, 5. The same movement continues because a straight line has constant slope. The slope can also be calculated from any 2 points on the line. Take the change in y. Divide by the change in x. Suppose the points are 2, 5 and 5, 11. The change in y is 11 minus 5. That equals 6. The change in x is 5 minus 2. That equals 3. The slope is 6 divided by 3. The result is 2. The same line has the same slope everywhere. The points may be far apart or close together. The ratio remains constant. The order of subtraction must be consistent. If we calculate second y minus first y, we must also calculate second x minus first x. Reversing both subtraction orders produces the same result. 5 minus 11 over 2 minus 5 gives -6 over -3. The result is still +2. But reversing only one subtraction creates the wrong sign. The numerator and denominator must describe movement in the same direction. A positive slope rises from left to right. As x increases, y increases. The larger the positive slope, the steeper the rise. A slope of 1 rises 1 unit for every 1 unit to the right. A slope of 3 rises 3 units for every 1 unit right. A slope of 1/2 rises 1 unit for every 2 units right. All are positive. Their steepness differs. A negative slope falls from left to right. As x increases, y decreases. Consider y equals negative 2x plus 4. The y-intercept is 4. The line crosses the vertical axis at 0, 4. The slope is negative 2. From the intercept, move right 1 and down 2. This gives the point 1, 2. Move right 1 and down 2 again. This gives 2, 0. The line descends steadily. A slope of negative 1/2 can be understood as down 1 for every 2 units to the right. Fractions often make slope movements easier when written as rise over run. Negative 3/4 can mean down 3 and right 4. It could also mean up 3 and left 4. Both movements remain on the same line. A slope of 0 produces a horizontal line. Consider y equals 3. Every point has y coordinate 3. X may be any value. The points negative 2, 3, 0, 3, and 5, 3 all lie on the same horizontal line. There is no vertical change. The rise is 0. 0 divided by any Tunyo run is 0. So the slope is 0. A vertical line has undefined slope. Consider x equals 4. Every point has x coordinate 4. The line passes through 4, 0, 4, 3, and 4, negative 5. There is vertical change, but the horizontal change is 0. Slope would require division by 0. That is undefined. So vertical lines do not have a numerical slope. Horizontal lines have slope 0. Vertical lines have undefined slope. These ideas are sometimes confused because both lines have a special relationship with the axes. The difference comes from the denominator. A horizontal line still allows horizontal movement. Its vertical change is 0. A vertical line has no horizontal change at all. The run is 0. The equation y equals mx plus b can describe every non-vertical line. It cannot describe a vertical line because a vertical line assigns many y values to one x value. In x equals 4, the value 4 is fixed horizontally. Y may be anything. Solving for y would not produce one output for every x. Vertical lines need their own simple form. X equals a constant. Horizontal lines use y equals a constant. The y-intercept may be positive, negative, or 0. In y equals 3x minus 5, the line crosses the y-axis at negative 5. In y equals negative x, the intercept is 0. The line passes through the origin. The invisible coefficient of x is negative 1, so its slope is negative 1. From the origin, move right 1 and down 1. The point 1, negative 1 lies on the line. Move left 1 and up 1. The point negative 1, 1 also lies on it. When the equation is y equals x, the slope is positive 1. The line passes through the origin and rises at a balanced diagonal. Every point has equal x and y coordinates. 1, 1, 2, 2, negative 3, negative 3. Graphing can also begin from standard form. A linear equation may be written as ax plus by equals c. For example, 2x plus 3y equals 12. One way to graph it is to solve for y. Subtract 2x from both sides. 3y equals negative 2x plus 12. Divide by 3. Y equals negative 2/3 x plus 4. Now the slope is negative 2/3. The y-intercept is 4. Begin at 0, 4. Move right 3 and down 2. This reaches 3, 2. Move right 3 and down 2 again. This reaches 6, 0. The line can be drawn through the points. Another method is to find intercepts. The x-intercept is where the line crosses the x-axis. Every point on the x-axis has y equal to 0. Substitute y equals 0 into 2x plus 3y equals 12. 2x equals 12. X equals 6. The x-intercept is 6, 0. To find the y-intercept, substitute x equals 0. 3y equals 12. Y equals 4. The y-intercept is 0, 4. 2 points determine the line. Intercepts are often convenient when the equation is written in standard form, but one intercept may not be enough. If a line passes through the origin, both intercept calculations may produce the same point. A second point must then be found another way. The x-intercept and y-intercept are different from x and y themselves. An intercept is a point where the graph crosses an axis. The x-intercept has y-coordinate 0. The y-intercept has x-coordinate 0. These points help describe position. Slope describes direction. Together, slope and one point determine a unique non-vertical line. Suppose a line has slope 3 and passes through the point 2, 5. We can build its equation using point-slope form. Y minus the known y-coordinate equals the slope multiplied by x minus the known x-coordinate. Here, y minus 5 equals 3 times open parenthesis x minus 2 close parenthesis. This equation describes every point whose movement from 2, 5 follows slope 3. We can simplify it into slope-intercept form. Distribute 3. Y minus 5 equals 3x minus 6. Add 5. Y equals 3x minus 1. The y-intercept is negative 1. Check the known point. Substitute x equals 2, y equals 6 minus 1, y equals 5. The point lies on the line. Point-slope form is useful when a point and slope are known. Slope-intercept form is useful when slope and vertical intercept matter. Standard form is useful for intercepts, integer coefficients, and certain equation systems. The forms look different. They may describe the same line. Algebra allows movement between them. Equivalent equations create identical graphs. Consider y equals 2x plus 3. Subtract 2x from both sides. Negative 2x plus y equals 3. Multiply every term by negative 1. 2x minus y equals negative 3. All three forms describe the same line. The graph does not care which form is written. The form only changes which features are easiest to see. Parallel lines have the same slope. They rise or fall at the same rate. Because they move in the same direction, distinct parallel lines never meet. Consider y equals 2x plus 1. And y equals 2x minus 4. Both slopes are 2. One crosses the y-axis at 1. The other crosses at negative 4. They remain separated by a constant vertical distance. If the intercepts were also equal, the lines would not merely be parallel, they would be the same line. Two equations can appear different while describing coincident lines. For example, y equals 2x plus 1 and 2y equals 4x plus 2. Divide the second equation by 2. It becomes y equals 2x plus 1. The graphs overlap completely. Perpendicular lines meet at a right angle. For non-vertical and non-horizontal lines, their slopes are negative reciprocals. If one slope is 2, the perpendicular slope is negative 1/2. If one slope is negative 3/4, the perpendicular slope is positive 4/3. The reciprocal exchanges numerator and denominator. The negative sign reverses direction. Multiplying the two slopes produces negative 1. A horizontal line and a vertical line are also perpendicular. The horizontal line has slope 0. The vertical line has undefined slope. Their relationship is treated separately because 0 has no reciprocal in ordinary real number arithmetic. Graphs also reveal solutions to systems of equations. A system contains two or more equations considered together. A solution must satisfy every equation in the system. Consider y equals x plus 1 and y equals negative x plus 5. Each equation describes a line. The solution to the system is the point where the lines intersect. At that point, the same x and y values satisfy both relationships. We can find the intersection graphically or solve it algebraically. Because both equations equal y, set their right sides equal. X plus 1 equals negative x plus 5. Add x to both sides. 2x plus 1 equals 5. Subtract 1. 2x equals 4. X equals 2. Substitute into either equation. Y equals 2 plus 1. Y equals 3. The solution is 2, 3. On the graph, the lines cross at that point. One intersection means one solution. Parallel distinct lines never cross. Their system has no solution. Coincident lines overlap everywhere. Their system has infinitely many solutions. The same three possibilities appeared earlier in linear equations. One solution, no solution, infinitely many solutions. Graphing makes them visible. The algebraic cancellation patterns correspond to geometric relationships. Different slopes produce one intersection. Equal slopes with different intercepts produce no intersection. Equal slopes with equal intercepts produce the same line. Systems can also be solved by substitution. Suppose y equals 2x plus 1 and x plus y equals 10. The first equation already tells us what y equals. Substitute 2x plus 1 in place of y in the second equation. X plus open parenthesis, 2x plus 1, close parenthesis equals 10. 3x plus 1 equals 10. Subtract 1, 3x equals 9. X equals 3. Then y equals 2 times 3 plus 1. Y equals 7. The solution is 3, 7. Substitution replaces one variable with an equivalent expression. The system becomes one equation with one unknown. Another method is elimination. Consider x plus y equals 7 and x minus y equals 1. Add the equations. The positive y and negative y cancel. 2x equals 8. X equals 4. Substitute into x plus y equals 7. 4 plus y equals 7. Y equals 3. The solution is 4, 3. Elimination uses addition or subtraction of equations to remove one variable. Sometimes an equation must first be multiplied, so the coefficients become opposites. Consider 2x plus y equals 9 and 3x minus 2y equals 4. Multiply the first equation by 2. 4x plus 2y equals 18. Now add it to the second equation. 4x plus 2y plus 3x minus 2y equals 18 plus 4. 7x equals 22. X equals 22 sevenths. The solution may be fractional. Substitute the value back to find y. The arithmetic may become less tidy. The method remains valid. Graphically, the lines intersect at a point with fractional coordinates. A system's solution does not need to appear at a grid intersection. Functions expand the idea of relationships. A function is a rule that assigns exactly one output to each allowed input. The input is often represented by x. The output may be represented by y, or by function notation. Instead of writing y equals 2x plus 3, we may write f of x equals 2x plus 3. The symbol f is the name of the function. F of x does not mean f multiplied by x. It means the output of function f when the input is x. The notation gives the rule a name. If f of x equals 2x plus 3, then f of 4 means substitute 4 for x. F of 4 equals 2 times 4 plus 3. The result is 11. So f of 4 equals 11. The input 4 produces the output 11. If f of negative 2 is requested, substitute negative 2. 2 times negative 2 plus 3 gives negative 1. So f of negative 2 equals negative 1. The parentheses in function notation contain the input. They are not ordinary multiplication parentheses. This distinction is learned from context. When a letter names a function, f of x describes evaluation. The domain of a function is the set of allowed inputs. The range is the set of outputs produced. For f of x equals 2x plus 3, every real number can be used as x. The domain is all real numbers. The output can also become any real number. So the range is all real numbers. For f of x equals 1, divided by x, 0 is not allowed as an input. The domain excludes 0. The range also excludes 0, because 1 divided by a real Tungo number can never equal 0. For f of x equals the square root of x, the real number domain includes 0 and positive values. Negative inputs do not produce real outputs under the ordinary square root function. The range is also 0 or positive. A function may be represented by an equation, a table, a graph, a set of ordered pairs, or a verbal rule. The representations look different. They describe the same input-output relationship. A table may show x values in one column and outputs in another. A graph places inputs horizontally and outputs vertically. An equation gives a symbolic rule. A description might say double the input and subtract 5. Each representation reveals different features. An important rule says that one input cannot have two different outputs within the same function. The input 3 may not produce both 5 and 8 under one fixed function rule. Different inputs may produce the same output. That is allowed. For example, f of x equals x squared. F of 2 equals 4. F of negative 2 also equals 4. Two inputs share one output. The function condition remains satisfied because each individual input produces only one result. The vertical line test helps determine whether a graph represents a function of x. Imagine moving a vertical line across the graph. If the vertical line touches the graph more than once at any x position, then one input corresponds to multiple outputs. The graph is not a function of x. A non-vertical straight line passes the vertical line test. Every x position has one y value. A circle fails. For many x values, a vertical line crosses the circle twice. One input has an upper and lower output. The circle is still a valid relation. It is simply not a function of x, unless restricted to part of the circle. A vertical line also fails the test because one x value has infinitely many y values. A horizontal line passes. Every input gives the same output. Constant functions are still functions. The output does not need to change. Function notation allows several functions to appear without confusion. F of x may equal 2x plus 1. G of x may equal x squared. The names f and g tell us which rule to use. F of 3 equals 7. G of 3 equals 9. The same input enters different machines. Different rules produce different outputs. Functions can also be combined. F plus g evaluated at x means add f of x and g of x. If f of x equals 2x and g of x equals x plus 3, then f plus g of x equals 2x plus x plus 3. That simplifies to 3x plus 3. The functions are added output by output. They can also be subtracted, multiplied, or divided, where the denominator is tungo. Composition places one function inside another. F of g of x means use g first, then place its output into f. Suppose f of x equals 2x plus 1, and g of x equals x squared. Then f of g of x means replace the input of f with x squared. The result is 2x squared plus 1. But g of f of x means square the output of f. Open parenthesis 2x plus 1, close parenthesis squared. These are usually different. Order matters in composition. The inner function acts first. The outer function acts second. Composition resembles a sequence of machines. A number enters the first machine. Its output becomes the input of the next. If x equals 3, g of 3 is 9. Then f of 9 is 19. So f of g of 3 equals 19. For the reverse order, f of 3 is 7. Then g of 7 is 49. So g of f of 3 equals 49. The same functions in a different order produce different results. Inverse functions reverse input and output. If a function turns an input into an output, its inverse attempts to take the output back to the original input. Consider f of x equals 2x plus 3. Begin with x, multiply by 2, then add 3. To reverse the process, subtract 3, then divide by 2. The inverse rule is open parenthesis, x minus 3 close parenthesis, divided by 2. If the original input is 4, f of 4 is 11. Apply the inverse to 11. 11 minus 3 is 8. 8 divided by 2 is 4. The starting value returns. Not every function has an inverse that is also a function across its entire domain. F of x equals x squared sends both 2 and negative 2 to 4. If an inverse receives 4, it would need to choose between 2 and negative 2. That would produce two outputs from one input. To create an inverse function, the original domain may be restricted. If x is limited to 0 and positive values, then the inverse of x squared is the principal square root. The restriction makes the original function one-to-one. A one-to-one function gives different outputs for different inputs. No two inputs share one output. Its graph passes a horizontal line test. A horizontal line should not cross the graph more than once. This condition allows the input-output relationship to be reversed without ambiguity. Graphs also show increasing and decreasing behavior. A function is increasing across an interval when its outputs rise as the inputs increase. A positive slope line is increasing everywhere. A function is decreasing where outputs fall as inputs increase. A negative slope line is decreasing everywhere. Curved functions may increase in one region and decrease in another. The graph of x squared decreases as x moves from large negative values towards 0. Then it increases after 0. The turning point is the vertex. The graph forms a U-shaped curve called a parabola. Quadratic functions will be explored more deeply in the next part. For now, the graph shows something an equation alone may hide. The function changes direction. Its slope is not constant. Linear functions change at a constant rate. In y equals 3x plus 2, Every increase of 1 in x creates an increase of 3 in y. The rate of change is always 3. This constant rate is the slope. A table for the function reveals equal differences. If x increases from 0 to 1, y rises from 2 to 5. If x increases from 1 to 2, y rises from 5 to 8. Each step adds 3. A nonlinear function does not maintain the same difference. For y equals x squared, the outputs for x equals 0, 1, 2, and 3 are 0, 1, 4, and 9. The changes are 1, then 3, then 5. The rate itself changes. The graph curves. This difference between constant and changing rates is central. Lines represent steady change. Curves represent change that accelerates, slows, reverses, or follows another pattern. The slope between 2 points on a curve is an average rate of change. It tells us how much the output changed across an interval. Suppose f of x equals x squared. Between x equals 1 and x equals 3, the output changes from 1 to 9. The change in output is 8. The change in input is 2. The average rate is 4. A straight line connecting the points 1, 1 and 3, 9 would have slope 4. But the curve itself does not have slope 4 everywhere between those points. Its steepness changes. Calculus later studies the slope at an individual point. Algebra prepares the foundation through functions, graphs, and average rates. Piecewise functions use different rules in different parts of the domain. A taxi fare might follow one rule for an initial distance and another after a threshold. A shipping price may be constant within one weight range and increase in another. A piecewise definition lists each formula together with the inputs for which it applies. The graph may contain several line segments or curves. Open and filled circles can show whether boundary inputs belong to one piece or another. These are the same boundary ideas used in inequalities. A filled point means included. An open point means excluded. Functions can also model direct variation. Y varies directly with x when y equals kx for some constant k. The graph is a line through the origin. The constant k is the slope and the constant of proportionality. If y equals 4x, doubling x doubles y. Tripling x triples y. The ratio y over x remains 4 whenever x is tungoo. Direct variation describes constant proportional relationships. Cost at a fixed price per item. Distance at constant speed. Scale drawings. Conversions between proportional units. Inverse variation has the form y equals k divided by x. As x increases, y decreases in a way that keeps the product xy constant. If y equals 12 divided by x, then xy always equals 12. When x is 1, y is 12. When x is 2, y is 6. When x is 3, y is 4. When x is 6, y is 2. The graph is not a line. It forms two curved branches when positive and negative inputs are included. X cannot equal 0 because division by 0 is undefined. The axes act as asymptotes. The graph approaches them without touching them. Inverse variation appears when a fixed amount is shared. If 12 units of work are divided among more workers under ideal conditions, the time per worker may decrease. If a fixed distance is traveled at higher speed, the required time decreases. The product stays constant within the model. Algebraic models are simplifications. Real situations may include extra conditions. Traffic may affect travel time. Workers may interfere with one another. A model captures selected relationships. The graph helps show what the model predicts. Transformations allow a basic graph to shift, stretch, or reflect. Consider the parent function y equals x squared. Adding 3 outside gives y equals x squared plus 3. Every output increases by 3. The entire graph shifts upward 3 units. Subtracting 2 shifts it downward. Replacing x with x minus 4 shifts the graph to the right 4 units. Replacing x with x plus 4 shifts the graph to the left 4 units. The horizontal directions may initially feel reversed. Y equals open parenthesis, x minus 4 close parenthesis squared reaches its minimum when x minus 4 equals 0. That occurs at x equals 4. So the vertex moves right to 4. Y equals open parenthesis, x plus 4 close parenthesis squared reaches its minimum when x equals negative 4. So the graph moves left. The inside change determines where the input expression becomes 0. Multiplying the entire function by -1 reflects the graph across the x-axis. Y equals -x squared opens downward instead of upward. Replacing x with -x reflects a graph across the y-axis. For some functions, such as x squared, this reflection produces the same graph because positive and negative inputs already share equal outputs. Such functions are called even functions. F of -x equals f of x. Their graphs are symmetric about the y-axis. Functions such as f of x equals x cubed satisfy f of -x equals negative f of x. These are called odd functions. Their graphs have rotational symmetry around the origin. The words even and odd here describe symmetry properties. They do not mean the function accepts only even or odd numbers. Graphing technology can display these relationships quickly, but drawing a graph by hand remains useful because it forces the structure to be understood. A calculator may show a line. Algebra explains why it has that slope. A graphing tool may show an intersection. Solving explains the exact coordinates. A screen may hide a restricted point because of resolution. Domain reasoning reveals it. Technology supports understanding. It does not replace the meaning of the symbols. Graph windows can also mislead. A curve may appear flat because the vertical scale is too large. Two lines may appear parallel while intersecting outside the visible window. A function may appear to end when the graphing range simply stops. An asymptote may look like part of the graph. Changing the viewing window can reveal different behavior. The algebraic equation provides information beyond one picture. A graph is a window into the relationship, not the relationship's complete existence. The coordinate plane gives algebra a landscape. Variables become directions. Ordered pairs become locations. Equations become paths. Slope becomes movement. Intercepts become crossings. Systems become meetings. Functions become input-output machines drawn as shapes. A long equation can now be understood as more than a request to isolate x. It may describe an entire collection of possible points. This is why one algebra problem asks for a number, while another asks for a graph. The number may be one solution. The graph may be every solution at once. A useful rhythm for graphing a line is simple. Rewrite the equation in a convenient form. Identify the slope and an intercept. Plot one reliable point. Use the slope to find another. Draw the line through them, then check a point in the original equation. For a function, ask about its domain, its outputs, its intercepts, its direction of change, and whether every input has only one output. These questions make the graph readable. There is no need to absorb the entire coordinate plane at once. Begin at the origin, move horizontally, then vertically. One point appears, another point follows. A line forms between them. The equation and the picture begin describing the same quiet relationship. In the next part, we will move slowly through polynomials, factoring, quadratic equations, parabolas, roots, the quadratic formula, and why one equation may have two answers, one repeated answer, or no real answer at all. A polynomial is an algebraic expression built from terms containing variables raised to whole number powers. The expression 3x squared plus 5x minus 2 is a polynomial. So is x cubed minus 4x, and so is 7. A constant by itself is also a polynomial. Polynomials can contain one term, two terms, three terms, or many terms. A polynomial with one term is called a monomalial. 5x squared is a monomalial. Negative 3ab is another. A polynomial with two terms is called a binomial. X plus 4 is a binomial. 2x squared minus 7 is another. A polynomial with three terms is called a trinomial. X squared plus 5x plus 6 is a trinomial. The names describe the number of terms. They do not change the mathematics. The degree of a term is the total power of its variables. The term 5x cubed has degree 3. The term 2x squared y has degree 3 because the exponents add 2 for x, 1 for y. The total is 3. A Kundio constant has degree 0. The degree of a polynomial is the highest degree among its terms after like terms have been combined. For example, 4x cubed plus 2x squared minus 7x plus 1 has degree 3. The highest exponent is 3. The term 4x cubed is the leading term when the polynomial is written in descending order. Its coefficient, 4, is the leading coefficient. Writing polynomials in descending order helps reveal their structure. The highest power comes first, then the next, then lower powers. Finally, the constant. A polynomial such as 3 plus 2x squared minus 5x is usually rewritten as 2x squared minus 5x plus 3. The value has not changed. The arrangement has become easier to recognize. Polynomials can be added and subtracted by combining like terms. Consider 2x squared plus 3x minus 4, added to 5x squared minus x plus 7. Group the x squared terms. 2x squared plus 5x squared becomes 7x squared. Group the x terms. 3x minus x becomes 2x. Group the constants. Negative 4 plus 7 becomes 3. The result is 7x squared plus 2x plus 3. Subtraction requires careful attention to every sign. Suppose we subtract the polynomial 5x squared minus x plus 7 from 2x squared plus 3x minus 4. Write the first polynomial, then distribute a negative sign through the second. 2x squared plus 3x minus 4 minus 5x squared plus x minus 7. Now combine like terms. 2x squared minus 5x squared becomes negative 3x squared. 3x plus x becomes 4x. Negative 4 minus 7 becomes negative 11. The result is negative 3x squared plus 4x minus 11. The subtraction applies to the entire second polynomial. Every sign changes. Multiplying polynomials uses repeated distribution. A monomial multiplied by a polynomial is handled one term at a time. Consider 3x times open parenthesis, 2x squared minus 5x plus 4 close parenthesis. Multiply 3x by each term. 3x times 2x squared gives 6x cubed. 3x times negative 5x gives negative 15x squared. 3x times 4 gives 12x. The result is 6x cubed minus 15x squared plus 12x. Each coefficient is multiplied. Exponents of the same variable are added. The outside factor reaches every term. Multiplying two binomials creates four products. Consider open parenthesis, x plus 2 close parenthesis, times open parenthesis x plus 5 close parenthesis. Multiply x by both terms in the second binomial, x squared plus 5x. Then multiply 2 by both terms, 2x plus 10. Combine like terms. 5x plus 2x becomes 7x. The result is x squared plus 7x plus 10. The first term comes from multiplying x by x. The constant comes from multiplying 2 by 5. The middle coefficient comes from adding the two cross products. This pattern becomes useful when factoring. If we see x squared plus 7x plus 10, we can ask which two numbers multiply to 10 and add to 7. The numbers are 2 and 5. So the polynomial factors into open parenthesis x plus 2 close parenthesis times open parenthesis x plus 5 close parenthesis. Factoring reverses multiplication. It rewrites a polynomial as a product. The expanded form shows combined terms. The factored form shows the pieces that multiply. Consider x squared plus 8x plus 15. We seek two numbers whose product is 15 and whose sum is 8. 3 and 5 work. 3 times 5 is 15. 3 plus 5 is 8. So the factorization is open parenthesis x plus 3 close parenthesis times open parenthesis x plus 5 close parenthesis. Distribute to check. X squared plus 5x plus 3 x plus 15. Combine the middle terms. X squared plus 8x plus 15. The original polynomial returns. Now consider x squared minus 8x plus 15. The constant is positive 15. The middle coefficient is negative 8. We need two numbers whose product is positive 15 and whose sum is negative 8. Both numbers must be negative. Negative 3 and negative 5 work. Their product is positive 15. Their sum is negative 8. So the factorization is open parenthesis x minus 3 close parenthesis times open parenthesis x minus 5 close parenthesis. Now consider x squared plus 2x minus 15. The constant is negative. The two numbers must have opposite signs. We need a product of negative 15 and a sum of positive 2. 5 and negative 3 work. 5 times negative 3 is negative 15. 5 plus negative 3 is 2. so the factorization is open parenthesis x plus 5 close parenthesis times open parenthesis x minus 3 close parenthesis. The signs can be understood through the product and sum. A positive constant means the two signs match. A positive middle coefficient means both are positive. A negative middle coefficient means both are negative. A negative constant means the signs differ. The middle coefficient tells us which sign has the larger magnitude. This method works when the coefficient of x squared is 1. The trinomial has the form x squared plus bx plus c. We seek two numbers that multiply to c and add to b. Some trinomials do not factor using integers. For example, x squared plus x plus 1 has no pair of integers that multiply to 1 and add to 1. The integer factor pairs of 1 are 1 and 1, whose sum is 2, or negative 1 and negative 1, whose sum is negative 2. So the polynomial does not factor into integer binomials. It may still have roots found through another method. Factoring over integers is only one possibility. When the leading coefficient is not 1, factoring requires another step. Consider 2x squared plus 7x plus 3. Multiply the leading coefficient and the constant. 2 times 3 is 6. Now find two numbers that multiply to 6 and add to 7. 1 and 6 work. Rewrite the middle term 7x as x plus 6x. The expression becomes 2x squared plus x plus 6x plus 3. Group the first two terms and the last two. Open parenthesis 2x squared plus x close parenthesis plus open parenthesis 6x plus 3 close parenthesis. Factor each group. X times open parenthesis 2x plus 1 close parenthesis plus 3 times open parenthesis 2x plus 1 close parenthesis. Now both groups contain the same binomial factor. Factor it out. Open parenthesis 2x plus 1 close parenthesis times open parenthesis x plus 3 close parenthesis. Distribute to check. 2x squared plus 6x plus x plus 3. Combine the middle terms. 2x squared plus 7x plus 3. The method is sometimes called splitting the middle term. The middle term is rewritten so that grouping becomes possible. Consider 3x squared minus 11x minus 4. Multiply the leading coefficient and constant. 3 times negative 4 is negative 12. We need two numbers that multiply to negative 12 and add to negative 11. Negative 12 and positive 1 work. Rewrite negative 11x as negative 12x plus x. 3x squared minus 12x plus x minus 4. Group. Open parenthesis 3x squared minus 12x close parenthesis plus open parenthesis x minus 4 close parenthesis. Factor the first group. 3x times open parenthesis x minus 4 close parenthesis. The second group is already 1 times open parenthesis x minus 4 close parenthesis. Factor the common binomial. Open parenthesis x minus 4 close parenthesis times open parenthesis 3x plus 1 close parenthesis. The factorization can be written in either order. Multiplication is commutative. The factors may switch places. The value remains unchanged. Before attempting more complicated factoring, always look for a greatest common factor. Consider 6x squared plus 15x. Both terms contain 3x. Factor it first. 3x times open parenthesis 2x plus 5 close parenthesis. Now the expression is fully factored over the integers. If we ignored the common factor, the remaining structure would be harder to see. Consider 4x cubed minus 16x. Both terms share 4x. Factor it out. 4x times open parenthesis x squared minus 4 close parenthesis. The expression inside is a difference of squares. X squared minus 4 is x squared minus 2 squared, so it factors further. Open parenthesis x minus 2 close parenthesis times open parenthesis x plus 2 close parenthesis. The complete factorization is 4x times open parenthesis x minus 2 close parenthesis times open parenthesis x plus 2 close parenthesis. Factoring often happens in stages. First, the greatest common factor, then a recognizable pattern, then perhaps another pattern inside. The difference of squares follows a simple identity. A squared minus b squared factors into open parenthesis a minus b close parenthesis times open parenthesis a plus b close parenthesis. The middle products cancel when expanded. A squared plus ab minus b squared Only a squared minus b squared remains. Examples include x squared minus 9. This becomes open parenthesis x minus 3 close parenthesis times open parenthesis x plus 3 close parenthesis. 4x squared minus 25 becomes open parenthesis 2x minus 5 close parenthesis times open parenthesis 2x plus 5 close parenthesis. 9a squared minus b squared becomes open parenthesis 3a minus b close parenthesis times open parenthesis 3a plus b close parenthesis. The expression must be a difference. A squared minus b squared. A sum of squares does not factor using this real number pattern. X squared plus 9 cannot become open parenthesis x plus 3 close parenthesis times open parenthesis x minus 3 close parenthesis, because that product gives x squared minus 9. The sign matters. Perfect square trinomials create another pattern. X squared plus 6x plus 9 factors into open parenthesis x plus 3 close parenthesis squared. The first term is x squared, the last is 3 squared. The middle term is twice x times 3, that is 6x. Similarly, x squared minus 10x plus 25 factors into open parenthesis x minus 5 close parenthesis squared. The last term is 25. The middle term is negative twice x times 5. That gives negative 10x. Recognizing these patterns makes some factoring immediate, but they can always be checked by multiplication. A perfect square trinomial contains two identical factors. This becomes important when solving, because the corresponding root is repeated. A quadratic equation contains a variable raised to the second power as its highest exponent. The standard form is ax squared plus bx plus c equals 0, where a is not 0. The condition that a is not 0 matters. If a were 0, the squared term would disappear. The equation would become linear rather than quadratic. Quadratic equations often have two solutions. Sometimes one repeated solution, sometimes no real solutions. The number of solutions depends upon how the corresponding parabola meets the x-axis. Consider x squared minus 5x plus 6 equals 0. Factor the left side. We need two numbers that multiply to 6 and add to negative 5, negative 2 and negative 3. So the equation becomes open parenthesis x minus 2 close parenthesis times open parenthesis x minus 3 close parenthesis equals 0. Now use the zero product property. If a product equals 0, at least one factor must equal 0. This works because ordinary real number factors cannot multiply to 0 unless one of them is 0. So x minus 2 equals 0, or x minus 3 equals 0. The solutions are x equals 2 and x equals 3. Check. 2 squared minus 5 times 2 plus 6 is 4 minus 10 plus 6. That equals 0. 3 squared minus 15 plus 6 is 9 minus 15 plus 6. That also equals 0. The two solutions are also the x-intercepts of the graph y equals x squared minus 5x plus 6. At x equals 2, y equals 0. At x equals 3, y equals 0. The parabola crosses the x-axis at those points. Factoring reveals the intercepts directly. Consider x squared plus 6x plus 9 equals 0. Factor. Open parenthesis x plus 3 close parenthesis squared equals 0. The squared factor equals 0 only when x plus 3 equals 0. So x equals negative 3. The equation technically has two equal roots, negative 3 and negative 3. Because they are identical, we usually describe the equation as having one repeated real solution. The graph touches the x-axis at negative 3, but does not cross it. The point is the vertex. The parabola reaches 0 and turns around. Now consider x squared plus 1 equals 0. Rearrange. X squared equals negative 1. No real number squared equals negative 1. The square of a positive number is positive. The square of a negative number is also positive. The square of 0 is 0. So the equation has no real solution. Its graph y equals x squared plus 1 lies entirely above the x-axis. The basic parabola y equals x squared has been shifted upward by 1. It never reaches 0. If complex numbers are allowed, solutions do exist. A new number called I is defined so that I squared equals negative 1. Then x equals I, or x equals negative I. Complex numbers extend algebra beyond the real number line. They will appear again shortly. First, remain with the real number picture. A quadratic graph is a parabola. When the leading coefficient a is positive, the parabola opens upward. When a is negative, it opens downward. The larger the absolute value of a, the narrower the parabola appears. When the absolute value lies between 0 and 1, the parabola appears wider. The sign controls direction. The size controls vertical stretching or compression. Consider y equals x squared. Its vertex is at the origin. It opens upward. The graph is symmetric about the y-axis. The points 1, 1 and -1, 1 match. 2, 4 and -2, 4 match. The left and right sides mirror one another. Now consider y equals x squared plus 3. The graph shifts upward 3 units. The vertex becomes 0, 3. There are no x-intercepts because the minimum output is 3. Consider y equals x squared minus 4. The vertex becomes 0, -4. The graph crosses the x-axis where x squared minus 4 equals 0. Factor. Open parenthesis x minus 2 close parenthesis times open parenthesis x plus 2 close parenthesis equals 0. The x-intercepts are -2 and +2. The graph is symmetric around the y-axis. A quadratic written in vertex form appears as y equals a times open parenthesis x minus h close parenthesis squared plus k. The vertex is hk. The line of symmetry is x equals h. The value a controls opening direction and width. For y equals open parenthesis x minus 3 close parenthesis squared plus 2, the vertex is 3, 2. The graph has shifted right 3 and up 2. It opens upward because the coefficient is positive. Its minimum y value is 2. So it has no real x-intercepts. For y equals -2 times open parenthesis x plus 1 close parenthesis squared plus 8, the vertex is -1, 8. The graph opens downward because the coefficient is negative. It is vertically stretched by a factor of 2. The maximum output is 8. The axis of symmetry is x equals -1. Vertex form makes these features visible immediately. Standard form makes the y-intercept easy to see. Factored form makes the x-intercepts easy to see. The same quadratic may be written in all 3 forms. Each form reveals something different. Consider y equals x squared minus 6x plus 5. This is standard form. The y-intercept is 5. Factor it. We need numbers that multiply to 5 and add to -6, -1 and -5. So y equals open parenthesis x minus 1 close parenthesis times open parenthesis x minus 5 close parenthesis. The x-intercepts are 1 and 5. The axis of symmetry lies halfway between them. The midpoint of 1 and 5 is 3. So the vertex has x-coordinate 3. Substitute x equals 3 into the function. 9 minus 18 plus 5 equals -4. The vertex is 3, -4. So vertex form is y equals open parenthesis x minus 3 close parenthesis squared minus 4. Expand to check. X squared minus 6x plus 9 minus 4. That becomes x squared minus 6x plus 5. All 3 forms describe the same parabola. Standard form, factored form, vertex form. Each is useful for a different question. The axis of symmetry of a quadratic in standard form can be found with the expression -b divided by 2a. For a x squared plus bx plus c, the vertex's x-coordinate is -b over 2a. Consider x squared minus 6x plus 5, a equals 1, b equals -6, -b becomes +6, 2a is 2. The result is 3. This matches the midpoint of the roots. The y-coordinate is found by substituting 3 into the function. The formula works even when the quadratic does not factor easily. It locates the center of the parabola. Why does -b over 2a appear? It can be derived through completing the square. Completing the square rewrites a quadratic in vertex form by creating a perfect square trinomial. Consider x squared plus 6x plus 5. Focus first on x squared plus 6x. Take half of the x coefficient. Half of 6 is 3. Square it. 3 squared is 9. Add and subtract 9 so the value does not change. X squared plus 6x plus 9 minus 9 plus 5. The first 3 terms form a perfect square. Open parenthesis x plus 3 close parenthesis squared. The remaining constants are -9 plus 5, which equals -4. So the expression becomes open parenthesis x plus 3 close parenthesis squared minus 4. The vertex is -3, -4. Completing the square creates a square by adding the number needed to finish the pattern. Half the middle coefficient, then square it. Because adding a number changes the expression, we subtract the same number or balance it elsewhere. The transformation preserves value. Now solve x squared plus 6x plus 5 equals 0 through completing the square. Move the constant to the other side. X squared plus 6x equals -5. Take half of 6. That is 3. Square it to get 9. Add 9 to both sides. X squared plus 6x plus 9 equals 4. The left side is open parenthesis x plus 3 close parenthesis squared. So open parenthesis x plus 3 close parenthesis squared equals 4. Take square roots. X plus 3 equals +2 or -2. Subtract 3. X equals -1 or -5. These are the same solutions found through factoring. Completing the square works even when integer factoring does not. Consider x squared plus 4x minus 1 equals 0. Move the constant. X squared plus 4x equals 1. Half of 4 is 2. Square it to get 4. Add 4 to both sides. X squared plus 4x plus 4 equals 5. The left becomes open parenthesis x plus 2 close parenthesis squared. Take square roots. X plus 2 equals positive square root of 5, or negative square root of 5. Subtract 2. X equals -2 plus square root of 5, or x equals -2 minus square root of 5. These are exact solutions. They are irrational because square root of 5 is irrational. A decimal approximation could be calculated, but the radical form preserves the exact value. Completing the square also leads to the quadratic formula. Begin with the general quadratic equation. ax squared plus bx plus c equals 0. Assume a is not 0. Divide every term by a. X squared plus b over a times x plus c over a equals 0. Move the constant term. X squared plus b over a times x equals -c over a. Now complete the square. Half of b over a is b over 2a. Square it. B squared over 4a squared. Add this quantity to both sides. The left side becomes a perfect square. Open parenthesis x plus b over 2a, close parenthesis squared. The right side becomes -c over a plus b squared over 4a squared. Rewrite the first fraction with denominator 4a squared. -c over a becomes -4ac over 4a squared. Combine. The right side is b squared minus 4ac over 4a squared. Take square roots. X plus b over 2a equals plus or minus the square root of b squared minus 4ac, divided by 2a. Then subtract b over 2a. X equals -b plus or minus the square root of b squared minus 4ac, all divided by 2a. This is the quadratic formula. It solves every quadratic equation with real or complex coefficients in the usual setting. For ax squared plus bx plus c equals 0, identify a, b, and c carefully, then substitute them into the formula. The entire numerator is -b plus or minus the square root. The entire numerator is divided by 2a. Parentheses help preserve the structure. Consider 2x squared plus 3x minus 2 equals 0. Here, a equals 2, b equals 3, c equals -2. Substitute. X equals -3 plus or minus the square root of 3 squared, minus 4 times 2 times -2, all divided by 4. Simplify inside the square root. 3 squared is 9. 4 times 2 times -2 is -16. Subtracting -16 becomes adding 16. 9 plus 16 is 25. The square root of 25 is 5. So x equals -3 plus or minus 5, divided by 4. Create two solutions. -3 plus 5 is 2. 2 divided by 4 is 1/2. -3 minus 5 is -8. -8 divided by 4 is -2. The solutions are 1/2 and -2. Check by factoring. 2x squared plus 3x minus 2 factors into open parenthesis. 2x minus 1 close parenthesis times open parenthesis x plus 2 close parenthesis. The zeros are 1/2 and -2. Both methods agree. The expression inside the square root of the quadratic formula is called the discriminant. It is b squared minus 4ac. The discriminant tells us how many real solutions a quadratic has. If the discriminant is positive, its square root is a positive real number. The plus or minus sign produces two distinct real solutions. If the discriminant is 0, the square root is 0. Adding or subtracting 0 gives the same answer. There is one repeated real solution. If the discriminant is negative, the square root is not a real number. There are no real solutions. Instead, there are two complex solutions. Consider x squared minus 5x plus 6 equals 0. A equals 1, b equals negative 5, c equals 6. The discriminant is negative 5 squared minus 4 times 1 times 6. 25 minus 24 equals 1. Positive. So there are two distinct real roots. They are 2 and 3. Now consider x squared plus 6x plus 9 equals 0. The discriminant is 36 minus 36. 0. So there is one repeated real solution. X equals negative 3. Now consider x squared plus x plus 1 equals 0. The discriminant is 1 minus 4. That is negative 3. Negative. So there are no real roots. The graph does not cross the x-axis. The discriminant connects algebra and geometry. Positive means the parabola crosses the x-axis twice. 0 means it touches once. Negative means it never reaches the axis. The sign of the discriminant tells us how the graph and axis relate. Complex numbers allow negative discriminants to produce solutions. The imaginary unit I is defined by I squared equals negative 1. The square root of negative 1 is written as I. The square root of negative 4 becomes 2i. The square root of negative 9 becomes 3i. More generally, the square root of negative a can be written as I times the square root of a, when a is positive. Consider x squared plus 1 equals 0. X squared equals negative 1. So x equals plus or minus I. Consider x squared plus 4 equals 0. X squared equals negative 4. So x equals plus or minus 2i. A complex number has the form a plus bi. The number a is called the real part. The number b is the coefficient of the imaginary part. Examples include 3 plus 2i, negative 5 minus I, and 4, which can be written as 4 plus 0i. Real numbers are therefore part of the complex number system. An imaginary number such as 3i can be written as 0 plus 3i. Complex numbers extend the number line into a plane. The horizontal axis represents the real part. The vertical axis represents the imaginary part. The number 3 plus 2i corresponds to the point 3, 2. This does not make the number unreal or imaginary in the ordinary sense. The name is historical. Complex numbers have precise mathematical behavior and appear in physics, engineering, signal analysis, electronics, and many other areas. Addition of complex numbers combines real parts and imaginary parts separately. 3 plus 2i added to 5 minus I becomes 8 plus I. 3 plus 5 is 8. 2i minus I is I. Subtraction follows the same pattern. Multiplication uses distribution, and the fact that I squared equals negative 1. Consider open parenthesis 2 plus I, close parenthesis times open parenthesis 3 minus I, close parenthesis. Distribute. 2 times 3 is 6. 2 times negative I is negative 2i. I times 3 is 3i. I times negative I is negative I squared. Since I squared equals negative 1, negative I squared equals positive 1. Combine. 6 plus 1 is 7. Negative 2i plus 3i is positive I. The result is 7 plus I. Complex conjugates help simplify division. The conjugate of a plus bi is a minus bi. Multiplying conjugates removes the imaginary middle terms. Open parenthesis a plus bi, close parenthesis, times open parenthesis a minus bi, close parenthesis becomes a squared plus b squared. The product is real. For example, open parenthesis 3 plus 2i, close parenthesis, times open parenthesis 3 minus 2i, close parenthesis equals 9 plus 4. The result is 13. This is similar to a difference of squares pattern, but I squared changes the final sign. Complex roots of real coefficient quadratics appear in conjugate pairs. If 3 plus 2i is a root, 3 minus 2i is also a root. The symmetry comes from the real coefficients. Consider x squared minus 2x plus 5 equals 0. A equals 1. B equals negative 2. C equals 5. The discriminant is 4 minus 20, negative 16. Use the quadratic formula. X equals 2 plus or minus square root of negative 16, divided by 2. The square root of negative 16 is 4i, so x equals 2 plus or minus 4i, divided by 2. The solutions are 1 plus 2i and 1 minus 2i. They form a conjugate pair. Even when the graph has no real x-intercepts, the algebraic equation still has roots in the complex number system. The fundamental theorem of algebra states that a polynomial of degree n has exactly n complex roots when multiplicity is counted. A quadratic has 2, a cubic has 3, a fourth-degree polynomial has 4. Some roots may repeat, some may be real, others may be complex. The theorem gives polynomials a complete solution structure within the complex numbers. For a quadratic, the roots are revealed by factoring, or the quadratic formula. For higher-degree polynomials, methods may become more complicated. Some polynomials factor through patterns, some require numerical approximations, some have formulas that are far less convenient than the quadratic formula. Graphing helps locate real roots. The roots of a polynomial are the x-values where its graph crosses or touches the x-axis. Consider f of x equals x cubed minus 4x. Factor x times open parenthesis, x squared minus 4 close parenthesis. Then factor the difference of squares. X times open parenthesis, x minus 2 close parenthesis, times open parenthesis, x plus 2 close parenthesis. The roots are 0, 2 and negative 2. The cubic graph crosses the x-axis at all 3 points. Each factor creates one root. The multiplicity of a root tells us how many times its factor repeats. Consider f of x equals open parenthesis, x minus 1 close parenthesis, squared, times open parenthesis, x plus 2 close parenthesis. The root x equals 1 has multiplicity 2. The factor repeats twice. The root x equals negative 2 has multiplicity 1. At a root with odd multiplicity, the graph usually crosses the x-axis. At a root with even multiplicity, the graph usually touches the axis and turns. So the graph crosses at negative 2. It touches at 1. The repeated factor affects the shape near the intercept. A root with multiplicity 3 crosses but often flattens as it passes. Higher multiplicities create increasingly flat behavior near the root. The factor structure tells us more than the location of zeros. It hints at how the graph behaves there. The leading term controls the graph's end behavior. For a polynomial with large positive or negative x-values, the highest degree term dominates. Lower degree terms become relatively less important. Consider f of x equals 2x cubed minus 5x plus 1. For very large absolute values of x, the 2x cubed term controls the general direction. The degree is odd. The leading coefficient is positive. As x moves far to the right, the graph rises. As x moves far to the left, the graph falls. For an even degree polynomial with positive leading coefficient, both ends rise. The graph of x squared is the simplest example. For an even degree with negative leading coefficient, both ends fall. For an odd degree with negative leading coefficient, the left end rises and the right end falls. These patterns help sketch a graph before every detail is known. Degree suggests the broad shape. Factors reveal zeros. Multiplicity reveals crossing or touching. The y-intercept comes from substituting 0. Turning points appear between regions of increase and decrease. A polynomial of degree n can have at most n real roots. It can have at most n-1 turning points. A quadratic has at most 2 real roots and 1 turning point. A cubic has at most 3 real roots and 2 turning points. The graph may have fewer. The degree creates a maximum, not a guarantee. Polynomial division allows one polynomial to be divided by another. The process resembles long division with numbers. Consider x squared plus 5x plus 6 divided by x plus 2. Because the numerator factors as open parenthesis, x plus 2 close parenthesis, times open parenthesis, x plus 3 close parenthesis. The quotient is x plus 3, provided x is not negative 2 in the original rational expression. But division can also be performed without knowing the factors beforehand. Divide the leading term x squared by x. The result is x. Place x in the quotient. Multiply x by x plus 2. This gives x squared plus 2x. Subtract from the original polynomial. 3x plus 6 remains. Divide 3x by x. The result is 3. Multiply 3 by x plus 2. 3x plus 6. Subtract. The remainder is 0. So the quotient is x plus 3. If a remainder remains, the result includes a fraction. The polynomial division algorithm states that a dividend equals divisor times quotient plus remainder. The remainder has lower degree than the divisor. Synthetic division is a shorter method when dividing by a linear factor, such as x minus r. It uses only coefficients. The method can quickly test whether a number is a root. The remainder theorem says that when a polynomial f of x is divided by x minus r, the remainder is f of r. If f of r equals 0, the remainder is 0. Then x minus r is a factor. This is the factor theorem. A number r is a root exactly when x minus r is a factor. Consider f of x equals x cubed minus 6x squared plus 11x minus 6. Test x equals 1. F of 1 is 1 minus 6 plus 11 minus 6. That equals 0. So x minus 1 is a factor. Divide the polynomial by x minus 1. The quotient becomes x squared minus 5x plus 6. Factor the quotient. Open parenthesis. X minus 2 close parenthesis times open parenthesis x minus 3 close parenthesis. The full factorization is open parenthesis x minus 1 close parenthesis times open parenthesis x minus 2 close parenthesis times open parenthesis x minus 3 close parenthesis. A higher degree polynomial can sometimes be solved by finding one root, dividing out its factor, and solving the simpler polynomial that remains. Possible rational roots can be suggested by the rational root theorem. For a polynomial with integer coefficients, a rational root written in simplest form has a numerator that divides the constant term and a denominator that divides the leading coefficient. This creates a finite list of candidates. The theorem does not guarantee that any candidate works. It tells us which rational values are worth testing. For x cubed minus 6x squared plus 11x minus 6, the possible integer roots divide 6. Positive or negative 1, 2, 3, and 6. Testing reveals 1, 2, and 3. For many polynomials, graphing or numerical methods are more efficient. Exact factoring may not be available. Algebra includes both symbolic and approximate solutions. An exact answer may contain radicals. A numerical answer may be expressed as a decimal. Each form serves a purpose. Exact values preserve complete mathematical information. Approximations help with measurement and practical comparison. The quadratic formula may produce square roots that do not simplify. Consider x squared minus 2 equals 0. The solutions are plus or minus square root of 2. This is exact. Square root of 2 is approximately 1.414. The decimal continues without repeating. The approximate roots are about positive 1.414 and negative 1.414. The exact form remains preferable during algebraic work. Rounding too early can create accumulated error. Use exact values until a decimal is needed. Quadratic equations also appear in physical and geometric situations. Suppose a rectangle has length x plus 3 and width x. Its area is 40. The equation is x times open parenthesis x plus 3 close parenthesis equals 40. Expand. X squared plus 3x equals 40. Move everything to one side. X squared plus 3x minus 40 equals 0. Factor. We need numbers that multiply to negative 40 and add to 3, 8, and negative 5. So open parenthesis, x plus 8, close parenthesis, times open parenthesis, x minus 5 close parenthesis equals 0. The algebraic solutions are x equals negative 8, or x equals 5. But x represents a width. A negative width does not fit the physical context. So the meaningful solution is x equals 5. The rectangle's width is 5. Its length is 8. The area is 40. The rejected solution is mathematically valid for the equation. It is not valid for the geometry. Context filters the solution set. Projectile motion often produces quadratics. An object thrown upward may have a height modeled by a downward opening parabola. The vertex represents maximum height. The roots may represent moments when the object reaches ground level. One root may occur at launch, another at landing. The axis of symmetry gives the time halfway between these events. The negative leading coefficient reflects the downward acceleration. The mathematics describes a rise, a peak, and a fall. Revenue or profit models may also be quadratic. A parabola's maximum or minimum can identify an optimal price, dimension, or production amount within a simplified model. The vertex becomes practically important. For y equals ax squared plus bx plus c, the vertex occurs at x equals negative b over 2a. If a is positive, the vertex is a minimum. If a is negative, it is a maximum. Consider the function p of x equals negative 2x squared plus 40x minus 100. The leading coefficient is negative. The parabola opens downward. The vertex gives the maximum. The x-coordinate is negative 40 divided by 2 times negative 2. That becomes negative 40 divided by negative 4. The result is 10. Substitute x equals 10. Negative 2 times 100 plus 400 minus 100. That is 100. So the maximum output is 100 when x equals 10. The meaning depends upon the model. Perhaps x represents quantity, perhaps price, perhaps time. The algebra locates the peak. A model should still be interpreted carefully. Real situations may not follow a perfect parabola outside a limited range. Negative production values may be meaningless. Extremely large inputs may violate assumptions. The mathematical function can extend indefinitely. The practical domain may be smaller. This distinction between algebraic domain and contextual domain remains important. Quadratics can be solved through several methods. Factoring is efficient when the factors are visible. Square root methods work when one squared expression is isolated. Completing the square works systematically and reveals vertex form. The quadratic formula works for every quadratic equation. Graphing provides approximate roots and visual meaning. No single method is always best. Consider x squared equals 49. Taking square roots is immediate. X equals plus or minus 7. Factoring would also work. X squared minus 49 equals 0. Difference of squares, open parenthesis, x minus 7, close parenthesis times open parenthesis, x plus 7, close parenthesis equals 0. But the square root method is shorter. Consider x squared minus 9x plus 20 equals 0. Factoring is quick. The factors are x minus 4 and x minus 5. The roots are 4 and 5. The quadratic formula would work but require more arithmetic. Consider x squared plus 4x minus 1 equals 0. Integer factoring is not available. Completing the square is natural, or use the quadratic formula. Both produce negative 2 plus or minus square root of 5. The best method depends upon the structure. A useful first step is always to place the quadratic equation in standard form. ax squared plus bx plus c equals 0. Factoring and the zero product property requires 0 on one side. The quadratic formula requires correct identification of a, b, and c. Missing terms should be represented by zero coefficients. Consider x squared minus 9 equals 0. Here, a equals 1, b equals 0, c equals negative 9. The x term is missing, but b is still 0. Consider 3x squared plus 2x equals 0, c equals 0. This structure suggests factoring out x times open parenthesis, 3x plus 2 close parenthesis equals 0. The solutions are x equals 0 and x equals negative 2/3. Using the quadratic formula also works. But factoring immediately reveals the 0 root. Careful identification prevents sign errors. In 2x squared minus 5x minus 3 equals 0. b is negative 5, c is negative 3. When substituted into the quadratic formula, negative b becomes positive 5. The discriminant contains negative 5 squared, which is positive 25. The signs must be preserved with parentheses. Writing them clearly keeps the formula reliable. Graphing and solving are two views of the same problem. The equation f of x equals 0 asks where the graph reaches the x-axis. The factors tell us the intercepts. The discriminant tells us how many real intercepts exist. The vertex tells us the turning point. The leading coefficient tells us whether the graph opens upward or downward. The standard form tells us the y-intercept. The different pieces of algebra describe different parts of one shape. This unity is one reason quadratics are so important. They connect expressions, equations, factoring, functions, graphs, geometry, and physical models. A long quadratic problem becomes calmer when each feature is considered separately. What are a, b, and c? Can a common factor be removed? Does the expression match a special pattern? Can it factor? Is one squared quantity isolated? Would completing the square reveal the vertex? Would the quadratic formula be more direct? How many real roots should the discriminant predict? Do the solutions fit the original context? Every question narrows the path. There is no need to force one method. The algebra offers several. When factoring, multiply the factors back to check. When using the quadratic formula, verify the signs. When completing the square, add the same amount to both sides. When taking square roots, remember both signs. When interpreting a graph, distinguish crossing from touching. When working in a real situation, reject values that violate physical restrictions. The process becomes reliable through these quiet checks. Polynomials may appear to be long collections of powers, but they are built from the same ideas already explored. Terms, coefficients, like terms, distribution, factors, zeros, functions. A polynomial can be expanded, factored, evaluated, graphed, divided, or solved when set equal to 0. Each operation reveals another part of its structure. A quadratic is simply the first polynomial whose graph bends. The line from earlier parts changes at a constant rate. The quadratic changes its rate steadily. Its graph curves into a parabola. It may cross the axis twice, touch once, or remain entirely above or below it. Its roots may be rational, irrational, repeated, or complex. The equation may look different in standard, factored, or vertex form. Yet every form describes the same relationship. As the symbols become familiar, the parabola becomes less mysterious. A squared term creates the curve. The factors locate the zeros. The axis divides the graph symmetrically. The vertex marks the highest or lowest point. The discriminant predicts contact with the axis, and the quadratic formula provides a path when no simpler factorization appears. In the final part, we will move gently through radicals, rational expressions, exponentials, logarithms, sequences, and the larger idea that algebra is a language for patterns rather than a collection of disconnected rules. Radicals, rational expressions, exponentials, and logarithms may appear to belong to completely different areas of algebra. One contains square root symbols, another contains variables inside fractions, another places the variable in an exponent, and another introduces a word that sounds unfamiliar: logarithm. But these ideas are connected by one quiet principle. Every algebraic operation has an inverse. Addition is undone by subtraction. Multiplication is undone by division. Squaring is undone by taking a square root. Exponentiation is undone by a logarithm. Much of algebra consists of recognizing an operation and learning how to reverse it carefully. Begin with radicals. A radical is an expression containing a root. The most familiar is the square root. The square root of 9 is 3, because 3 squared equals 9. The square root asks which non-negative number produces the given value when multiplied by itself. The principal square root of 9 is positive 3. This is why the square root symbol by itself represents the non-negative root. But the equation x squared equals 9 has two solutions: positive 3 and negative 3. Both numbers produce 9 when squared. The distinction is important. The square root of 9 is 3. But solving x squared equals 9 gives x equals plus or minus 3. The square root symbol represents one principal value. An equation involving a square may require two possible signs. The square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 16 is 4. These are perfect squares. Their square roots are whole numbers. Other numbers do not have whole number square roots. The square root of 2 is irrational. Its decimal continues without ending or repeating. The square root of 3 is also irrational. So is the square root of 5. These values are still exact numbers. The radical notation preserves their exact form. A calculator may display an approximation. The symbol keeps the full value. Radicals can often be simplified by separating perfect square factors. Consider the square root of 12. 12 can be written as 4 times 3. The square root of 4 times 3 can be separated into the square root of 4 times the square root of 3. The square root of 4 is 2. So the square root of 12 simplifies to 2 square roots of 3. The value has not changed. The perfect square factor has been removed from the radical. Now consider the square root of 72. 72 contains the perfect square factor 36. 72 is 36 times 2. The square root becomes 6 square roots of 2. We could also factor 72 as 9 times 8. That path eventually reaches the same result. Using the largest perfect square factor may shorten the work. The square root of 50 becomes 5 square roots of 2, because 50 is 25 times 2. The square root of 48 becomes 4 square roots of 3, because 48 is 16 times 3. Simplification stops when no perfect square factor remains inside the radical. Variables can be simplified in the same way, but signs and assumptions matter. The square root of x squared is not always simply x. The result is the absolute value of x. This is because the principal square root must be non-negative. If x is positive, the square root of x squared is x. If x is negative, x squared is positive, and its principal square root is negative x. For example, let x equal negative 5, x squared is 25. The square root of 25 is positive 5. That is not equal to negative 5. It equals the absolute value of negative 5. So the general identity is the square root of x squared equals the absolute value of x. In many introductory problems, a variable may be assumed positive. Then the absolute value notation is sometimes omitted. But the assumption should be understood. The square root of x to the fourth power simplifies to x squared. X squared is already non-negative for real x. The square root of x to the sixth power simplifies to the absolute value of x cubed. Whether absolute value is needed depends upon whether the remaining expression can be negative. Even powers are non-negative. Odd powers may preserve the sign of x. Cube roots behave differently. The cube root of 8 is 2 because 2 cubed is 8. The cube root of negative 8 is negative 2 because negative 2 cubed is negative 8. Odd roots can accept negative inputs within the real numbers. Even roots cannot. There is no real square root of negative 9. But there is a real cube root of negative 8. The difference comes from powers. An even power removes the sign. A negative number squared becomes positive. An odd power preserves the sign. A negative number cubed remains negative. The index of a radical tells us which root is being taken. A small 3 indicates cube root. A small 4 indicates fourth root. When no index is shown, the radical means square root. The index 2 is understood but not written. The nth root of a number asks which value raised to the nth power produces that number. Radicals can be rewritten using fractional exponents. The square root of x equals x raised to the 1/2 power. The cube root of x equals x raised to the 1/3 power. The fourth root of x equals x raised to the 1/4 power. More generally, the nth root of x equals x raised to the power 1 over n. This connects roots with exponent laws. X raised to the 3/2 power can be interpreted in two related ways. Take the square root of x, then cube the result. Or cube x, then take the square root. For non-negative real x, both approaches agree. The denominator of the fractional exponent gives the root. The numerator gives the power. X raised to the power m over n means the nth root of x raised to the m power. Fractional exponents are not separate from radicals. They are another notation for the same operation. Negative fractional exponents add the reciprocal rule. X raised to negative 1/2 equals 1 divided by the square root of x. X raised to negative 3/2 equals 1 divided by x raised to 3/2. The negative exponent creates a reciprocal. The fractional part creates a root. The usual exponent laws continue to operate, provided the expressions are defined. Radical expressions can be added only when they contain matching radical parts. 2 square roots of 3 plus 5 square roots of 3 becomes 7 square roots of 3. The square root of 3 acts like a shared variable factor. The coefficients combine, but 2 square roots of 3 plus 5 square roots of 2 cannot combine. The radical parts differ. They are unlike terms. Sometimes radicals must first be simplified before like terms appear. Consider the square root of 12 plus the square root of 27. The square root of 12 becomes 2 square roots of 3. The square root of 27 becomes 3 square roots of 3. Now the terms match. 2 square roots of 3 plus 3 square roots of 3 becomes 5 square roots of 3. Without simplifying first, the relationship is hidden. Multiplying radicals can be more direct. The square root of 2 times the square root of 8 equals the square root of 16. That is 4. Or simplify the square root of 8 first. 2 square roots of 2. Then square root of 2 times 2 square roots of 2 gives 2 times 2. Again, the result is 4. For non-negative real quantities, the product of square roots can be combined beneath one radical. But addition does not follow that rule. The square root of a plus the square root of b is not generally equal to the square root of a plus b. For example, the square root of 9 plus the square root of 16 is 3 plus 4. That equals 7. The square root of 25 is 5. The values differ. Radical multiplication and radical addition follow different structures. Expressions such as the square root of a plus b cannot usually be separated. The radical applies to the entire sum. Just as exponents do not distribute across addition, roots do not generally distribute across addition. The grouping beneath the radical must be respected. A radical equation contains a variable inside a root. Consider the square root of x equals 5. Square both sides. X equals 25. Check. The square root of 25 is 5. The solution works. Now consider the square root of x plus 3 equals 7, where the entire quantity x plus 3 lies inside the radical. Square both sides. X plus 3 equals 49. Subtract 3. X equals 46. Check. 46 plus 3 is 49. The square root is 7. The solution works, but squaring can introduce extraneous solutions. Consider the square root of x plus 2 equals x, with x plus 2 inside the radical. The right side must be non-negative because the left side is a principal square root, so any solution must satisfy x greater than or equal to 0. Square both sides. X plus 2 equals x squared. Move everything to one side. X squared minus x minus 2 equals 0. Factor. Open parenthesis. X minus 2 close parenthesis times open parenthesis x plus 1 close parenthesis equals 0. The candidate solutions are 2 and negative 1. Check. X equals 2. The square root of 4 is 2. It works. Check. X equals negative 1. The square root of 1 is positive 1. That does not equal negative 1. So negative 1 is extraneous. It appeared because squaring erased the sign difference between 1 and negative 1. Every solution to the original equation solves the squared equation, but not every solution to the squared equation solves the original. Checking is necessary. If an equation contains two radicals, one may need to be isolated and squared more than once. Each squaring step may introduce additional candidates. The final check in the original equation becomes even more important. The goal is not merely to solve the transformed equation. It is to identify values that satisfy the starting relationship. Rational expressions are algebraic fractions. They contain polynomials or other algebraic expressions in the numerator, denominator, or both. Examples include 1 over x, x plus 2 over x minus 3, and x squared minus 9 over x plus 3. They follow the same rules as numerical fractions, but they also carry domain restrictions. Any value that makes the denominator 0 must be excluded. Consider 1 over x minus 4. With the denominator x minus 4, the denominator becomes 0 when x equals 4, so 4 is excluded from the domain. The expression exists for every other real value. Consider x plus 1 over x squared minus 9. Factor the denominator. X squared minus 9 becomes open parenthesis x minus 3 close parenthesis times open parenthesis x plus 3 close parenthesis. The denominator is 0 at 3 and negative 3. Both values are excluded. Finding restrictions is often easier after factoring. Rational expressions can be simplified by cancelling common factors. Consider x squared minus 9 over x plus 3. Factor the numerator. Open parenthesis x minus 3 close parenthesis times open parenthesis x plus 3 close parenthesis divided by x plus 3. The common factor x plus 3 cancels. The simplified expression is x minus 3. But the original expression excluded x equals negative 3, so the simplified form agrees with the original only when x is not negative 3. The graph of the original rational function resembles the line y equals x minus 3, except for one missing point. At x equals negative 3, the line would have y equal negative 6, but the original function is undefined there. The graph contains a hole. Simplification removed the visible factor. It did not restore the forbidden input. This is why domain restrictions must be recorded before cancelling. A common factor can cancel. A common term cannot. Consider x plus 3 over x. The x cannot cancel because the numerator is a sum. The expression may be separated instead. X over x plus 3 over x. This becomes 1 plus 3 over x, provided x is not 0. The original expression and the separated form are equivalent on the same domain. Now consider x times open parenthesis x plus 3 close parenthesis over x. Here, x is a factor of the entire numerator. It can cancel. The result is x plus 3, with x still restricted from 0. The difference lies between addition and multiplication. Terms separated by addition do not cancel. Factors joined by multiplication may cancel. Multiplying rational expressions involves factoring and cancelling common factors. Consider x over x minus 2 times x minus 2 over 3. The factor x minus 2 cancels. The result is x over 3. But x cannot equal 2, because the original denominator contained x minus 2. Now consider x squared minus 4 over x squared plus 3, x plus 2, multiplied by x plus 1 over x minus 2. Factor each polynomial. X squared minus 4 becomes open parenthesis x minus 2 close parenthesis times open parenthesis x plus 2 close parenthesis. X squared plus 3x plus 2 becomes open parenthesis x plus 1 close parenthesis times open parenthesis x plus 2 close parenthesis. The full product contains several common factors. X plus 2 cancels. X plus 1 cancels. X minus 2 cancels with the denominator factor in the second fraction. The simplified result is 1. But the original restrictions remain. X cannot equal -1, -2, or +2. At every other allowed value, the original product equals 1. Factoring reveals the cancellations. Division of rational expressions uses reciprocals. To divide by a fraction, multiply by its reciprocal. X over 3 divided by x plus 2 over 5 becomes x over 3 times 5 over x plus 2. The result is 5x over 3 times open parenthesis, x plus 2 close parenthesis. Restrictions come from every original denominator. X plus 2 cannot equal 0, so x cannot equal -2. The divisor itself also cannot equal 0. The fraction x plus 2 over 5 becomes 0 when x equals -2. The same value is already excluded because division by 0 would occur. In more complicated problems, values that make the divisor's numerator 0 must also be excluded. Adding rational expressions requires a common denominator. Consider 1 over x plus 1 over 3. The common denominator is 3x. 1 over x becomes 3 over 3x. 1 over 3 becomes x over 3x. The sum is x plus 3 over 3x. The restriction is x not equal to 0. Now consider 2 over x minus 1 plus 3 over x plus 2. The denominators are different. A common denominator is open parenthesis, x minus 1, close parenthesis, times open parenthesis, x plus 2 close parenthesis. Multiply the first numerator by x plus 2. Multiply the second numerator by x minus 1. The combined numerator becomes 2 times open parenthesis, x plus 2 close parenthesis, plus 3 times open parenthesis, x minus 1 close parenthesis. Expand, 2x plus 4 plus 3x minus 3. Combine like terms, 5x plus 1. The result is 5x plus 1 over open parenthesis x minus 1 close parenthesis times open parenthesis x plus 2 close parenthesis. The restrictions are x not equal to 1 and x not equal to -2. The denominator remains factored unless expansion serves a particular purpose. A factored denominator makes restrictions and common factors easier to see. Rational equations can often be solved by multiplying every term by the least common denominator. Consider 1 over x plus 1/2 equals 1. The denominator restrictions require x not equal to 0. The least common denominator is 2x. Multiply every term by 2x. The first term becomes 2. The second becomes x. The right side becomes 2x. So 2 plus x equals 2x. Subtract x. X equals 2. Check. 1/2 plus 1/2 equals 1. The solution works. Now consider 1 over x minus 2 plus 1 over x equals 1, with x minus 2 as one denominator. The restrictions are x not equal to 2 and x not equal to 0. The least common denominator is x times open parenthesis x minus 2 close parenthesis. Multiply every term. The first fraction becomes x. The second becomes x minus 2. The right side becomes x times open parenthesis x minus 2 close parenthesis. So x plus x minus 2 equals x squared minus 2x. Combine and rearrange. 2x minus 2 equals x squared minus 2x. Move everything to one side. 0 equals x squared minus 4x plus 2. This quadratic does not factor neatly over integers. Use the quadratic formula. X equals 4 plus or minus the square root of 16 minus 8 divided by 2. The square root becomes the square root of 8. That simplifies to 2 square roots of 2. So x equals 2 plus or minus the square root of 2. Neither candidate is 0 or 2. Both satisfy the domain restrictions. They should still be checked in the original equation. Multiplying by variable expressions can sometimes produce candidates that make an original denominator 0. Those values must be rejected. Rational functions often have asymptotes. An asymptote is a line that a graph approaches. A vertical asymptote commonly appears where a denominator becomes 0, and the factor does not cancel. Consider f of x equals 1 over x. The denominator is 0 at x equals 0. The y-axis, x equals 0, is a vertical asymptote. As x approaches 0 from the positive side, 1 over x grows very large and positive. As x approaches 0 from the negative side, the output grows very large and negative. The graph approaches the y-axis but never touches it. The x-axis is a horizontal asymptote. As x becomes very large in either direction, 1 over x approaches 0. It becomes closer and closer to 0 without becoming 0. The graph approaches y equals 0. Asymptotes describe long-term or near-boundary behavior. They are not always barriers the graph can never cross in every context. A rational function may cross a horizontal or slant asymptote, but it cannot take a value at a true vertical asymptote, where the original expression is undefined. The degrees of the numerator and denominator help determine horizontal behavior. If the numerator's degree is lower than the denominator's degree, the horizontal asymptote is often y equals 0. If the degrees are equal, the horizontal asymptote is the ratio of the leading coefficients. For example, 2x squared plus 1 over 5x squared minus 3 approaches 2/5 as x becomes very large in magnitude. The lower degree terms become relatively insignificant. The leading terms dominate. If the numerator's degree is exactly 1 greater than the denominator's degree, polynomial division may reveal a slant asymptote. The function approaches a line rather than a constant. This continues the larger algebraic idea that the highest powers control long-term behavior. Exponentials place the variable in the exponent. A basic exponential function has the form b raised to the x power, where b is positive and not equal to 1. Consider 2 to the x. When x equals 0, the output is 1. When x equals 1, the output is 2. When x equals 2, the output is 4. When x equals 3, the output is 8. Each increase of 1 in x multiplies the output by 2. This is different from a linear function. A linear function adds a constant amount for equal input steps. An exponential function multiplies by a constant factor. For y equals 3x, increasing x by 1 adds 3 to y. For y equals 3 to the x, increasing x by 1 multiplies y by 3. At x equals 0, 3x is 0, but 3 to the 0 power is 1. The placement of x changes the entire type of function. Exponential growth occurs when the base is greater than 1. 2 to the x grows. 3 to the x grows faster. 10 to the x grows faster still. The graph passes through 0, 1 because every Tunguo base raised to 0 equals 1. The outputs remain positive. The x-axis is a horizontal asymptote. As x moves far into negative values, b to the x becomes a very small positive fraction. It approaches 0 without reaching it. Exponential decay occurs when the base lies between 0 and 1. Consider 1/2 raised to the x. At x equals 0, the output is 1. At x equals 1, it is 1/2. At x equals 2, 1/4. At x equals 3, 1/8. Each increase of 1 multiplies the output by 1/2. The function decreases towards 0. The outputs remain positive. Growth and decay are determined by repeated multiplication. Exponential models appear whenever a quantity changes by the same percentage or factor over equal intervals. Population growth, compound interest, radioactive decay, cooling approximations, spread of information, and depreciation may all use exponential models under appropriate assumptions. Suppose a population begins at 100 and doubles every year. After t years, the model is 100 times 2 to the t power. At t equals 0, the population is 100. After 1 year, 200. After 2 years, 400. After 3, 800. The amount added each year is not constant, the multiplying factor is constant. This distinction separates exponential growth from linear growth. Compound interest is exponential because interest is added to the current balance. Then future interest is calculated on the larger balance. If an initial amount P grows at rate R per period, the balance after T periods may be written as P times open parenthesis 1 plus R close parenthesis raised to T. For a decrease, the factor may be 1 minus R. A 5% increase corresponds to multiplying by 1.05. A 5% decrease corresponds to multiplying by 0.95. The percentage must be converted to decimal form. Repeated percentage change compounds. A 10% increase followed by a 10% decrease does not return to the starting value. Suppose a quantity begins at 100, increase by 10%. The result is 110. Then decrease that new amount by 10%. 10% of 110 is 11. The result is 99. The changes were applied to different bases. Percentages are multiplicative. Equal percentage changes in opposite directions do not generally cancel. Exponential equations can sometimes be solved by rewriting both sides with the same base. Consider 2 to the x equals 8. 8 is 2 cubed, so 2 to the x equals 2 cubed. The exponents must match. X equals 3. Consider 3 raised to 2x minus 1 equals 27. 27 is 3 cubed, so 2x minus 1 equals 3. Add 1. 2x equals 4. X equals 2. The method works because exponential functions with the same valid base are one-to-one. Equal outputs require equal exponents, but many exponential equations cannot be rewritten with a convenient common base. Consider 2 to the x equals 10. 10 is not an integer power of 2. The solution lies between 3 and 4, because 2 cubed is 8 and 2 to the 4th is 16. To find an exact expression, we use logarithms. A logarithm asks a question about an exponent. The logarithm base 2 of 8 equals 3 because 2 cubed equals 8. The statement log base 2 of 8 equals 3 is exactly equivalent to 2 cubed equals 8. The logarithm is the exponent. It tells us which power of the base produces the given number. Log base 10 of 100 equals 2 because 10 squared is 100. Log base 10 of 1000 equals 3. Log base 10 of 1/10 equals -1 because 10 to the negative first power is 1/10. Log base 3 of 1 equals 0 because 3 to the 0 power is 1. The base must be positive and cannot equal 1. The logarithm's argument must be positive within the real numbers. There is no real logarithm of 0. No positive base raised to a real power produces 0. There is also no real logarithm of a negative number under the ordinary real logarithm system. Exponential functions produce positive outputs. Their inverses accept positive inputs. Logarithms undo exponentials. If b raised to x equals y, then log base b of y equals x. These are two forms of the same relationship. The exponential form emphasizes the power. The logarithmic form isolates the exponent. To solve 2 to the x equals 10, take logarithms. X equals log base 2 of 10. A calculator may approximate this as about 3.322. Another method uses common or natural logarithms. Take the logarithm of both sides. Log of 2 to the x equals log of 10. Use the power rule. X log of 2 equals log of 10. Divide by log of 2. X equals log of 10 divided by log of 2. This is the change of base formula. It allows a logarithm in any base to be calculated using a standard logarithm key. Common logarithms use base 10. Natural logarithms use a special base called e. The number e is approximately 2.718. It appears naturally in continuous growth, calculus, probability, and differential equations. The natural logarithm is written as ln. It is the inverse of e raised to x. ln of e to the x equals x, and e raised to ln of x equals x for positive x. The base e may initially seem arbitrary, but it arises when growth is compounded continuously and in many natural rate processes. For basic algebra, it behaves like any other valid exponential base. Logarithms follow laws connected to exponent laws. The logarithm of a product becomes a sum. Log base b of mn equals log base b of m plus log base b of n. This works because multiplying powers with the same base adds exponents. If m equals b to the p and n equals b to the q, then mn equals b to the p plus q. So the exponent needed to produce the product is the sum of the individual exponents. The logarithm of a quotient becomes a difference. Log base b of m divided by n equals log base b of m minus log base b of n. Dividing powers subtracts exponents. The logarithm of a power brings the exponent forward. Log base b of m raised to k equals k times log base b of m. Raising a power to another power multiplies exponents. The logarithm laws are not unrelated new rules. They are exponent laws read through the inverse operation, but logarithms do not distribute across addition. Log of m plus n is not generally log m plus log n. The product rule applies to multiplication, not addition. This resembles earlier cautions. Exponents do not distribute across sums. Radicals do not separate across sums. Cancellation does not cross addition. The operation between terms determines which rule is valid. Logarithmic equations require attention to domain. Consider log base 2 of x equals 3. Convert to exponential form. X equals 2 cubed. X equals 8. The argument is positive, so the solution is valid. Now consider log base 10 of open parenthesis x minus 1, close parenthesis equals 2. Convert. X minus 1 equals 10 squared. X minus 1 equals 100. X equals 101. The argument x minus 1 is positive. The solution is valid. Now consider log of x plus log of x minus 9 equals 1, where the second argument is x minus 9. Both arguments must be positive, so x must be greater than 9. Use the product rule. Log of x times open parenthesis x minus 9 close parenthesis equals 1. Assuming common logarithm, convert to exponential form. X times open parenthesis x minus 9 close parenthesis equals 10. Expand. X squared minus 9x minus 10 equals 0. Factor. Open parenthesis x minus 10 close parenthesis times open parenthesis x plus 1 close parenthesis equals 0. The candidates are 10 and negative 1. But the domain requires x greater than 9, so only x equals 10 remains. Check. Log of 10 is 1. Log of 1 is 0. The sum is 1. The solution works. The negative candidate arose from the quadratic. It is not allowed in the original logarithmic expressions. Domain checks are essential. Exponential and logarithmic graphs are reflections of one another across the line. Y equals x, because the functions are inverses. The exponential graph passes through 0, 1. The logarithmic graph passes through 1, 0. The exponential graph has a horizontal asymptote at y equals 0. The logarithmic graph has a vertical asymptote at x equals 0. The domain and range exchange. For an exponential function, the domain is all real numbers, and the range is positive. For its logarithmic inverse, the domain is positive, and the range is all real numbers. The reflection makes the inverse relationship visible. Sequences organize numbers according to position. A sequence is a list with a rule or pattern. 2, 5, 8, 11, 14 forms an arithmetic sequence. Each term is 3 more than the previous term. The constant difference is 3. An arithmetic sequence changes linearly if the first term is a 1 and the common difference is d. The nth term can be written as a 1 plus open parenthesis, n minus 1 close parenthesis d. The n-1 appears because the first term requires 0 steps of the common difference. The second term requires 1 step. The third requires 2. For the sequence 2, 5, 8, 11, the first term is 2 and the difference is 3. The nth term is 2 plus 3 times open parenthesis, n-1 close parenthesis. Simplify. 2 plus 3 n-3 becomes 3 n-1. Check n equals 1. 3 times 1 minus 1 is 2. Check n equals 4. 12 minus 1 is 11. The formula gives any term directly without listing every earlier value. A geometric sequence changes by a constant multiplying factor. 3, 6, 12, 24, 48 is geometric. Each term is multiplied by 2. The common ratio is 2. A geometric sequence is exponential. If the first term is a 1 and the common ratio is r, the nth term is a 1 times r raised to n-1. For the sequence beginning with 3 and doubling, the nth term is 3 times 2 raised to n-1. At n equals 1, the exponent is 0. The value is 3. At n equals 4, the exponent is 3. 3 times 8 is 24. Arithmetic sequences have constant differences. Geometric sequences have constant ratios. One adds repeatedly, the other multiplies repeatedly. A recursive definition describes each term using previous terms. The arithmetic sequence may be defined by saying the first term is 2, and each next term equals the previous term plus 3. This builds the sequence step by step. An explicit formula gives the nth term directly. Both forms describe the same pattern. Recursive definitions emphasize how the sequence grows. Explicit formulas emphasize position. Some sequences use more than one previous term. The Fibonacci sequence begins with values such as 0 and 1. Each later term is the sum of the previous two. 0, 1, 1, 2, 3, 5, 8, 13. The rule is recursive. No constant difference or ratio controls the whole sequence. Patterns can be more complex than simple linear or exponential change. Series are sums of sequence terms. An arithmetic series adds terms from an arithmetic sequence. A geometric series adds terms from a geometric sequence. The sum of the first n terms of an arithmetic sequence can be found by multiplying the number of terms by the average of the first and last terms. This works because terms can be paired. The first and last have one common sum. The second and second to last have the same sum. The list balances symmetrically. A finite geometric series also has a formula, derived from multiplying the sum by the common ratio and subtracting. The repeated middle terms cancel. The result depends on the first term, the ratio, and the number of terms. An infinite geometric series can sometimes have a finite sum. This may seem impossible at first, but it happens when the terms shrink rapidly enough. Consider 1/2 plus 1/4 plus 1/8 plus 1/16, continuing forever. The partial sums approach 1. After the first term, the sum is 1/2. After 2 terms, 3/4, then 7/8, then 15/16. Each new sum moves closer to 1. The total never passes 1. The infinite series converges to 1. For a geometric series whose ratio has absolute value less than 1, the infinite sum equals the first term divided by 1 minus the ratio. If the absolute value of the ratio is 1 or greater, the terms do not shrink towards 0 sufficiently, and the ordinary infinite series does not converge. The concept of convergence prepares the way for calculus, but it begins with an algebraic pattern. A process may continue forever while its total approaches a finite boundary. Algebra is often introduced as a collection of rules. Move this term, change that sign, multiply these powers, factor this trinomial, clear this denominator. But the rules become easier to remember when their reasons are visible, like terms combine because they represent copies of the same quantity. Distribution works because multiplication reaches every term in a sum. Factoring reverses distribution. Equation steps preserve balance. Inequality signs reverse under negative multiplication because the number line reflects. Exponent laws count repeated factors. Negative exponents create reciprocals. Fractional exponents describe roots. Logarithms recover exponents. Graphs collect solutions into visible shapes. Functions describe input-output relationships. Sequences describe patterns across positions. The subjects are connected. Consider one simple expression, 2x plus 3. It can be read as an instruction. Multiply the input by 2, then add 3. It can be a function, f of x equals 2x plus 3. It can be graphed as a line. Its slope is 2. Its y-intercept is 3. It can become an equation, 2x plus 3 equals 11. Then x equals 4. It can become an inequality, 2x plus 3 is less than 11. Then x is less than 4. It can become part of a sequence rule. The nth term equals 2n plus 3. It can become part of a sequence rule. The nth term equals 2n plus 3. It can become part of a composition, or an inverse function. One small expression participates in many algebraic ideas. The topic changes according to the question being asked. An equation asks which input gives a particular output. A graph asks how every input and output pair is arranged. An inverse asks how to recover the input. An inequality asks which inputs keep the output within a region. The symbols remain connected through the same rule. A useful way to approach any algebra problem is to begin by identifying its type. Is this an expression to simplify? An equation to solve? An inequality describing a range? A function to evaluate or graph? A polynomial to factor? A fraction with domain restrictions? A radical equation that may create extraneous solutions? An exponential equation requiring logarithms? a sequence asking for a term or pattern. The first question is not always what operation should be performed. It may be what kind of object is being examined. An expression has no equal sign. It can be simplified or evaluated. An equation claims equality. It can be solved. An inequality compares order. Its solution is often a region. A function assigns outputs to inputs. It has a domain and range. A polynomial may be rewritten in expanded or factored form. The language of the problem tells us the goal. Then inspect the structure. What is grouped? Which operation is outermost? Where are the variables? Are they added, multiplied, placed in denominators, raised to powers, placed inside roots, used as exponents? The position of the variable often suggests the method. A variable added or multiplied leads toward linear equation methods. A variable squared may suggest factoring, square roots, completing the square, or the quadratic formula. A variable in a denominator suggests restrictions and common denominators. A variable inside a root suggests isolation and careful squaring. A variable in an exponent suggests matching bases or logarithms. The structure quietly points toward its inverse. Then consider restrictions before transforming. A denominator cannot be zero. An even root requires a non-negative input in real algebra. A logarithm requires a positive argument. A real-world variable may represent a positive length or whole number of objects. Restrictions are not added after the answer. They belong to the original problem. They determine which transformations and results are valid. Then perform one clear step at a time. Distribute. Combine like terms. Apply the same operation to both sides. Factor. Rewrite with a common base. Take logarithms. Every new line should follow from the previous line. The purpose is not to make the work look long. The purpose is to keep the reasoning visible. A skipped line may be harmless when the structure is familiar, but when confusion appears, restore the missing steps. Write the negative sign. Use parentheses around substituted values. Show the common denominator. Record excluded values. Separate the plus and minus cases. Paper can carry the complexity, so the mind does not need to hold everything at once. Finally, check. Substitute a solution into the original equation. Test a value in an inequality region. Multiply factors to recover the original polynomial. Compare a graph's intercepts with the algebra. Confirm that denominators remain Tunyo. Check that logarithm arguments are positive. Ask whether the answer fits the context. Checking is not a sign of uncertainty. It is part of mathematical reasoning. It connects the final line back to the original question. Many confusing algebra mistakes are not caused by a lack of intelligence. They come from small structural changes. A negative sign is lost. An exponent is distributed across addition. A term is cancelled instead of a factor. A square root is taken without both signs. An inequality is divided by a negative without reversing. A denominator restriction is forgotten. A logarithm rule is applied to a sum. These errors are understandable because the expressions are compact. The solution is not faster work, it is slower reading. Ask what the symbol controls. Ask whether the operation is addition or multiplication. Ask whether two terms are truly alike. Ask whether a transformation can create extra solutions. The expression usually reveals the answer when its structure is respected. Algebra is not a collection of mysterious letters replacing understandable numbers. It is a language that allows numbers to remain open. A variable may be one unknown value, a changing input, a general quantity, or a parameter controlling an entire family of relationships. The letter gives mathematics room to speak about patterns. Instead of proving that 3 plus 5 equals 8 once, algebra can describe why a plus b equals b plus a for every pair of numbers where the operation is defined. Instead of calculating one rectangle, algebra can describe the area of every rectangle with length L and width W. Instead of measuring one moving object, algebra can relate distance, rate, and time in a general form. The abstraction may initially feel less concrete, but it is what gives algebra its reach. One equation can describe many situations. One function can represent infinitely many input-output pairs. One identity can remain true across every allowed value. One graph can show the complete behavior of a relationship. Algebra compresses repetition into structure. This is why letters eventually become helpful rather than confusing. They free the mathematics from one particular example. The equation 2x plus 3 equals 11 gives one solution. but the expression 2x plus 3 describes a whole family of values. The function y equals 2x plus 3 turns that family into a line. The inverse expression, open parenthesis, y minus 3, close parenthesis, divided by 2, reverses the process. The inequality, 2x plus 3 less than 11, identifies a region. The symbols are not separate tricks, they are different views of one relationship. As this journey through algebra comes to an end, return gently to the beginning. A variable is a number whose value may be unknown or changeable. A coefficient tells how many copies of a variable term are present. A constant remains fixed. Terms are separated by addition or subtraction. Factors are joined by multiplication. Like terms share the same variable structure. Parentheses show grouping. The equal sign means both sides have the same value. Negative numbers extend the number line in the opposite direction. Absolute value measures distance from zero. The order of operations tells us how to read a compact expression consistently. Distribution opens products across sums. Factoring gathers common structure back into products. Equations preserve balance. Inequalities preserve order, except when negative multiplication reflects that order. Coordinates turn pairs of numbers into points. Lines reveal constant rates of change. Functions connect inputs with outputs. Polynomials gather powers into structured expressions. Quadratics bend lines into parabolas. Their roots reveal where the graph reaches zero. Radicals undo powers. Rational expressions carry division and restrictions. Exponentials describe repeated multiplication. Logarithms ask which exponent created a value. Sequences arrange patterns through time or position. Every idea grows from familiar arithmetic. The symbols become denser. The relationships become more general. But the basic operations remain. Add, subtract, multiply, divide, raise to a power, reverse that power, compare, group, and preserve what is equal. There is no need to remember every formula at once. Understanding creates places where formulas can rest. The quadratic formula belongs to equations containing a squared variable. Slope belongs to constant rates and straight lines. Exponent laws belong to repeated multiplication. Logarithm laws belong to those same exponent laws viewed in reverse. Common denominators belong to fractions representing pieces of the same size. Each rule has a home. When a rule feels disconnected, return to its home. Ask what operation created the expression. Then ask what operation can reverse or reorganize it. Mathematics becomes quieter when every symbol has a reason. A fraction bar groups. A radical covers its input. An exponent controls its base. A coefficient multiplies its variable. A negative sign reverses direction or indicates subtraction. An equal sign balances two values. An inequality points toward order. A graph turns all those relationships into space. Nothing needs to be guessed from appearance alone. The notation carries instructions. And when the notation feels crowded, it can always be translated into words. The quantity x plus 3, all divided by 5. The square of the entire binomial. The distance between x and 4. 2 multiplied by every term inside the parentheses. A value greater than or equal to the boundary. Reading slowly makes the invisible grouping audible. Then the algebra can proceed one small movement at a time. There will always be problems that require patience. A factor may not appear immediately. A graph may need several points. A logarithmic equation may produce a quadratic. A rational equation may create restrictions. A polynomial may resist exact factoring. Difficulty does not mean the foundation has disappeared. The same principles continue beneath the longer work. Structure, equivalence, balance, inverse operations, and careful checking. A complicated problem is usually not one enormous idea. It is several smaller ideas placed together. Separate them. Simplify one part. Preserve the rest. Then continue. There is no need to race the symbols. Let each line become understandable before moving to the next. An algebra problem does not become more correct because it was solved quickly. A clear method is more valuable than a fast guess, and an error discovered through checking is not wasted work. It reveals exactly which structure needs another look. Perhaps a sign, a domain restriction, a missing factor, or an operation performed in the wrong order. The mistake becomes information. Then the next attempt begins with greater clarity. Tonight, the letters can become quiet again. X does not need to be mysterious. It is simply a place where a number may be waiting. Y may be the output that follows. A graph may be the path they draw together. An equation may be the moment two expressions balance. A function may be the rule carrying one value into another. And algebra itself may be understood as a gentle language for relationships. Let the formula settle without pressure. Let the number lines stretch softly in both directions. Let the coordinate axes fade into the background. The parabolas, fractions, roots, and logarithms do not need to be held in memory all at once. They will remain available when they are needed. For now, it is enough to remember the simplest rhythm. Read the structure, choose one valid step, preserve the relationship. Then check where the step has led. One operation, one line, one quiet piece of understanding, and then another. Sleep well, and good night.